chairs of the session. The session name is Terrestrial Ecosystem, Water Stress and Water Use. I invite the chairs to on the dais, Alberto Olioso and M. Shekhar, IISc. The rapporteur for the session is Kailash Dakore. I invite him as well on the dais. So I hand over the sessions to the chairs, and please you may start.
Shall we go ahead?
Yeah.
So very good morning to all of you today. I hope all of you are doing good and had good rest yesterday. So today we have the first session on surface energy balance and evapotranspiration modeling. I hope I'm reading correctly. And we have 1, 2, 3, 4, 5 talks today, and very interesting talks. And the first talk is by Bimal Bhattacharya from SAC Ahmedabad. So may I call Bimal? We have 15 minutes, Bimal, for you. We'll take all the questions at the end of the session to have full all of them. Thanks.
Good morning to all, and good morning to co-chair and rapporteur. So today I will just take you to through our journey, which is a legacy for our thermal remote sensing and evapotranspiration from Kalpana 1 era to the Trishna, how we have arrived. So Kalpana 1, you know that it was a geostationary satellite in the name of Kalpana Chawla. Initially, it was named METSAT. So it is basically geostationary meteorological satellites. But why we were interested for that? Because that has only 3 bands that included one thermal infrared band, one water vapor channel, and one broad visible band. So our interest was for the thermal infrared and the visible. So next, please. So before I proceed, I would like to mention the contributions of different students, especially in their doctoral studies, who have significantly contributed in this journey from 2007 to 2022. So wherever the circles are there, they are not my directly PhD students, but they have closely worked in through Space Applications Center and significantly contributed. So others, actually, you can see that some of them are already present in this auditorium and have contributed in this journey. So they are now well placed in their growth career, and I believe that in the Trishna time frame also they will be again contributing significantly for taking it forward. Next one. So if we see the global energy balance, and here we are particularly interested for knowing the or determining the latent heat fluxes. And these latent heat fluxes comes from soil evaporation and the plant transpiration. And then it goes to the upper atmosphere forms the cloud, and then cloud recycle back through rainfall. So that constitutes the water cycle. So latent heat flux actually acts as a eco-hydrological link in the water cycle, as well as if you see this transpiration loss from the plants, it actually relates to the stomatal opening and the closure. So there are lot of resistances actually are involved at the stomatal level, at the stomata and relatively upper layer of the atmosphere just above the canopy. So there actually it constitutes the surface conductance and also the aerodynamic conductance. So when water will be available to the roots, so stomata will open. Of course, if there is not much heat stress and the radiation, and it will allow CO2 to enter. So it actually facilitates the CO2 exchange also. So these evapotranspiration and CO2 exchange actually are the coupled process. So there actually the latent heat flux plays as the link for the as a ecophysiological link. So that's why we are interested to know very precisely how much latent heat flux in terms of evapotranspiration can take place. And I would like to mention just two projects of ISRO which actually facilitate us to take through this journey. One, we have started one energy and water balance monitoring from geostationary platform, though that time during 2003-4 we did not have the viable data from geostationary satellite, but Kalpana 1 satellite was just launched, I think, in 2002, but the data actually have started coming after 2007. So, but planning was there. So we have started with the collaboration from different agriculture universities with some portable small instruments to measure the energy balance in the field. We did not have any tower concept, and we did not have the facility or to convince the higher management for taking this sort of tower based measurements. So we have started, I think Kanish was part of that journey. We have traveled together a lot in Punjab and several other regions. And next, when the ISRO community has seen the results and seen that yes, this has some merit, so they have actually requested us to take up a bigger project, which is energy and mass exchange in vegetative systems, which is actually sponsored from ISRO Geosphere Biosphere program. So first project was on Earth observation application mission. We have different platforms of taking up the projects, and this is ISRO Geosphere Biosphere program. So these two projects and these ISRO GBP program actually continues up to 2015. And there, that time we have interacted with Professor Shekhar, we have established tower there. I think still that tower is functioning. And after that also, I think a lot of adaptation of the tower has happened in Karnataka. So next one, please. So this was the scenario. Now, why we require continuous evapotranspiration for water resources management? So first we have to look at the land water budget, what it is. So any budget actually will have the gain and the loss component. So gain component is the water gain through rainfall and irrigation, and the losses is through surface water flow, groundwater recharge, and also the evapotranspiration. So here the when the first two components are very less, then if you see that rainfall plus irrigation will be almost equal to evapotranspiration, and if there is no rainfall, then straightforward, if there is irrigation, no irrigation, you can, it is reflected to the evapotranspiration. So, and these ET actually constitutes almost 30 to 75% of the water budget. So how much dynamicity is involved in this ET part, that you know, and there is lot of uncertainty, especially over India, to know the water budget, because water budget is generally, ET is calculated as a residual of the water balance. So that is not always true. So there should be some independent estimate of ET, which I think we can do through surface energy balance modeling, and where this ET is estimated as a residual of the surface energy balance in terms of latent heat flux. When you know the net radiation, then ground heat flux, and the sensible heat flux, which is going above the canopy to the atmosphere. So, however, this evapotranspiration is required for various scales, like for regional and country scale drought assessment, and also annual water budget or water accounting. And if we uh, go further down to landscape or river basin scale, this is will be required for drought and flood forecasting, change in water use due to shift in land use. And finally, if we go to farm scale or maybe micro watershed scale, we need to know the crop water requirement, crop water use, and then that will dictate what will be the allocation and the irrigation optimization, and it will have implications for the water rights compliance. Next, please. So our first study actually we have done with very small number of in situ measurements and the satellite data. That time MODIS data was only the source for us, and we have taken the MODIS data, and first we tried to estimate latent heat flux through very complex turbulence heat flow computations, where all atmospheric stability, instability parameters actually have to be estimated using Richardson number and many other things. So lot of inputs actually were required. Still, we computed. Of course, this was restricted to very specific some homogeneous agriculture situations where we had few ground measurements, and then we simulate the water balance also for those cases, and we try to plot whether the energy balance ET and water balance ET have similarity or not. So we found that some good encouraging results are there, and while doing that, we have seen that if we take the land surface temperature and air temperature difference and in situ evaporative fraction, which is coming from the Bowen ratio measurements, so 1 minus evaporative fraction, which is actually very well related to this surface temperature, surface air temperature difference. So that has given us good insight that yes, actually we should target first the evaporative fraction. So how to know the evaporative fraction? And then again, we have seen that there is an index called TVDI, temperature vegetation dryness index. So there also with 1 minus EF, we had got very good correlation. So for uh, the gradient of the surface air temperature difference as well as also the surface dryness, evaporative fraction has good relation. So that was our understanding in 2007. Next. So then we thought to bypass actually the complex computations of the atmospheric stability, because uh, finally on real time to incorporate all these things, come up with some certain automated products. So that actually requires a lot of exogenous meteorological forcings. So that may not be always possible. So we thought to make it relatively simple, and then a lot of papers also have come up that time. So this SSEB model, TSEB model, and then land surface temperature, albedo scatter, NDVI scatter, how you can determine. So lot of work has been going on over the world using those data sets. So we also tried that, and then if you just reorient algebraically, so the latent fluid flux can be estimated in terms of the product of the evaporative fraction and the net available energy, which is nothing but the difference between net radiation and the ground heat flux. So this evaporative fraction actually can be the signal of evaporative fraction actually is hidden when you plot the land surface temperature and the albedo. So land surface temperature gives you the emissive properties and albedo gives you the reflective properties. So when these two properties you can plot in the two-dimensional space, so you can have the some kind of triangular space, and there you can define that when land surface temperature is a maximum for given albedo, so that will follow some sensible heat flux which is highest for possible this landscape situation. And so there will be a concept of dry edge and the wet edge conditions. So this is typically the contextual model. However, I think you will hear more from Albert in his presentation, more in depth for the different implementations of this. So I have some more slides. Okay. Yeah. So then from these we have seen that this albedo 2D space sampling window, we have taken the 200 kilometer by 200 kilometer to capture the spatial heterogeneity at 1 kilometer spatial resolution. Of course, we have got good validation statistics of 14%, but that is on the very homogeneous measurements over homogeneous crop patches. However, we have found the over heterogeneous patches, we have got the 23%. And we have found this LST has more sensitivity than albedo because albedo dynamic range is less than the LST. And also we found the time of overpass is very, very important. This aqua time actually gives us the higher accuracy than the Terra overpass. On the other hand, when we have plotted the in situ evaporative fraction versus LAI, in situ evaporative fraction versus NDVI, we found this inverse triangle. And I think this plot, this sort of 2D space has been used by Ishwar later for the disaggregation purpose. And from this work, then we have computed for monthly scale evapotranspiration, and wherever our measurements were there we have plotted this estimated evapotranspiration from satellite and sum up. Then we try to find out this what is the consumption pattern. Whether crop wise consumption, whatever the traditional knowledge we had that rice takes a lot of water, sugarcane takes a lot of water, whether it is matching with that or not. And we have found that it is giving exactly that similar pattern, that where you can see here that rice has higher consumptive water use as compared to groundnut or potato and mustard. So this paper has been published in Agriculture Forest Meteorology. Next one. Then we have, by that time, we have actually the Kalpana 1 satellite, and there you can see this visible, then water vapor, thermal infrared, day, night, and we are having the half an hourly data. And actually, I am very fortunate that I was actually the part of this that era, and I have closely worked with our data products people who are sitting in this campus. And that time we did not have the MOSDAC, and it was initiated. IMD was looking for such kind of products and test bed and all this. So I have seen full journey of these up to Insert 3D 3D, 3DR, and 3DS. So good thing is that the concept of giving some products have come up that time, and that time we have come up with the shortwave downwelling, shortwave radiation. Actually, that time it was very difficult to convince people that what this product will actually tell. So somehow we managed to convince that this product will also help in the renewable energy. So, but on the other hand, this will also be useful for ET computations and the crop yield modeling. So that time, again, this Mehul and team, they have come up with the land surface temperature product. And fortunately, there was another Indian geostationary satellite that time, which is INSAT 3A. So INSAT 3A CCD had the multispectral camera. So we were able to develop the NDVI product, and these radiation and the vegetation products actually help us to actually further work in the evapotranspiration. Next one. And also, that time, our chairman, Madhavan Nair, he insisted that Kalpana 1 data relay transponder should be used for the in situ automatic weather station measurements, and scientists should have the weather data on their desktop. So that's how the IMD also later has adopted this transponder based technique and for getting the AWS network spread over India. But we were given the task that you have to define certain something based on this for agriculture. So immediately came to my mind that micrometeorological tower with the Bowen ratio system, which is with the slow response sensors, can be defined with radiation and the temperature at the vertical levels. And we have put lot of sensors, and there was a network built for experimental purpose in the 20 locations. These network we call the agromet station, and those data were actually thrown to through the EAGI antenna to the Kalpana satellite, and data reception happens in the Bhopal campus, and these data were actually populated to the our internet server. So this was part of energy mass exchange project, and then using that data and also the our resource set data and the Kalpana data, we could arrive at the surface albedo, and there are certain relationships we have developed for the cloudy sky conditions based on the net long wave and net short wave, based on Easium paper, and also the soil heat flux and the NDVI based model, G by RN model. So next one, please. So these actually, then we have plotted the again LST albedo. So again those scattered, but we were actually focusing mainly on the post monsoon season. We did not address cloudy sky condition that time. And then finally we have arrived at the 8 kilometer K1 VHRR evapotranspiration, which we have compared with the Modis Aqua, and we finally got some 26% of the difference if we take Modis as a reference, because 8 kilometer to in situ, again it will give more error. So we have got better accuracy in the wherever the measurements were done or some homogeneous patches are there, but as heterogeneity increases, the accuracy was less because of there are certain footprint matching issues. And also we have found that evaporative fraction actually requires large sampling window to capture the heterogeneity, and in this LST albedo 2D space, conductances we have not actually addressed. What we have, I have mentioned in the beginning, that ecophysiological link. Next one. So we have tried another method, that if we take the morning temperature and the noon temperature and take the difference, and we plot with the NDVI, which is called so-called the thermal inertia versus NDVI to displot. Yes, from the dry edge slope, you can actually see that interannual variability, how in drought and no drought situation, it captures very well. And this paper we have actually published in later, very later, by with Dr. Rahul in International Journal of Remote Sensing. Next one. So we were looking forward to some model which will give the analytical solutions. We were very, we are in close touch with Kanishk. By that time, Kanishk left for UK and then journey to JPL and the list. So he has come up with a new model called Stick. So he will elaborate in his presentation more. However, what we have done is that we try to couple the thermal inertia and the ground heat flux, and this coupled model, actually the pixel based model, and these actually gave us more confidence, and we could arrive at the 25% of some accuracy with respect to the ground measurements, and that with respect to the northern and southern hemispheres. They are actually thermal inertia based heat flux. We have compared with several other heat flux models also, and we found that this thermal heat flux model has certain edge over the other heat flux models. Of course, it was restricted whenever the fractional vegetation cover is actually, but it should not be applicable for fractional vegetation cover greater than 0.5. That was a suggestion by Denis Baldacci. So we have worked on that, because when the canopy cover is more, we have seen that ground heat flux may not be very high, that contribution. Next one. So these I'll briefly mention. Ishwar has actually done the evaporative fraction disaggregation, because finally what he was presenting yesterday is very relevant. So if we have to apply in the precision level, so LST evaporative fraction needs to be actually disaggregated or maybe downscaled. So this is a very good example where he has published in JGR and over Berambati watershed. So we had very long association with Ishwar and Professor Shekhar's team. Next. So finally, eco stress has given us relief in terms of the 65-meter thermal infrared and very good LST accuracy. Though time of overpass is a matter of concern, we have used again this stick model along with the eco stress plus Landsat combination, and we tried to see in a farm that whether it can capture the crop water stress. So yes, within farm, it actually captures the crop water stress. If we take the ratio of ET by PET, so you can get those kind of variability. And finally, we have seen when we compared with the eddy covariance system, then it actually matches, it gives an error of 12%. That is very good. So, and also we have taken the temporal progression. So, ET should have the, again, ecophysiological link with the CO2 exchange. So we have plotted with the net ecosystem exchange, though there is some shift in the peak level. So there is a good match, because when more negative value of NEE will be there, that means more photosynthesis. So evapotranspiration versus photosynthesis you can have. So it shows that the model has a strength, and it has good correlation with the physiological activity of the plant. Next. So this is my last slide. Then if we sum up from the Kalpana to the eco stress level, so from 8 kilometer to 65 meter, in between we had insert 3D and then MODIS 1 kilometer. So if we take in situ as a reference for the, then we have RMSE, we have got from 35% to 12%, though in between I admit the model is changed, but still, I believe from this quantified number that there must be some good role of the spatial resolution of the thermal infrared. So otherwise, you won't get 35% to 12% accuracy. So with Trishna algorithm, I believe the way we have prepared for the contextual models, pixel level model, and many other things, we can achieve our target of 15% error in the evapotranspiration product. However, there are certain research challenges that we have to establish with respect to the evaporative fraction versus water stress. Zeal yesterday has pointed out that question, that whether NISR can help in that. And the global G model and the gap filling, temporal ET scaling, that instantaneous to the daily, and we were in talk for the global availability of the solar radiation from the geostationary satellites. So then CalVal is a very thing you need to have the good reference to have the to tell the accuracy. And then when we get the 60-meter kind of ET, how we can downscale it at the 10-meter or 20-meter. So that is a very challenging thing. And in future, we can try, since Trishna will be providing the noon night, but may not be paired always. So whether thermal inertia based ET can give better estimates or not. Thanks to all of you for your patience.
Thank you, Bimal, for a very interesting talk and the journey so far. So thank you. We'll reserve the questions for the end of the session all together pulled.
Okay.
Thank you. So may I call upon my good friend Kanishk for the next talk? If you can save a couple of minutes, that will be good.
Good morning to everyone. So for me, it gave a great intellectual boost since yesterday when I saw that there are many presentations that have shown that how the stomatal closure is accelerated in response to plant water stress. And this is always set up as a background to explain that how the LSD-induced water stress can be used to constrain evapotranspiration models for the future global missions. So this talk particularly tried to reflect that if we are able to link the two critical conductances with ET through a closed form equation, so what we can contribute for the future thermal mission and what reflection we can generate out of this entire study. So first, let us say what is the closed form ET equation. And here, considering the closed form ET equation, we always consider the Penman-Monteith as the most complete closed form evapotranspiration equation. So if you see this right side box, so this equation is mainly driven by some variables, some constants, and some state variables. In the form of variables, it is driven by net available energy, which is the engine to start the surface energy balance. And it is also driven by the atmospheric vapor pressure deficit, which acts as a pump to pull the water from the plant to the atmosphere. However, it also involves two critical state variables, which is called aerodynamic conductance, which involves the physics in energy balance, and it also involves canopy surface conductance, which mainly involves the biology in surface energy balance. And since we cannot observe these two state variables, application of Penman-Monteith in thermal remote sensing is a big challenge. And another most important thing is that if we think we can measure these two conductance terms at the large scale at which thermal remote sensing is applicable, then of course it gets a green tick that yes, Penman-Monteith is a closed form of equation. However, since there is no universally agreed model of aerodynamic and canopy conductance, so therefore we cannot consider Penman-Monteith as a closed form of equation. And in addition, the structure of the model is not enough to accommodate the thermal remote sensing integration. Because in the left-hand side with this simple energy balance diagram, resistance diagram, you see that the aerodynamic equation of latent heat flux and aerodynamic equation of sensible heat flux, by simple algebraic reorganization, we can express the aerodynamic and stomatal conductance through these two equations, where you can clearly see that there is a large feedback. So while aerodynamic conductance is influenced by the stomatal conductance, and stomatal conductance is also being influenced by the aerodynamic conductance, and there is a clear limit in dry condition to wet condition that which one of these two conductances will dominate or preponderance. So therefore, the objective of the study is to integrate the physics and surface energy balance and land surface temperature with the stomatal conductance theory and formulating the closed form LST integrated Penman-Monteith equation. And the overarching objective is to find out some analytical solution of these two conductances with respect to those variables which we can physically observe, so that we can put the conductances back into Penman-Monteith equation, and we can confidently say that, yes, we have a closed form version of Penman-Monteith with LST integrated. Next slide, please. So in doing so, it tries to do the following. So if you consider, if you carefully check the figure in the right-hand side, so this is a figure in the x-axis. It is divided into two different approaches, image-based or the contextual approach and the pixel-based approach. So these are the two approaches, and in the y-axis, the scale is according to simplicity to intermediate to complexity and from pragmatic to idealistic. So while it tries to set up a complementarity between image-based and pixel-based approach, on the other side, it also wants to bridge the overarching gap that exists between single source and two source model. Because in the single source model, we always have the challenge of having one equation and two unknowns, because sensible heat flux is driven by the aerodynamic temperature, not LST, and we cannot observe the aerodynamic temperature, and it is also driven by aerodynamic conductance, which also we cannot observe. To mitigate that challenge, of course, there are huge study of two-source model, both by USDA and CESBio colleagues and friends, but we all come into one conclusion that, yes, there are two unknown temperatures, we can observe only one, and there are many more conductances and which we cannot observe physically. So now the question is, what is the basis of integrating LST into the Penman-Monteith? So first I had to start with the observational evidence in the Mediterranean climate. So if you see this Penman-Monteith equation, it considers into two parts. One signifies the energy limited environment, and another signifies the water limited environment. In the energy limited environment, it is mainly dominated by net available energy, because in this environment, there are plenty of water available, and this in the denominator, the conductance ratio is mostly approaching 1. So that leads ET to be driven by the net available energy. And in the water limited environment, it is having tremendous net available energy, but it is challenged due to very high soil water stress, that means elevated LST and extremely high vapor pressure deficit. So as a result, the second term of Penman-Monteith equation is more dominant. And when the stomatal conductance is compromised at the cost of increasing aerodynamic conductance, their ratio is tending to 0. So therefore, the second term is also becoming more and more dominant. So if we plot in Mediterranean agriculture or irrigated agriculture, a diurnal plot of radiation and latent heat flux, we can clearly see that the typical bell-shaped curve under the clear sky of radiation, but there is a large diurnal asymmetry in latent heat flux, and this large diurnal asymmetry is created when there is a progressive decline in stomatal conductance as compared to the aerodynamic conductance. And to understand it more, here we have plotted this conductance ratios as a function of LST with in situ data, where this ratio is the significator of stomatal stress or biophysical control. And what we found is we could clearly see that with increasing LST, first the ratio increases because these are the conditions under the humidity controlled environment. There are plenty of humidity in the atmosphere. So despite LST is increasing, plant can still transpire. But after one point is reached when the vapor pressure deficit is also increasing along with the land surface temperature, that means when from the bottom and from the top, when we are reaching the aridity limit, then stomatal control is becoming more and more significant. As a result, the conductance decreases. To understand it even more better, that what is the timing of this kind of decrease, we plotted the same graph for different time of the day, and you can clearly see that the plot in the inset, that these increase in conductance ratios are more until we reach around 11 o'clock or 12 o'clock, but after 12 o'clock, there is a clearly declining pattern. So this is a great coincidence because the Trishna launching, the overpass time will be at 12:30 in the afternoon. So that means we will be doing the thermal remote sensing acquisition exactly at the time when the water stress is kicking in. So this is very good signal for the thermal remote sensing community. Next slide, please. So this is another beautiful picture of the woody savanna. And you can see that almost for the same magnitude of net radiation, there is a even maximum diurnal asymmetry, and that diurnal asymmetry starts from 10 o'clock in the day. Because if you see the this scatter diagram, here what we found out is due to the strong stomatal control, which is 10 times larger as compared to the even the Mediterranean agriculture and the irrigated agriculture, we could clearly see that there is very small time during the early morning in the day between 8 o'clock or 10 o'clock when there are little bit relaxed, plants are operating under a little bit of relaxed environment. But after 10 o'clock, they are extremely stressed. And as a result, there is a very strong stomatal control with high atmospheric aridity and high land surface temperature. So these, next one, please. So these are the two examples, but there are many more examples which I cannot share because of the time constraint. But these observational evidence says that we have a possibility to develop the closed form expression of the conductances as a function of LST, and which could apparently facilitate the physical integration of LST into Penman montate. So in order to do that, we took the model surface temperature initiated closure. I'm not going to go into the detail of the equation. It has been presented in many different symposiums, but the overall structure of the model is like this. The variables that is presented in the red color, these are the variables which we cannot observe. So what we wanted to do is we wanted to retrieve these variables from the surface energy balance theory, and we wanted to use those remote sensing and environmental variables which we can physically observe. So what are the inputs here? We can use LST, which is available from the thermal sensor. We have broadband emissivity, we have broadband surface albedo, we have we have fractional vegetation cover. And with respect to meteorology, we have downwelling shortwave radiation, either from geostationary or any weather-based model. We have air temperature, dew point temperature, and relative humidity. So using these and using net available energy as an engine, land surface temperature as a fuel, and VPD as an atmospheric pump. So we form different state equations of conductances, aerodynamic temperature, and we used advection aridity hypothesis to form state equation of evaporative fraction. So we can solve these state equations. However, there are more unknowns. So after some initial estimates of latent and sensible heat fluxes, we iteratively solve the aerodynamic variable. We iteratively solve coupled ground heat flux, and we are able to get closed form expression of this conductances, evaporative fraction, and plus as an additional the Priestley-Taylor coefficient. And finally, we have an LST integrated closed form version of Penman montate. Now to test what is the region of evaluation. Why I like Mediterranean region, because these are the regions where there is a very strong coalition of soil moisture, drought, dry down, and atmospheric vapor pressure deficit. So it is extremely low in fuel, I mean high soil water stress, which is shaking hand with extremely high vapor pressure deficit and very strong engine. So in order to evaluate, we used Landsat 8 and 9 LST at 30 meter spatial resolution, and in combination with Sentinel-2 VIS NIR. And this evaluation was done over 4 sites for a period of 8 years. And because of the predominant clear sky availability, so we could be able to extract almost 92 data points per site. So we could be able to validate this approach over more than 350 data points in California. Next slide, please. So here is an example that how does stick reproduce ET variability. This is the instantaneous latent heat flux. The first one is for alfalfa, and then the second one is for corn. And you can clearly see that there is a phase of dry down and greening phase. And mostly these are the regions where in summertime, this almost doesn't get any rainfall. And the model is able to capture the greening and dry down phase. And for me, the most important part that I was interested in how the model is behaving when fractional vegetation cover is extremely low, and which is combination and plus the combination of soil and atmospheric water vapor deficit. And next slide, please. So this is the natural ecosystem, Tonzi Ranch and Vaira Ranch. Many of you know about these two ecosystems, and some of you might have visited. So you can see there is an extremely high soil moisture dry down where summertime latent heat flux almost goes to zero, or between 0 to 100 watts per meter square. And on the other side, it is driven by extremely high energy. And here also we could clearly see that during the summertime, the model is able to capture the extremely low latent heat flux values. Next slide, please. So next was how does the evaporative fraction compares, because evaporative fraction or the ecosystem stress is one of the central point of Trishna mission. So this is the first plot. It compares the evaporative fraction from stick versus evaporative fraction measured for a range of LSTR temperature difference, because we know that LSTR temperature difference is one of the indicator of crop water stress. So we could clearly see that the points are very well distributed in both the sides of one-to-one line, and it could clearly capture both the energy limited and water limited environment. However, the normalized RMSD was 40%. And then we wanted to understand then how the soil and atmospheric water stress and vegetation fraction is contaminating the model bias. So the first plot in the right-hand side, we plotted the bias in latent heat flux, and in the x-axis, it's a LST, where the range varies from low soil water stress to high soil water stress, and the variation in the point color is according to the atmospheric water vapor deficit, which is from humid to arid. And although we didn't find a very high systematic error, but still there is a significant systematic error with a correlation of 20% in both the cases. And what we have found that when there is extremely high soil water stress or acute soil water stress plus atmospheric water stress and very low fractional vegetation cover of less than 20%, still we have a tendency to get a little bit of overestimation. Next slide, please. Now we have a long-term debate that what are the effects of percentage of surface energy balance closure and on the ET model bias, and whether there is any role of soil water content in instigating that bias more. And then what is the impact of percentage of surface energy balance closure and vegetation fraction of model error. So this footprint, you all are aware that the footprint in which the ground heat flux is measured, which is very little at a tiny point as compared to the entire footprint that is covered by the eddy covariance fluxes and net radiation. So as a result, next slide, please. So the first scatter, it shows the bias in latent heat flux versus energy balance closure. And here also we could see a significant trend in the energy balance closure when we plotted the bias with the closure for a entire range of soil water content, which ranges from saturation to wilting point. However, the relationship is very weak. So despite we are using our analytical model, still the points are well distributed, but clearly we have found out that under extremely low soil water stress, still there are more bias we are getting, and that is exactly falling with the very low fractional vegetation cover or when the surface is very bare. However, the systematic error is low across water stress and vegetation fraction. Next slide, please. So here is the first reflection. The first reflection is that we must use dual conductance to determine the ET responses to LST variability, because the first thing we need to understand what is the capability of our ET model to reproduce the generalized behavior of the conductances. So the first plot, we evaluated for the first time how the stomatal conductance from the thermal remote sensing compares with the stomatal conductance that we get in the across the eddy covariance scale. So there is a significant relationship. The correlation was not super strong. It was around 50%. But what we realized is the critical factor is also aerodynamic conductance, because the aerodynamic conductance we got weak relationship. However, we are getting a compensation effect of the conductances when we plotted the ratio of the conductances observed versus predicted. And why this compensation is happening? Because again, if you see the Penman-Monteith equation, in the denominator of the equation, we have these two ratios. So these two ratio, their good relationship is compensating the effect of poor relationship for the aerodynamic conductance. Next slide, please. I just have 3 more slides to share with you. So now the next question is how we are going to use this closed form ET model for the thermal mission. I'm really thankful to Simon Hook, who recommended this kind of work to European Space Agency, and I was given the responsibility to lead the development of European Eco-Stress Hub, where we wanted to test the structurally different ET models and LST. In the first phase, and apparently we aim to generate time series clear sky LST, ET, and GPP at high spatial temporal resolution. In one to 1.5 years, all these data products will be available. And I'm going to show the 2 preliminary results. In the phase 1, we evaluated stick with 2 different other models. One is surface energy balance system, which is a single source model, and another is a 2 source energy balance model across different range of stressed to unstressed environment. And here we could clearly see that all the 3 models, they are producing a systematic bias under acute water stress condition. And these are the also conditions where latent heat flux is extremely low. And the detail of these results are available in our publication, you can see. And to understand that why this kind of acute water stress is producing systematic bias, this is a recent study that we did. We wanted to study the impact of LST on ET and conductances. So what we did is we generated LST from 2 different algorithms, split window and temperature emissivity separation. And we ran our ET model with these 2 algorithms, and these are the results of cropland and grassland. So in the left-hand side, what you can see, the remarkable thing that we found out, that for LST deviation of plus minus 2 Kelvin, we have found that the percentage ET deviation in savanna is remarkably higher as compared to cropland. And this high sensitivity is generating because of extremely super sensitive nature of stomatal conductance due to LST deviation. You could clearly see that between plus minus for negative 2 Kelvin, the LST deviation, our percent deviation in stomatal conductance is reaching close to 200%. And this relative sensitivity of stomatal conductance is way more higher as compared to the aerodynamic conductance. And that's why in the reflection, as I mentioned, that we should take care of the dual conductances. So this is my last slide. The second reflection that I get for myself, that is, we need a transformative approach when there are acute water stress. We may think of using the TIR and shortwave infrared synergy and emphasizing more the role of stomatal conductance more in thermal ET models. However, if we keep on thinking using this kind of analytical model, these are relatively less data intensive, and it could facilitate the operational ET generation relatively easier to implement regionally. And the most important thing that I see is LST, it takes the picture at a single snapshot. Like we have the whisk broom sensor. So at that microsecond and milliseconds of exposure, we are transforming this radiant signal into LST, and then we are using this complex energy balance model into ET. So how much error we are generating in each and every step. And then when we are comparing this with a continuous observation of evaporative fraction or evapotranspiration, and under extremely dry environment, even if we are getting 30 to 40% error, we can still thank ourselves that we are able to capture the signal, and then how best we can use the other sensor signal synergy to narrow down the errors. So with this, I would like to thank you all and all the Trishna colleagues, my EcoStress colleagues and LSTM, and we hope to work more with you in the future and bring forward and generate more knowledge for the future generation. Thank you.
Thank you, Kanish. Can you have the next presentation by Patel from Indian Institute of Remote Sensing?
Good morning, all. Much has been talked about how food security and water security is linked, just like gross photosynthesis and evapotranspiration coupled. So water security, that has got major implication on food security, productivity. So we need to improve water productivity, particularly more crop per drop. How we can produce more crop per drop. So this is a presentation to address how field scale evapotranspiration can be used for improving or monitoring water productivity and finally production. Next slide. So as we all know, accurate assessment of evapotranspiration is very much important for field scale ET, which is providing valuable information for quantifying water stress, water use, crop water productivity, and finally production. Much has been talked also about how this surface energy balance can be used with the thermal remote sensing data and certain optical data. So if we use thermal remote sensing data with certain high resolution satellite like Sentinel, which not only provide high resolution land surface temperature, but also improve temporal scaling for calculating surface energy balance. Besides, Sentinel also has got Sentinel-1, which provides micro backscatter, mainly SAR data. So if we model SAR backscatter, certain parameter of SAR with the evapotranspiration, highly trained model with the machine learning technique that can be used to gap fill when there is a cloudy season or rapid moisture change. So that with that objective, we have used both the surface energy balance, calculating ET as a residual of surface energy balance, mainly SABI model, and also together with the machine learning model to gap up certain during cloudy period. So this is the objective to generate high resolution LST image through this aggregation strategy, map evapotranspiration with satellite thermal energy balance model, and also to demonstrate applicability of this high resolution ET for water productivity and yield prediction. Next. So these are the various data of Sentinel, Landsat, INSAT, flux tower observation, meteorological data, instrument, all we have used for one Saharanpur site. This is I wanted to bring to your notice. This is a one part of the one project, National Carbon Project, Soil Vegetation Atmospheric Flux, which is led by our mentor, Dr. Dadwal Sahab, who is present among us, who has set up first time in Indo-Flux network for taking EDCORA's measurement across India. So this is one of the site which is we are measuring carbon and water vapor exchange over sugarcane ecosystem. Next, so we are taking measurement regularly, both flux tower, leaf area index, soil moisture, and all other PAR, FPAR at the Saharanpur site for not only water vapor exchange, but also carbon exchange and understanding major ecosystem process which is required for developing models. Next. So here you can see how carbon and water flux are tightly coupled. So we can see the uptake during the daytime and release during the night time. And it is also following the same fashion with the leaf area index, means ginness, and also evapotranspiration. So this is a site where we are monitoring for last 4 or 5 years for energy and water vapor and carbon exchange. Next. So first objective, that is downscaling. Here mainly we have used not linear regression. We have used polynomial regression technique. First between the coarse resolution Landsat 30-meter data with the Sentinel 10-meter optical reflectors data. So after developing certain polynomial regression, we have applied to the continuous time series of different vegetation index to map this 10-meter resolution LST through disaggregation strategy. Next. So these are various dates. We got a good amount of this agreement or the coefficient of determination for different techniques. Next. So you can see here land surface temperature for every month. First we have computed for with the disaggregation strategy for the Saharanpur site. Next. You see clearly distinct field boundary also after downscaling of LST with this polynomial disaggregation strategy. Without downscaling original, you can see there is a shaded or fed up boundary. Now clearly distinct, even field boundary and fields are visible. So all across the whole growing season of sugarcane, we could able to derive this. And also to certain extent, we have validated with tower data, mainly temperature. So you are seeing here systematically some 25 to 30% overestimate. That means temperature is higher than land surface temperature throughout the growing season. Next, also we have tried to use thermal camera, FLIR thermal camera at high resolution to validate this land surface temperature for the different crops in the different sugarcane and as well as other crops. So particularly sugarcane, we are getting good agreement because that vegetation stage was almost green vegetative stage. Other crop either soil background was much exposed, so we couldn't get much accuracy with the thermal camera and downscale LST. As for remote sensing energy balance model, there is a good amount of knowledge being collected. So over the period, many energy balance model being developed. Initially contextual model, then two source, single source. Nowadays, everybody is talking about multi-source ensemble model, where machine learning, thermal energy balance model, as well as land surface model, all are coupled, integrated to derive high resolution as well, both partially and temporally evapotranspiration product. Next. So here we have used mainly SABI energy balance model, which what already Dr. Bhattacharya has talked about. So we have quantified here evaporative fraction by using dry age and cold age by parameterizing that TS NDVI space through trapezoid manner, mainly albedo, NDVI albedo. Then this evaporative fraction we have multiplied with the available net energy to get the evapotranspiration. Next. So here you can see these are the different sort of equation what were employed. Main satellite input is leaf area index, inside based solar radiation, albedo, vegetation cover fraction, MEGT. So 5-6 input variable which we have used from the satellite, and finally try to parameterize this evaporative fraction at the 10-meter resolution scale. Next. So classification next. Here you see the partial pattern of evapotranspiration, which is okay, ranging from 0 to 7 mm in general at 10-meter resolution scale. For some selected that, we further work, we have gap fill and derive more temporal scale evapotranspiration. Next. Here, finally, okay, 10-meter grid scale, we have presented in the field scale, one field, which is where our tower is located. That particular village, you can see there is a dynamic variation in the within the field as well as different field with respect to the ET. And it is matching much more up to September or October. Means just okay, sugarcane is ripen or mature. Up to that, it is closely matching. Then after we are seeing little bit deviation between the ED chorus evapotranspiration estimate and the high resolution ET estimate. This may be because mismatch of the tower footprint. This flux tower may be having a footprint of 100, 150 meter, but 10-meter resolution, that is a very highly heterogeneous. So you will find many, okay, it is more homogeneous, but this is a within that 100 or 150 footprint, there may be fallow land, there may be some other crops. 70% is sugarcane, but there are other covers. So it is the average ET from the AD chorus is the average flux. But here you are getting high resolution, so there is a mismatch is also there. Next. So this, okay, so high resolution ET we have used for the derived crop yield prediction, already relative evapotranspiration model at the high resolution for estimating field scale crop yield. Next. You can see same village we have estimated field scale yield and crop cutting experiment we have carried out for the certain field. And we get very good, okay, agreement between the crop cutting experiment based yield as well as relative evapotranspiration model applied at the 10-meter evapotranspiration estimate. Same data also. Next. We have used, this is okay, we have done for the every weekly for whole time series. My PPT is not working, not loaded, but this is a slide slow. Every weekly, we have estimated gross primary productivity with the both Sentinel-1, Sentinel-2, and Landsat. Then evapotranspiration on a weekly basis. Then we try to estimate water productivity for that particular village, every field scale, and we can get that is a high water productivity, high evapotranspiration, even it goes up to 10 meter. So this slide slow is not working. Okay, next. Here, this also, we same technique we have also applied to another, our large scintillometer tower is there. There we also could be able to estimate every weekly 10-meter resolution evapotranspiration for rice and wheat, and it was interpolated to get the daily time series of the ET with the gap fill model from the machine learning based Sentinel-1 based machine learning model. Next. So here you see rice water productivity. This is a little bit lesser than the wheat productivity. It is mean productivity is around 0.62 mean water productivity, but wheat productivity is around 0.8. Next. So this is a field scale what we can get for the annual time series with the ratio of crop yield and ET. But at the same time, we could able to monitor also physiological water use efficiency for understanding ecosystem function. Next. So what there are certain challenges and scope. What as Bhattacharya has said, we need to improve partial temporal resolution of satellite sensor technology like Trishna, LSTM, which can match real requirement of irrigation management or decision support system for the irrigation scheduling. Also, we need to improve latency period, like okay, near time availability of ET retrieval. That can really help farmer for some irrigation to get the better irrigation advisory service. Finally, development of this all RS technology has really improved computing technology, big data, cloud computing, everything nowadays is available for better operational management of and also hydrological monitoring, crop water management, and finally improving productivity and to certain extent achieving climate resilient agriculture through study like okay water and carbon linkage we can better identify which are the hotspot area of water saving practice and so on. Next. So we are involved, okay, Indian Institute of Remote Sensing also trying to participated with this, okay, Trishna mission. We are going to provide these 3 calibration and validation site for energy and mass exchange and productivity. So these 3 sites already we have participating at the Palampur in Himachal Pradesh, then Saharanpur, and then one is in Pannagar, Uttarakhand. Large aperture scintillometry, which gives 1 kilometer path length evapotranspiration. So we are getting this all continuous data, and we are using this all for understanding ecosystem processes, both water and carbon exchange with the Trishna mission. Thank you.
Thank you.
Yeah.
Thank you, Patel. We'll take the questions at the end of the session so that we can group in one shot. So next, can I call Rahul?
Very good afternoon, good morning to all. We are here to manage the agriculture water management. I am trying to also manage the time here. So I'm presenting this effect of diurnal and angular thermal infrared measurement on field scale evapotranspiration. Basically, we have done a field-based study only, and I've showcased you some result what we obtained using our field-based study and do some modeling. Next. The background, in India, we are having a very over usage of water. So precision agriculture play a key role for water management. And it is highly scale dependent. If you want to do a precision agriculture, people are doing it for costs very high. But India demand very high spatial resolution data for precision agriculture. And for this, ET is most important thing to generate the water footprinting from any field to regional scale. And in past, we have used different type of approaches, already has been mentioned, so I'm skipping this. And moreover, very important is that we are only doing a single time observation and trying to generate a diurnal ET. So that is the function of many meteorological and surface parameter. And we have to see how it is affecting the daily ET quantification. And regarding LST is highly dependent upon the angle also, and it changes if you change the angles. The difference from the normal nadir to different angles go up to 16K and 12K in different type of ecosystem. Next. So at present, what we have a past experience. In the past, we have generated, installed near about many towers in different agro ecosystem in Indo-UK Encompass project, and in which we have collected a lot of data, and we have make our understanding in a better way that how different agro ecosystem, atmosphere and soil has been coupled and vegetation is coupled due to different meteorological and land forcing. Next. So in this, you can see what we have data collected from the different sites. I have just give you a very rosy picture because in the first left-hand side, you're seeing the diurnal variability of latent heat flux in the different vegetation phases. In vegetative phase and advanced vegetative phase and ripening stage, how the ET diurnality is decreasing. But it is a very rosy picture because it is also a function of advection. And because of advection, and advection is a function of wind velocity, so it may change very fast also. So diurnality will affect, but I have showcased for a simple reason, I showcase you a very simple picture. Next is the albedo. Albedo is a diurnal we have seen, so that's why the albedo value remain constant between 11 to 2. And similarly, if you plot the diurnality of latent heat flux for different ecosystem, you see how much fluctuation in a particular day we are getting in different ecosystem. I'm just taking the 2 more contrasting agro ecosystem. One is JSM, which is Jaisalmer, which is a totally a desert area, and one is SMS, which is Samastipur, is a humid area. So this is a totally irrigated area. So you can see how much fluctuation in the diurnality is there. So when you're taking the one-time observation, how much you are sacrificing when you're doing the daily quantification. Similarly, then in the vegetation part also, we have some diurnality, but that is more stable. Next. And you can see the diurnality in you can see in every month. It is starting from January, sometime name is missing, from up to December. I have plotted diurnal plot, and you can see the partitioning in a semi-arid region of India, how the partitioning is affected in the different. This is starting from January, Feb, and March. And you can see in In the sixth, you can see the sixth because the sixth graph is representing the summer, how you can see the change in the sensibility part, which is represented in the red. So you can see maximum energy now is partitioned in the sensibility part. And when the season is changing, the partitioning is going to be changed in different latent heat and sensible. Next slide. And you can see also the diurnality of that vegetation fraction also during the clear sky and cloudy sky. In cloudy sky, the thermodynamicity of the system is more stable. That's why the evaporative fraction more or less remain going to be 1. But in the case of clear sky, the lot of fluctuation is there. So it is clear that if you want to address the diurnality, you need more and more data sets. Next. So this is our experiment. What we have done, we have collected data using thermal camera. And we are also using the hyperspectral imager snapshot to generate the vegetation reflectance. We also have an albedo meter, and we also have different other systems to generate the data sets. And we have a nearby observatory of Indian meteorological departments where we have taken the air temperature, humidity, other things. So this experiment has been conducted in 2 sites, and in the center part of India, this is Ujjain and Vidisha, and the crop was taken is the wheat crop. So we have seen that how the changes is changing in the different environment from vegetative phase to ripening stage. Next. So this is just a snapshot of a morning time to afternoon time, how much change is there, and the contrast of this image will change when you have a different type of object in the field also. So when you are taking the only one field, you are more or less getting the same type of color, but you have more things like a human being also, then the contrast is different. Next. So this is the ET model. We have taken the Kanishka models or stick model because this is the most best method we can use on a very high spatial data. So this is the 5 centimeter data. So we have used this model only, and I am not going to detail because already Kanishka has elaborated in a better way. But we have tested this model in the different part of India, and so we are confident about this error part. So that's why we have opted this part, even though we have used different model also for this study, but they are not giving us very conducive result. So that's why we have not presented here. Next model. Next. So in the first experiment, what we have done, we have used taken the data in a diurnal way from morning to afternoon hours, and we have seen there is a change in that land surface temperature. Because this is a Feb month, the change is very less, and change in albedo and NDVI is also very stable because the system is very stable. So we have seen, even though when a crop is in a vegetative phase, there is a very less change in the LST is happening, and that is also reflected in ET part also. So this is the first experiment when we found that in the vegetative phase, the diurnality is not going to change much. Next. In the second experiment, what we have done, we have used the data of in a ripening stage of data and taking the measurement in morning hours, afternoon hours, and late afternoon hours also, where we have seen there is a lot of change in the LST part, and that is also reflected in the ET part also. The diurnality is affected in this particular experiment. So that is a ripening stage. And third experiment, what we have done, we in the vegetative phase also we have taken the data of thermal data in different angles. So we have taken the data in different angles between 12 to 12:30. That is a Trishna pass. So we have taken the data in that part, and then we have seen that how if the ET change in the 10 degree from Nadir, the 2 to 10%, 4 to 15, up to 22% change in ET is observed with the change in the angle from 10 to 50 degree. And similarly, the LST is going to be changed up to 26%. So that is very important thing when we are doing, because in Trishna, we having, even though we have a 3-day data, but exact view angle repetition is in the 8 days. So the angle correction is very important. Otherwise, the angle will give you a lot of error in the ET estimation. Next. So this is a conclusion that the diurnal behavior of ET is also a function of crop phenology. And we have seen, and there is a change when you're changing from vegetative to phenological stages, the diurnality effect, and that also affect LST part and ET part also. And crop growth progress from vegetative maturity its water demand is very different what we have in the final phase. So that's why the ET diurnality is affected. But here important thing is that when we have taken the experiment and taken the thermal data, we make sure that wind is very calm. Because in our past experiment, just recent experiment with G's in Berambadi, we have seen that wind is playing a very fast, very high speed is there. So we are unable to even to get a ground data also. So that's why when we are taking this type of ground experiment, we make sure that the wind should be very calm. Otherwise, that this advection effect will be play a very vital role, and your experiment will be totally disturbed. And this study can be a valuable contribution to map ET and monitor the ET terrestrial ecosystem using noontime thermal observation and registering for future missions like Trishna. So the message is that when we try to model diurnal ET, you also have to take care about the wind component, because that will be affect a lot, even though we are taking the solar radiation, but wind also play a very vital role when you estimate the diurnality of the ET and the daily estimates. Thank you. Now, last slide. Thank you.
Thank you, Rahul.
Thank you.
Thank you. So may I call now Atira, please?
Good morning, all. I'm Adira, and my presentation is on the topic comparative analysis of temporal upscaling methods for daytime ET estimation. So using thermal data, when we are using thermal data, we are estimating ET at an instant, and then afterwards for various applications, we are getting daytime ET by scaling using multiple scaling factors like evaporative fraction, solar radiation, net radiation, etc. So the basic assumption behind this scaling is that the scaling factor will remain same throughout the day. So that is known as the self-preservation of the scaling factor, but this may not hold true when there is like a cloud cover or some kind of changes. The assumption of self-preservation may not hold true. So when we are estimating daytime ET by scaling, there may be a factor of error that is coming due to this estimation. So this assumption. So in this study, we are trying to see if the availability of diurnal ET is going to improve the daytime ET estimation when compared to that of availability of a instantaneous LST. So the study was done at two sites, Navagam and Maligaon. Navagam is in Gujarat, which is a rice and wheat field, and Maligaon is in Maharashtra, and it's a vineyard. So the study was done for a few cloud-free days on these two sites. So the overall methodology that I have followed is LST from MODIS at 10 a.m. or 1:30 p.m. is given as input to the sparse model to compute ET at instantaneous, that is at 10:30 and 1:30 p.m. Then later on, this is scaled to daily ET using incoming solar radiation as the factor. And the other method is like we have 4 LST observations from MODIS during a day. So this LST estimation is given, this instantaneous LST is fitted using a DTC model to get diurnal half-hourly LST values, which is given as input to a sparse model, and thus we'll get a half-hourly diurnal ET. And I have averaged the daytime ET from the model to get the daytime ET. So only the daily towers of ET is only average, so that night effect is removed, and all the other variables which is required as input to sparse are taken from the field only. And this daytime ET estimated from the 3 different LST sources combined with the in situ measured ET. Like half an hour in situ ET is averaged again to the daytime ET, and that value is combined with the 3 daytime ET obtained. So this is the diurnal curve at Navagam site on 2 different days of LST as well as evapotranspiration. So here it shows like ET is able to get the diurnal curve as such. The ET model is able to get the diurnal curve, but there is some error at some point. There are like higher error at some point compared to that of other times. So similar results were seen in Maligaon also. The model was able to capture the diurnal ET, but there is like an error factor in some of the places. So this is the RMSE in mm per day obtained when MODIS diurnal LST was used to compute ET, and MODIS LST at 10:30 as well as 1:30 p.m. was used to estimate ET. So here we can see that when we are using MODIS LST to compute ET, and then when we are scaling it into daily ET, we are getting lesser error compared to that of diurnal ET availability. So the box plot shows the percentage error in the daytime ET in comparison with the in situ daytime ET. So here also we can say there is less error when we are using the MODIS LST at 1:30 to compute ET and then scaling it into daily scale. So to further investigate why this is, so we have computed the percentage error of estimated ET as well as NSE for every hour from 8 a.m. to 4 p.m. Using a time series of data. Not just a few days, but a time series of data from multiple sites were used to compute what is NSE as well as percentage error with respect to the observed ET. Using, we have included two more models, PTGPL as well as stick also. So we can see that around the noon time from 12 to 2, there is like a less error in terms of ET as well as there is a high NSE values. So this implies that models are performing better during the noon time from 12 to 2. And this may be the reason that our scaling of 1:30 ET value to daytime is giving us better results compared to even when we are having diurnal ET. So in conclusion, like the sparse model was able to capture the diurnal pattern, but the traditional temporal scaling approach, when we were using 1:30 p.m. LST, was giving much better results compared to that of even diurnal ET or the LST values that we used at 10:30 a.m. This may be due to the model performance, which is better during the noon time. Even we can see that as day progresses, like afternoon or before noon, we can see that the models were not performing much better. So if we need to model in terms of thermal TIR based ET, we have come a long way, but we have to improve in terms of diurnal ET modeling. So we may have to do some inclusion, like we have to improve the model in terms of radiation partition, diurnal variation of radiation partitioning, aerodynamic or stomatal conductance, as well as the soil heat flux variations. These kind of studies are important when there are like intermittent cloudy days, like in certain day there is like cloud, and for some particular day scaling may not help, so that during those such days we may need a diurnal ET. So this kind of modification need to be included so that we can do a better diurnal ET modeling.
Thank you, Atira. So the session saw very interesting presentation starting from Bimal, then Kanishk, then we had Patel, and then Rahul and Atira. So the session is open for queries to the presenters. Please.
All presenters can come to dais.
Hoping we'll have questions. Yes. So can we have a mic over there, please? Or maybe if you want to come down.
So my question is related to use of ET to estimate field boundaries. I saw some interesting results where field boundaries are also estimated. So I guess large-scale empirical data sets are now present for field boundaries. Has there been any study on use of ET to determine these? And for the ET measurements that you presented, Kanishk, what is the scale of ground truthing that you were doing? What is the scale of ground truth measurements that?
So there's mic there also.
Hello. So this particular for field boundary, how we have captured field boundary? Because this field boundary we have captured with the GPS survey. It is available with the mill, sugarcane mill catchment area. Every sugarcane mill catchment area, they are doing every year field boundary survey, GPS survey for each and every sugarcane field. So that field boundary survey we have got from the sugarcane mill catchment authority.
So you asked me about the footprint, right? The measurement scale. So as you can see that I showed the results of the heterogeneous ecosystem. So it's a Mediterranean. So when the corn is of course not mature in the early vegetative stage, so then the scale is of course going to be very much less, like I would say 50 meter to 100 meter, that the fetch ratio.
Of farms that you were covering, not like the spatial resolution.
And it's based on the Landsat data. So 1 pixel size is 30 meter.
Right. So not the spatial resolution, but how many places did you measure?
It's one eddy covariance tower in one farm.
Only one tower.
Yes, one in the cornfield, another in the alfalfa field. They are permanently installed, one in grassland and another in woody savanna.
Thank you. Yes, please. Maybe you can
good morning,
introduce
everyone.
yourself, your name.
Yeah, I'm Dr. Shesha Kumar. Just I'm looking after agro advisory services from India Meteorological Department. So I also worked with the SAC for some time. So I worked with Bimal sir. Sir, as you said, sir, as you presented all of the wonderful presentation, very informative. So we can use this to the field scale as well. So thing which I observed is, sir, what you show. The field observation mostly were collected from the agricultural land only. So there are 15 to 16 land use land covers are there in India. How we were using information from those land use cover for calibrating this Trishna mission. Kanishka sir, you also said that the stick model maybe you showed is only calibrated at the land use land cover, this agricultural land. So what about this natural vegetation? So where this Trishna will take observation from that also. So how that factors can be incorporated into that monastic model. And so Patel, sir, you said we have developed some irrigation model which can be used for irrigation scheduling and all. So in case if there is any model, operational model, which can be shared with us so that we can implement it in larger scale. So two are just wanted for my information. One is for strategies where we can scale up. So that we want.
Hello. Yeah, Shesh, it's a very good question. Actually, we have dedicated session tomorrow on Calvel. Okay. So there you will come to know that for validation of the ET products, we have categorized the land use wise between the agriculture and the natural vegetation. So for agriculture, we have taken C3 and C4 crops. And for vegetation, we have taken the different forest types. Okay. But not too many. So we have taken a stock of the eddy covariance tower availability and the data from different agencies within ISRO and across the ISRO. And I believe that there must be some more also, because from Dr. Dadwal's presentation, I came to know that 35 such flux towers are available. So we are inviting all to be part of this Calvel team. And apart from that, there will be also data availability from the French and some other global sites. Okay, so in that way, I think the agriculture and natural forest sites measurements will be available. Only thing is that the people or scientists who will be associating or will be associated with the Calvel activities, they should volunteer the data through a proper access mechanism. Anyway, that detail we will discuss tomorrow. Thank you.
For Kanish, there was some question.
If I understood your question about the model calibration, right? So here, stick is an analytical model. So calibration only concerns if you are using the prescribed function of conductances when you need to change the parameter or aerodynamic parameter. So that's why in the methodological slide, I clearly said that it doesn't need any conductance parameterization. So as a result, I need not to adjust any calibration parameter. Yeah, it can work on across any surface. So the only thing is I didn't check it on concrete or over the complete sand. The reason being, then we don't know what is the ground heat flux. That's why. Yes, yes. it works always even much better in forest vegetation. But since we are working on the Trishna is all about water stressed ecosystem. Here I presented the most difficult sites, and we wanted to see that how much error it can generate, because we should not be shy of showing our error instead of showing, because we have an utopian world, we are all used to seeing 90% correlation and perfect evaluation. So I'm slightly away from it. I try to show where it is not working and try to find the reasons. So that's why I tested it across extremely difficult ecosystems.
As you have said, okay, we have not developed as such irrigation advisory service model, but we have tried to develop a model based on the relative evapotranspiration to get yield prediction. Another, evapotranspiration is one of the critical variable that can be used for irrigation scheduling along with the soil moisture status. So both soil moisture and evapotranspiration, we are now have developed certain kind of API application with the Google Earth engine. So we are directly getting automatically this evapotranspiration GPP both together to get the water productivity. But anyhow, we are having one project. We are now developing a framework as well as irrigation advisory service model, a decision support system by integrating ARIMA, weather forecast, and high resolution weather forecast, and this high resolution evapotranspiration product into a certain framework to develop irrigation advisory service for particularly Udhamsi Nagar, Uttarakhand.
Thank you.
Just to add to what Dr. Patel has said, that tomorrow we'll have, after Calval session, the downstream applications. I think you will be also part of that. So we want that these Trishna products should feed into the operational service system, because always ISRO or any other space agency cannot do to the service oriented always in the downstream. So we encourage the people or organizations who are providing the service like IMD, then CDAC, then there is MS Maulana Vishnu National Crop Forecast Center. So there are many others. So in their system, and then National Hydrology Program. So in their system, this product should go directly ingested so that their purpose will be served and it is delivered proper way.
Excellent. Any other questions, please? Yeah.
Hello, my name is Sarazan from CNES. I have a question for Atira. What solar radiation data did you use? It is measured, it is a geostationary data?
Solar radiation data.
Yeah.
Everything is from field.
Okay.
On field solar radiation.
Thank you.
Thank you. Yes, yes.
My questions is to Kanish, because he conveyed that this aerodynamic temperature play a very vital role regarding the stomatal conductance. So, and we have seen that aerodynamicity is a function of wind. And we have seen the wind blow in some part of India is very, very fast. And we have recently experienced in Barambadi. Because of that, we have suffered a lot. We have a very less scanning of UAV. So my question is that when this wind is so much important, then when we go for a one-time pass and doing the diurnality to address a daily ET, so what precaution we have to take?
The thing is, if wind is generated as a result of pressure gradient force, so if it's a free convection, so wind is not an independent component in the land atmosphere system, basically. But if wind is the only source of variation in ET, then I don't think I have any answer for you.
But just one point I would like to add. In the Calval activities, you know that LST correction also, like directionality, there will be correction for the turbulence. Okay. So this is part in the Calval, but exactly you cannot everywhere correct. But thing is that where you are measuring actually, suppose if there is no cloudy situation but high wind speed, so if you are taking UAV at maybe centimeter or maybe few meter scale, so their turbulence effect will be definitely more. But from CNES airborne study, they have clearly showed that when you go from 5 meter to 50 meter, so the high frequency error actually is minimized, but there must be certain components of the wind which can reflect.
We can discuss more in the coffee so that gives
But
opportunity.
my question is regarding diurnality. One time taking is stable is fine. But when we're going for diurnality, when we're taking, we have seen in thermal camera, with the John Louis experiment, when we have taken in Navagam, when the stable is there, temperature is fine. But diurnality affect a lot in the morning and afternoon. When we're taking the one snapshot, very calm situation. But in morning and afternoon, wind speed is very high or low. So that will affect the daily ET.
Any more? You had a question, please. From efficient. For whom this is?
Sir, this is for
Anyone?
Rahul sir as well as Kanishka sir.
Okay.
That how the crop coefficient part is taken care to measure evapotranspiration.
Crop coefficient.
So crop coefficient based approach is completely different approach. That's the FAO Penman-Monteith approach, where you use the weather data to get a reference evapotranspiration, and then you multiply it by crop coefficient to get something which is called crop ET. If you do not have a lot of water stress, and if you're working in extremely challenging environment where getting satellite data is very difficult, I would say this is still a workable method. But if there are a lot of water stress, then I think you have to be very careful before using that method.
Just to give you more clarity on that, there will be water stress product also here. So their ET and PET ratio. So in that PET also, one is the reference evapotranspiration with respect to some grass reference, but that can be potential ET also with some particular crop. So there, this crop coefficient part will be actually applicable. Okay, and that can come from the LAI and the NDVI, which will come from VSWIR data.
Thank you. And I think we should close the session. We are running late for the next session. So
Yeah.
any other questions can be discussed on the coffee. And thank you for all the presenters for this session. And thank you all for this interaction.
Yeah.
It was
So,
a pleasure for me to interact and be chair with Albert. You have anything, any observations?
I'm going to talk later, so I didn't want to talk now.
yeah.
So the session is
And
closed.
yeah,
for the-
so as a token of gratitude, we would like to present our session chairs with a memento. I would like to invite Dr. Charles Miller on the stage. I request Dr. Charles Miller to present the memento to Dr. Albert. I again request Dr. Charles Miller to present the memento to M. Shekhar. So we thank the session chairs, Dr. Albert and Dr. Shekhar, for conducting this session beautifully. I also thank the reporter Kailash Dakore for noting down the important minutes of the meeting. I also thank the speakers and the audience for making this session successful. So, yeah, so there is an important announcement first related to the poster session. The poster session is now open. I request all the participants of the poster session to put up their posters at their respective given poster numbers in the poster gallery at the back of the auditorium. The dedicated session for poster interaction is 3 to 4 p.m. in the evening. Audiences are free to interact with participants during break time as well. So now we conclude the session. We break for tea or coffee. We will resume the next session again in 15 minutes. 15 minutes. 11:30. May I have your attention, please? Yeah, we are now going to start the second session of the day 2. And I invite the session chairs, Dr. Gilles and Dr. Kanish on the dais. I also invite the rapporteur Athira KV on the dais. I request the rapporteur Athira KV to be present on dais. Okay, so now I hand over the session to the session chairs.
Yes. So we'll start this second session about ecosystem stress. So there is one constellation, and we'll start this session with Albert Olioso from URFM in RAE on evapotranspiration and water stress. How will they be assessed using Trishna data? So I invite Albert to come.
Change the slides. This is for the pointer. Okay.
So now you know why I was not talking before, because I'm going to talk now. Yes, so I'm going to introduce you the daily evapotranspiration product we want to have with Trishna. I think in the program, it is written that I'm going to talk about Evaspa. Evaspa is one of the models that's going to be used to provide this evapotranspiration product, but it's not the only one. So I'm going to show this just now. There is a lot of people who, I don't know if this, okay, we don't see it. There are a lot of people are involved in this work. It's not that everyone was touching the models or so on, but there is a lot of talking and thinking about how to do everything. So all these people were involved, and there are some other I forgot, of course. Yeah, okay. Just look at the right of the screen where you have some of the products that will be delivered by Trishna. And the one I highlight are the one we are requesting for working to derive evapotranspiration. So first we have the surface reflectances, and of course the LST, the land surface temperature. And with this variable, it's possible to derive some of the parameters which are required for computing evapotranspiration, like the vegetation, what we call here the vegetation variables are like, for example, the leaf area index or the fraction cover, and also the albedo, which is a very important parameter in the evapotranspiration calculation. And of course, at the end, we compute the evapotranspiration and some indices related that are supposed to indicate water stress. What is important in what we want to do is not to have evapotranspiration just at the time the satellite is coming, but to have continuous monitoring of evapotranspiration, because in any application or most of the application, not saying all of them, but most of them, we need to have the cumulative value of evapotranspiration. This is a scheme with how this data are arranged in order to obtain evapotranspiration. So the pointing system, you see something? I don't. Okay. So at the near the bottom, you have, or at the bottom, you have the time series of evapotranspiration we want to have at the end. And just above, you have the two different models that are used to derive this evapotranspiration. So there is on the right the contextual model, which was shown by several person this morning. And also in the middle or on the left, a simple pixel model. So these two type of model works very differently. And we think we need to have different models in order to assess evapotranspiration in a better way. Sorry. And of course, all the variables we required, which are at the top, are coming from Trishna data and used to compute albedo and vegetation variables and surface temperature, of course. And also something which is quite different from any other system is that we compute also from Trishna the solar flux and the long wave flux that are going to feed the net radiation calculation. So first, I'm going to talk about the level 2B, where we are going to derive evapotranspiration maps on days when we have Trishna acquisition. And of course, this will depend on the satellite revisit. So if the satellite is not coming, there is no map. And also on the cloud cover, since the measurements in the thermal infrared are not going through the cloud. We said before that we want to have the product delivered 12 hours after acquisition. It may be difficult, but Wim van Siassen yesterday said we have to get the product before breakfast. So now I think we should move to, instead of 12 hours later, before breakfast looks good to me. We are going to use two models. So the first one is called Evaspa, is a contextual model. So it helps to it is used to compute the latent heat flux. The second model is a stick model that was already presented a little bit by Kanishka this morning. So which is a single pixel model, which means that it can work for one pixel and another one, while the Evaspa model requires all the pixels together in order to work. This is providing only the latent heat flux, and we need to integrate this latent heat flux to the daily scale. And in this, at the moment, we are going in a very simple way, which is usually working well, is that we use the incident solar radiation and the ratio between the incident solar radiation at the time of the satellite acquisition, which is provided by Trishna, and the daily value of solar radiation in order to scale the evapotranspiration to the daily scale. In the product, we want to also deliver an evaluation of the uncertainty. And at the end, we also want to deliver water stress indexes, which are not the evapotranspiration, but that are an indication of the impact of water level on the flux or on the ecosystem processes. So that can be the evaporative fraction, which is one of the parameter or variable which is computed by Evaspa, for example, or that can be also something which is related to the ratio between the evapotranspiration and the potential evapotranspiration. Few words about the Evaspa model. So I said several times already that it is a contextual model. It's working from the surface temperature, but also you need something related to the status of the surface in terms of vegetation density. So that can be the fraction cover, that can be a vegetation indices. And we also use, in parallel, model related to the albedo instead of the vegetation indices, like the SCB model that was also presented this morning. For this type of model, we compute the latent heat flux from the evaporative fraction and the available energy, which is the net radiation minus the J flux. And to get the evaporative fraction, we have a proxy which is related to the position of one pixel. So if you look at the graph, you have TS, so it is the temperature for one pixel, and we look to the position of this temperature compared to the maximum value of temperature and the minimum value of temperature. And the main one of the main process in deriving evapotranspiration with this type of model is to find the limit, the upper limit, which is considered to be, we call that the warm edge, where the evaporative fraction and the evaporation are going to be set at minimum value. We often use 0. And at the bottom, we have the cold edge, where we set the evapotranspiration is at the maximum it can have. There are strong hypotheses to run this model. This hypothesis is that the variation in surface temperature within the image is just related to the water status and the quantity of vegetation. Any other reason that makes the temperature changing is invalidating this hypothesis. Like, for example, if there is a change in radiation, if there is a change in air temperature, it's putting a problem in the calculation. Also, we need to run this type of model. We need that in the image, we have a dry area that make possible to derive the warm edge and wet area that are used to derive the cold edge. So with this model, we scale the daily evapotranspiration. We scale the latent heat flux to daily evapotranspiration, as I was saying, using the ratio between solar radiation at the time of the satellite measurement and the integrated value of solar radiation during the day. And also with Evaspa, something which is not done in most of the model usually, or maybe never done before, is that this is a multi-data, multi-model framework, which means that for some of the equations of the model, we have several versions. Like, for example, looking at the dry edge and the warm and the wet edge, we have several ways to derive them, which means that we have several values of evaporative fraction for each pixel. We may also have several values of solar radiation inputted in the calculation. And this generates several values of evapotranspiration. And that helps to obtain with an ensemble calculation. So an average, which is going to be the estimated evapotranspiration, but also a standard deviation of the estimation that can be used as an indication of the uncertainty in the calculation. This is the scheme where Emmanuel put all the different products that are going to be entering the calculation. So you have on the left the list of all the different products. So all these products are coming from Trishna calculation. And after that, so the model is running in order to have the latent heat flux, so LE at the end. And using the daily solar radiation, we obtain the daily evapotranspiration. And after that, we also have the stress indices, like that can be the evaporative fraction, and also SI, which is the ratio of daily evapotranspiration to potential evapotranspiration. What is important, so I won't talk anymore about the stress indexes. So what is important is that, okay, we have a lot of Trishna products that are entering the calculation, but still we need some information from outside. And in particular, the daily solar radiation is something that it is not possible to obtain directly from Trishna calculation, from Trishna information. So we think to use just geostationary satellite data that provide the solar radiation with a good resolution, spatial resolution. There may be also some kind of theoretical calculation that can be used. And at the end, the Evaspa product will be an instantaneous evaporative fraction, a daily value of evapotranspiration, and quality flag, and also the water stress indices. The second model we are going to use is a stick model that was presented this morning. So it's working in a way completely different from Evaspa. In this model, you have all the resistances or conductances framework that are used, that are a lot closer to the theory to compute the fluxes. In Evaspa, we put all these equations away. We don't need them. So the model used the Penman-Montis equation. It was modified in order to be able to integrate the surface temperature. And you have a scheme with a model, but I'm not going to detail. And at the bottom, you have a comparison to ground data that was done from EcoStress data that showing that the model is working well. So there are other validations showing it's working well. And if we look at the same scheme, that's the one for Evaspa. So it's almost similar. The model is not working the same way. So the box in the middle is different. But there is something which is very different, and that has a great influence on the calculation, is what's happened for the meteorological information. So the model requires the daily solar radiation, but it is also required at the time of the satellite, the air temperature and the relative humidity. And this is a big problem. This is because these values are complex to obtain at the pixel level. So why we are using these two models? So there is first reason, of course, was because I was working with Evaspa and developing Evaspa with other people, and Kanishka is working with STIC and developing STIC. So that is the main first reason we are using this model. But actually, it's why we are working with this model, the real question. And this is the main point of these two types of models, is that these two types of models, they reduce the number of inputs that are required in order to compute evapotranspiration if you compare to, for example, the TSEB model developed in the United States. With these two models, we don't need information, for example, on the wind speed. And the wind speed is something you cannot obtain easily, but it's not even easily. It's almost you cannot obtain the wind speed at the pixel scale. When you have the calculation of aerodynamic equation, you need to have the roughness parameters, all the aerodynamic parameters at the ground, and this is something we cannot have with remote sensing data. So the two models, STIC and Evaspa, they don't use these two variables in order not to input uncertainty or error coming from these two values. So that was the main reason to use this type of model in order to derive an operational product. And if you look at here, it is uncertainty calculation for different models. So at the bottom, you have the evaporative fraction model, like the contextual model, like Evaspa. So it is one example. And you see that main uncertainty, so at the scale is representing the standard deviation of evapotranspiration. And you see that, for example, the evaporative fraction is the main source of uncertainty in the evaporative fraction model. And this uncertainty is coming to the way to obtain the line, the wet line and the dry line in the contextual model. But if you look at the top with an aerodynamic model, so it's not the case of STIC, but it's the case, for example, of TSEB, you see that the wind speed and the uncertainty on the wind speed has a very large impact on the uncertainty in the calculation of evapotranspiration. So to summarize this, at the bottom with Evaspa, all inputs are coming from remote sensing data. Just the integrated solar radiation is coming from outside. But we have a very strong homogeneity hypothesis that in many situations can be invalid. With STIC, we don't require the aerodynamic parameter, but we require to have information on air temperature and relative humidity at the pixel scale. And this is working on the spatial distribution of this variable in order they are accurate enough to run the model is a big challenge. I was talking about the question of the lines, the dry line and the wet line. Here you have the two examples on the left. A situation where you don't have, for example, the most of the left is we don't have the wet line. At the right, we don't have the dry line. And this impacts the calculation of evaporative fraction and then the calculation of ET. This is an example of results using the Evaspa model in Sahélian area in Senegal, where you can see with the model in direct use, you have the yellow estimation. So if you look at the period where the evapotranspiration is very low, you see that the estimation is quite high. And this is related to the fact that, we have problem to find the wet line. And the Nesrine Farhani is working in Montpellier in France. So I'm supposed to finish, right? Okay. So she developed method in order to improve the calculation by changing the way of obtaining the line or dropping some of the line calculation. Okay, I wanted just to say one word about level 3, where we need to have a continuous estimation of evapotranspiration. At the moment, we have implemented some gap filling methods which are very simple, which are related to the interpolation of the ET to solar radiation ratio. But under development, we are working on the inclusion in this type of interpolation method of the rainfall and the irrigation events. And just to show here, so at the end, we should have value of evapotranspiration every day. In the top graph, you can see a comparison between Landsat and Trishna on one example and on the synthetic data. The red line is the real value, let's say, and all the black lines are different reconstructions that were done using the ratio to solar radiation. And depending on the day we start the reconstruction, and you see that as Landsat is coming, so it's one Landsat every 16 days, it's not catching a lot of the real evapotranspiration data, and the interpolation between the value, the available value, is generating very different evolution of calculated evapotranspiration. Of course, with Trishna, this is better because the resolution is, the time revisit is increasing. And at the bottom, you have a graph on 2 years showing the difference in uncertainty in the ET retrieval related to the interpolation problem and the gap filling. And you see that coming from Landsat to Trishna is decreasing a lot this uncertainty. And I think I'm over for now.
Thanks, Albert. So we'll take the questions at the end, like the other sessions. Albert has been presenting the rationale behind the choices for the level 2 and level 3. So now we are going to dive into the processing chains, and this will be presented by Emmanuel Sarrazin from the CNES.
Okay. Hello, everyone. So I'm going to give you an overview of the current state of development of the Trishna L2B and L3 processing chain for the French ground segment. Yesterday, some of the L2B products were presented, and I will mainly focus my talk on ET product. Okay, so evapotranspiration play a key role for water cycle. It represents the largest water loss component of continental surfaces. Nearly 2/3 of precipitation are returned back to the atmosphere by ET. So the temporal and spatial distribution of ET is relevant information for monitoring crops, for instance. Trishna will produce several ET products, but also we deliver a continuous time series providing every day the best possible estimates for field scale daily ET. The L2B products are single date. They are associated to single satellite acquisition. They represent geo and biophysical variable at surface level extracted from L2A product. So the input data to produce L2B products are the L2A product, but also meteorological data such as air temperature, dew point temperature, gas content, and aerosol content, but also static auxiliary data like digital elevation model and land use and land cover maps. So here is a diagram that I've presented earlier by Albert. It is a workflow of L2B processing chain. Albedo, downward, short-wave, long-wave radiation, and vegetation and this algorithm were presented yesterday. You can notice, as Albert said, that there are two ET products, one from a single pixel model called STIC and one from a contextual method called Evaspa. As the both models were introduced earlier this morning by Kanishka and Albert, as Albert said previously, there is no perfect model for computing ET. Each model has its advantages and its drawbacks. So depending of the landscape and the usage of the ET product, one model might be more interesting than the other. So L2B Trishna product will contain albedo, instant downward shortwave and longwave radiation, vegetation and heat, but also instant evaporative fraction from single pixel, daily single pixel evapotranspiration, instant contextual evaporative fraction, daily contextual evapotranspiration, and also water stress indices. So it was decided in the ground segment that from L1C processing step, Trishna data will be tiled, processed, and distributed according to the AMGS tiling system. This is the same tiling system that the one used for Sentinel-2 product. This is not a problem for the majority of the algorithm of the L2B processing step because most of them are single pixel. Each pixel can be processed independently, but it is not the case for Evaspa algorithm. As Albert said earlier, it is a contextual method. In Evaspa, all the pixels must be processed simultaneously to compute the dry and the wet age. And as Albert said also, Evaspa had the advantage to not require any meteorological data to compute evaporative fraction, but it assumes homogeneous condition for all the pixels in the process area. So all the pixels must present no variation in climate variable, no variation in aerodynamic parameter, and no variation related to topography. And so you can imagine that is, for any time in the world, this is not always the case. For instance, in mountainous area, there is no guarantee that all the pixel the pixel elevation can vary greatly within the tile. So in order to process Evaspa in an operational way, we need to even identify for each tile the valid zone to compute Evaspa. That is to say, we have to identify in advance the pixel that we consider in homogeneous condition. So we have developed a methodology based on digital elevation model and water mask to define this valid zone. So we discard water pixel. We also discard pixel with a larger slope. And then considering a range of altitude with a fixed size and the distribution of pixel elevation, we identify in the tile the range of altitude that contain the largest number of pixels. And then we apply some regular algorithm, some cleaning algorithm to regularize the area. So is an example of the tile around the city of Nice in France. So as you can see on your left, there is a lot of water pixel, but also a lot of mountainous area. So if we use our algorithm, we can identify the valid pixel where you can apply Evaspa correctly. But there is another problem. To detect wet and dry edges, you need a sufficient number of pixels. So in a tile, in a Trishna tile, there are about more than 3 million pixels, which is largely enough to apply Evaspa. But for tile in coastal area or in mountainous area, this is not the case. So we have to process tile together, and to do it operationally, we have to define the tile association for the processing. So that's what we are trying to do. We have defined an automatic association of tile so that we can process tile together and have enough tile in the group of tile to apply correctly Evaspa. The methodology is based on several steps. First, we compute the number of valid pixels per each tile. Then we identify those tiles which are a number of valid pixels below a threshold. Then we associated those tiles according to the following rules. One tile must belong to only one group, and one tile must be associated to a group that contain its adjacent tile, and also to a group that contains the largest number of valid pixels. So here it is an example of our tiles in Italy. So there is also, so for the association, there is also such criteria like connectivity, also like belonging to the same land area, to the same orbit, and also to the same UTM zone. So over Italy, we have computed the number of valid pixels for each tile, and you can see that there is tile where there is largely enough pixels to compute Evaspa, but for coastal area, the number of valid pixels is very low, so we have to regroup the time. So with this methodology, as you can say, we can regroup a valid pixel, like in Corsica or maybe in Sicily, to increase the number of valid pixels per group. So all the tiles in a group must be processed together in the ground segment. So it has to be some paying attention about synchronicity and to wait that all tile is a process before applying Evaspa method. In order to validate the algorithm and tune algorithm parameter, we have decided to do a data benchmark. We have identified several study cases, south of France, Sahel, North Africa, India, and space, as well as ground truth data. The objective of this benchmark is to produce data as close as possible as the future Trishna product. We will use Landsat, Sentinel-2, and EcoStress, as well as Constellar tier data. And we will try to process this data as close as possible as it will be processed in the ground segment. Let's talk about L3 product. Albert say a few words of L3. And so L3 product is a continued time series of daily evapotranspiration. It is available every day, even without Trishna acquisition. So for day with a Trishna acquisition, it is created from L2B daily ET product. But for day without Trishna acquisition, we will use external solar radiation data as well as meteorological data, and we apply interpolation, extrapolation based on Gad-Philippe methodology to estimate ET, to estimate ET. So L3 product is produced for both L2B ET products. So we will have a daily contextual ET and a daily single pixel ET, as well as flag and uncertainty associated to all distributed variables. So what would look like L3 product? So each day we need to have an ET estimation. So we have defined a sliding window of several days where each L3 product might be updated to a newer version according to new satellite acquisition arrival. And the project, the version of the product will be archived once the project date is no longer within the sliding window. So here the diagram, you can see each box represents a date. So there is L3 project that correspond to Trishna acquisition. And you can see between two acquisition date interpolated project and extrapolation happen where after an acquisition date where there is no already another acquisition date available. So for a day without a Trishna acquisition, the new L3 product will be extrapolated. So for first time, just using solar radiation data, but maybe after a rainfall or water budget model. But for Trishna acquisition, the new L3 product will correspond to L2B product, and then we will have to update the previous L3 product, the L3 product via interpolation. So each day, some product may be updated in the sliding window. So to conclude, we have defined a first version of algorithm for L2B and L3 protection, as well as the sequencing of this algorithm. There are still work to do. We are currently developing the processing chain and preparing the data benchmark for algorithm performance validation. Once we will have the first version of the algorithm as well as a data set for the benchmark, we will be able to improve the algorithm from L2B, and for L3, try new interpolation technique based on rainfall, API index, as such as water budget model. Thank you for your attention.
Emmanuel. Now there is some cancellation, so we can directly go to the third presentation, which is again presented by Albert, because Samuel, actually Samuel is in Arbenaban, but he couldn't come. And he will be presenting some outputs of Evaspa for concrete examples.
So now you understand why I didn't want to talk before. I have to save my words, I don't know. Now I'm going to present the work done by Samuel Emwangi. So he was not able to be there. He's in a hotel somewhere because he was not going to enter ISRO. This is the work on benchmarking of Evaspa, and it is done in collaboration with several labs in France. Wait, so I don't remember how it works. This way. So he was providing me the slides, and in terms of environment of its work, he started the talk on we have already different evapotranspiration products that exist coming from different laboratories using different type of methodology and different models. So there is a list in the middle here. And but the thing that none of these products is providing information on the daily scale and at a high resolution at the same time. Even if some, like Vapor, for example, which is provided by FAO, has a capacity of doing it. But the Vapor can provide information at a decametric scale. but it's the only one. So when developing the Trishna program, the goal was to have this daily evapotranspiration at high resolution. And everything that was done was to go in this direction, and that can fill the gap between the product we already have and what we require for, in particular, for agricultural application. So still we have the contextual model, as here we are using Evaspa. So the two type of model using, so the fraction cover on the left, so the diagram between fraction cover and surface temperature, and also the SCB model using albedo. And what is important here after that is all the different type of input on the left. And this talk is going to talk is going to be a lot on the uncertainty assessment of evapotranspiration. So on the left, you have as input, you have the radiation data. You have the surface temperature, you have albedo, you have NDVI. And what is important in this work is that radiation data, we took the radiation data from several sources of data. So there is ERA5, the ERA5 and ERA5 land. MERA reanalysis also. ERA5 is a European reanalysis. And MSG is a solar radiation obtained from Meteosat or geostationary satellite. For LST, we are using here the MODIS data, and there is several MODIS products for LST. So there is two satellites, Aqua and Terra. So it's already two surface temperature sources, but also there is two algorithms to obtain surface temperature with MODIS data. This is MODIS 11, which is based on the split window, and MODIS 21 based on the test algorithm. So that means that we have four different temperature for MODIS data, and plus we add also data from BIRS and the NPP platform. I was saying in the talk before that we have different ways to derive the dry and wet line. So it's on the graph, you can see several different lines. So these different lines or different algorithms to get the line provide different evaporative fraction estimation. And there is also a point that was not presented because I switched the slide, but famous Gilles Boulet is going to provide information on that later, is the calculation of the grounded flux, which is based on by parameterizing the ratio between net radiation and grounded flux using vegetation indices, for example. And we have different models to do that, or actually different set of parameters to do this calculation. So at the end, we have a lot of different estimation of evapotranspiration by combining all the variation between these variables, these input variables, or way to compute some of the internal variables of the model. So in this case, we have 4 LST, 3 radiation, 9 evaporative fraction, and 9 grounded flux for each pixel, which means I don't know how much is written later, a certain number of evapotranspiration estimation. Here, the benchmarking is going to be done on several flux stations in the south of France. We have flux stations at different time. Some of them still working, some of them were in the past. On the triangle are forest ecosystem. The round part are different type of natural land. And there is also some stars where we have crops. And all these data were acquired using a covariance system. The other inputs are like NDVI coming from MODIS data, albedo computed from MODIS product also. And I was saying, yeah, okay, the reanalysis and the satellite, geostationary satellite data for the radiation data. Here you have a comparison So it's not an assessment of the accuracy of the calculation, but it's a comparison between the different estimations. So it's a root mean square difference of the calculation done using one LST product at a time, not the 4 LST products together, in comparison to the Aqua 11 product. And you see that if we are using the other algorithm, so the Aqua 21, so using the test method, we have almost the same accuracy or the same, the results between the different estimation are close. But if we are using VIRS data, we have a large discrepancy between the different estimations. And I don't know, at the moment, we don't know why. Here we have the uncertainty assessment of this calculation. So at the top, you have the difference in uncertainty or the influence of the type of calculation of surface temperature on the uncertainty in calculation of evapotranspiration, either depending the algorithm, so 11 versus 21, or depending on the platform. And what you can see is that two algorithms are providing results in quite a short range, but when you change the platform, the uncertainty is increasing. But this uncertainty on evapotranspiration in terms of standard deviation here is not very large. So at the most is 0.5 millimeter per day. At the bottom, you have the breakdown of uncertainty between the different sources of uncertainties that are introduced in the calculation. So you have in blue the surface temperature. You have in red the solar radiation. In green, what is this? Orange, the evaporative fraction, and purple, the J flux. And you see that in this case, so it's sorted by season, but you have on the left all the sites together, and after that a plot for each site. So you see that surface temperature has still quite a large impact on the calculation because the uncertainty is like 1/3 of the final uncertainty. And also the calculation of evaporative fraction has a large uncertainty on the calculation. Here there is an evaluation of the data, the retrieved data, and the uncertainty on one site. It is a forest close to Montpellier in south of France. It is a on oak forest. The surface is quite flat, and on the right you have the uncertainty related to the different product, the different radiation product, and you can see that the solar radiation at the top so has an uncertainty which is changing from day to day because the different products sometimes they converge. So it's at the top is the instantaneous radiation. In the middle is the total solar radiation during the day, and at the bottom, no, it's not that. Sorry, I'm sorry, I'm lost. So at the top is a long wave radiation. I was wondering why this uncertainty is so different, but okay. So you see that the uncertainty for the different type of radiation we are using inside of the model are not the same. And when you transfer that in the calculation, so you have on the top the calculation of evapotranspiration, the values that are computed when we have MODIS data. In gray, you have the range of the estimation. And you can see that the ensemble average, so which is derived from all the calculation together, where we compute the final evapotranspiration as the mean of all the estimation of evapotranspiration. So the ensemble average ET, which is supposed to be the final product, is following almost the measurement. At the bottom, you have the same thing, but after interpolation and gap filling when we don't have the data. And so when you look at the root mean square error for this estimation, we have something which is less between 0.5 millimeter per day and 1 millimeter. And it's improving when we do gap filling, because very often gap filling is done when we have cloud and the evapotranspiration level decrease. That decrease the error. And also the last line is the best model. So among all the models we have, so it's 972 results here. The best estimate when we take one model is 0.6 millimeter per day. Here there is some evaluation or some to spot some of the problem we have, like at fall, there is a lot of rain coming, and the evaluation of evapotranspiration, the evapotranspiration will compute, we often have a gap. And it may be related to the problem, of the line, I mean, the definition of the dry line, which is not available at that time. Okay, I can. Here you have the evolution of uncertainty. So in green, for all of them, is the evolution, is a full uncertainty on evapotranspiration estimation. And from the top to the bottom, you have first the uncertainty in red, the part of uncertainty in evapotranspiration determination, which is related to the uncertainty in surface temperature, because we have 4 different products. Below you have the impact of radiation. And after that, the evaporative fraction impact. And after that, the grounded flux impact. So it's the same type of results than when they were integrated before, but you can see that for this example, the highest uncertainty is coming from the land surface temperature product. And after that, the radiation has a large impact, in particular at some period of the day, of the year when we have a lot of cloud. And the evaporative fraction method and the grounded flux have a lower impact. This type of uncertainty analysis is not something like is going to be always like that. In what I was presented in the previous talk, the range or the sorting of the different uncertainty was not the same. For example, the land surface temperature didn't have such a large impact like here. So I think I'm at the end. So the Evaspa is used here to provide evapotranspiration maps over southern France. We have a large spread in the different estimations because of the different sources of uncertainty, and that land surface temperature is providing the largest uncertainty in this calculation. The lowest uncertainty is coming from the grounded flux method. And maybe we need some additional information in order to improve, it's not maybe sure, but to improve the possibility of to apply the contextual model when we don't have the line, when we are not able to really compute the dry line or the wet line. Okay, we can. Thank you.
Thanks, Albert. So we'll come back to uncertainty with the contextual methods in Nesrin's speech at the end of that session. But in the meanwhile, we are going to go to another presentation, which is actually taking advantage of different kind of input data for a specific crop which is coming, and adding, I suppose, what is fluorescence adding to the estimation of evapotranspiration water use efficiencies. So this will be presented by Karun Choudhary. I hope I'm spelling it right. Thanks.
Okay. Thank you. Good morning, everyone. Since morning, we have seen many presentation on ET, and my presentation is also on ET, and I will try to keep it very short so that you all can get more eating time. So actually, this is a small study which we have carried out in a form of cumin farm, which is in the semi-arid ecosystem at Kazri. Kazri is research station of ICR, Indian Council of Agriculture Research, where we have the adicovidian system. And since past 3 years, we are monitoring these fluxes, different fluxes at interval of half an hourly. And we are doing the energy budgeting as well as carbon budgeting. So we have a good chance. Here we have established the flux box, the first flux box in India, which is measuring the shift signal at every minute interval. So it's a high resolution shift signals. So already different presenters have said the context for my work, that is the applicability of the water use efficiency. Dr. Bhattacharya sir in yesterday's presentation and today Patel sir, they have said the importance of the high resolution water use efficiency can lead to many important parameters for the crop growth as well as to manage the crop. And if we see the literature, this water use efficiency estimation is really lacking, particularly for the crop of low biomass. Most of the this cumin, which is a spice crop in India, so it's a low biomass crop. So fortunately, we have this flux box here, and this SIF, as we know, is a good proxy of the primary productivity, and recently gaining much popularity. Earlier traditional approach of light use efficiency based model, where we are estimating the GPP using FFR, literature says the CIP is much more closely related with the GPP. So to investigate all these things, we have taken the objective to estimate the ET using the energy balance models, and to estimate the GPP using the simulated SIP, as well as to use this flux box to derive a relationship between the SIP and GPP. So there is the two instrumentation which I spoke, is the adicovidian towers and the flux box. The flux box is equipped with the spectroradiometer, which gives the radiance observation with a spectral resolution of 0.3 nanometer. And like that, two spectroradiometers are there. And we have very recently installed in the month of February. So this cumin crop, basically it grows in a winter season, spanning from the November, mid-November or the early December to the mid of the March. So we have tried to take all LST products from the Landsat 8 as well as 9, as well as the eco-stress data. We got sufficient eco-stress data, but the applicable eco-stress data were very limited to 5 only because of the irregular different passing time. So we have avoided the passing time of the very early morning as well as very late in the evening. Corresponding Sentinel-2 datasets we have used for simulating the scope reflectance spectra, as well as INSAT 3D for insolation we have used. So we basically, it has two parts, ET estimation and GPP estimation. ET estimation, we have selected the simplest and most widely used model, SEBBL. The parameterization has been done using the optical data sets. Wherever the eco stress is there, we have taken the nearest Sentinel-2 data sets to estimate the albedo and other variables. Some aerodynamic parameters we have collected from the flux towers and we have incorporated into the models. For scope parameterization, we have done the scope parameterization for the particular crop using the existing data sets available with us, as well as from the literature. Through scope, we are using the LUT lookup table methods, and we have generated the SIF, simulated the SIF for all these passing dates. And this SIF in turns related with the GPP. So these are the parameters we have used for parameterizing the SIF. some of the variables which are the varying during the crop growing season. We have given the range. Other variables like leaf parameters and leaf biochemical parameter, we have fixed the value from the literature. Literature are really lacking for the cumin crop, so we have taken for the low biomass crop the similar values. And this scope were done the forward modeling, and we simulated the spectra as well as the different fluxes from the scope. So from the flux box, we have retrieved the SIF using the IFLD method, which is the improved Fraunhofer Lime depth method given by Alonso. It has a better accuracy than the 3FLD or simple FLD method. And SIF were estimated at 2 wavelengths, that is the far red as well as red SIF. And Sebel, when we have run the Sebel, we got a good time series of the ET product, and the variation, it could be able to capture the variations in the ET of the crop during the crop growing season. ET from the cumin crop, we can see it goes up to around 2.5 to 3 at the max. And in fact, we can see the variation within the plot. Plot of 3 hectare of area. This variation mostly because of the difference in the canopy growths in different areas. So if we compare this Sebel ET with the flux tower ET, we have seen it matches well with the measured ET flux tower, especially in the later part of the crop growing period. In the early part, there were a few deviations, mostly maybe because of the major component from the evaporation, or the canopy is too short to get this energy balance closure possible. So we got a good coefficient of determination or relationship at the later period of the cumin crop. When we have simulated the spectra using scope, we have achieved a good simulated spectra, Sentinel-2 spectra, which is a resampled from the hyperspectral spectra. So here again, we have seen the spectra matches well when the LAI has reached beyond 1.5 or 2, it matches very well. We can see the differences of 10% to 15%, but differences were more than 20% in the NIR region when the crop is in the early growing stage. Then fluorescence, we try to estimate this, simulate the fluorescence. It gives the fluorescence A, fluorescence B, as well as integrated, hemispherically integrated fluorescence from the scope. So we have seen the hemispherically integrated, that is the total SIF, and the SIF which is estimated from the flux box, it has a good agreement. I'll say the trend remained the same. I will not say very good agreement, but the trend matches. This is the dotted one is the simulated one, and the black one is the observed one. So we have only flux box for the peak growing season to the end of the season, because we have established in the month of February, first week of February. So in during those period, it has a reducing trend, and the simulated one also shows the same. Further, we have seen the relationship between the hourly eddy covariance GPP and the SIF. And here we got a good correlation with the SIF, a linear correlation. Whether it's a linear or curvilinear is again a research questions. So we have got a good correlation with both the SIF A as well as SIF B. So, but we could get a better relationship or better correlation with the SIF B, which is a red SIF. Again, the SIF at the current fluxes has a quite good agreement, and SIF has a good agreement with the water fluxes also, which we can take it as a further research. So finally, we have computed the primary productivity from the empirically derived GPP through the simulated SIP, and a time series of gross primary productivity were generated and compared with the gross GPP derived from the flux tower. So from the simulated one, we are seeing that it has undermined at the peak growing stage, and there are variations. These variations, the reason for it that need to be explored, that I am taking at a future activity. If you see the water efficiency correlation with each other, it has agreement, but the few areas, the early part of the season as well as the end harvesting period, it deviates from the observed one. So this was the study to demonstrate the use of multi-temporal high resolution thermal data for assessing the ET as well as water efficiency of a crop. And we can also explore different model. In fact, I tried for using the simple surface energy balance approach also, but being the dry area, it was overestimating than the SEBL. So I have not put as a part of this study. We have to look into the, now thanks to the this workshop where I have explored different other methods also like ISPARS and Evaspa. And in fact, chair person Jill and Ishwar, they have demonstrated and given a hands-on training. So after going from there, here, I will explore those models and compare with these several results. So in the SIF, we need to upscale to larger area. It's this result is only for one field. So in the later part, I will take it for a larger area. So how this SIF can be used for upscaling these GPP parameters. So we need to explore this machine learning based inversions. Because these SIP as well as GPP, we cannot invert using scope model alone. We have to use the machine learning models to invert these parameters. Thank you very much.
Thanks a lot. So I don't know if we are now ready for the remote presentation. So maybe
Hello.
one question. No, it's okay. Yeah. Take some questions. Yes. Yes.
Hello. Can you hear me?
So for Dr. Chowdhury, who's just speaking about water use efficiency, we have a space and time mismatch between what Trishna will deliver, which is every few days, maybe every 3 days with a different look angle at 50 meters versus Flex, which will be 300 meters for SIF coming approximately every month, or you might be able to use Tropomi or Sentinel-5, but that's 7 or 8 kilometers at nadir every day. So how would you propose to generate water use efficiency with the satellite-based products?
Yeah, rightly said, because the SIP product, the currently available SIP products is quite coarse, as well as the upcoming SIP missions Flex, it will be 300 meter. 300 meter is also good enough. But these currently want to use these multispectral data sets where those red edge bands are available. So whether using those bands can be able to simulate or not. Second, where we can use the satellite based is the hyperspectral. So we have the hyperspectral mission plan, and using the hyperspectral data, the simulations or the SIP simulations can be better represented. So we need not to wait for a Flex mission. Maybe we can use the hyperspectral and multispectral data. Thank you.
Yeah, I have just two suggestions to this. Since the water productivity not only is a SIF dependent, maybe you have to go for the primary productivity modeling. So in that, actually, Trishna has a lot of scope. So that we are working in that because the radiation fluxes will be available, and then required the products like LAI, and then sweep channel also will be available. So we had a lot of experiences for doing yield modeling based on the primary productivity, and it is being operationally also used mainly. So, but at this resolution, we can derive primary productivity from Trishna products, and that can also be used as a substitute. But for direct estimation of the SIV, as he has told, that hyperspectral data, yeah, definitely we can explore, and your emit data can, I think, help. I don't know that what will be the lifetime of emit in future, and maybe SBG visual hyperspectral also will be very effective for that.
Okay, thanks. I think we can switch to Nesrin. So Nesrin, can you hear us?
Yes. Hello.
Good. So your presentation will be screened here, and you have to say next.
Okay.
Tu as juste à dire next pour la prochaine diapo à chaque fois.
Okay.
Okay. Is yours. À toi.
Thank you. So I'm Nesrin Farani from Hydrosciences Montpellier. I'm working with the ecosystem stress Trishna mission, Trishna group, and my talk will be about evapotranspiration estimates in SAR regions using an ensemble contextual model, mainly medium and high spatial resolution comparison. So next. SAR region is identified as a hotspot for climate change. Apart from water scarcity, strong seasonal climate contrast that induces interannual variability of water resources, these regions are characterized by overgrowing population and mainly high dependency on agriculture and livestock production. So all these induce water resource management and food security issues. Next, please. We need an accurate estimation of evapotranspiration in spatially distributed manner, and this could be performed by using satellite data. Next, please. So for evapotranspiration estimation, we will use Evaspa tool that it was presented by Albert and several persons before. So just to remind quickly, it's a contextual method. It means that it uses thermal contrast in the same image in order to estimate a relative evapotranspiration estimation. It's an ensemble model. It means that it's a multi-data and multi-model tool, and it provides the advantage that it provides the evapotranspiration estimation with related uncertainties. And as we observe here, it uses mainly surface temperature and vegetation index. Here for this work, we will use albedo as a vegetation index since we use the SAB-based method. So we use these two variables in order to provide evaporative fraction and therefore an evapotranspiration at satellite overpass. So as it was precised by Albert, the advantage to use this tool is that use a reduced number of inputs, and for this main reason it was selected as a primary method to use for Trishna mission. Next, please. To estimate the evaporative fraction for each pixel, we need to estimate its positioning between two limiting boundaries, between hottest pixels and coldest pixels, in order to identify the evaporative fraction as it's presented here in the equation. However, the problem, since it's an ensemble method, it can use different methods to estimate dry or wet edges. As we present here, for example, for the wet edge, we can define different limiting boundaries. And it impacts significantly the evaporative fraction and therefore the evapotranspiration estimation. So the challenge here for an operation used in Trishna is to estimate correctly our limiting boundaries in order to identify correct ET estimation. So for this aim, we have to select appropriate method to use. And also we have to provide sufficient heterogeneity level. And for this, we will use high spatial resolution data in order to reach the maximum of heterogeneity level. Next, please. So at this step, my study area is Senegal Center. It's located in Africa. It's a tropical semi-arid climate characterized by strong seasonal variation, and it's characterized by a monsoon period that starts from mainly from June till October. And in our study area, we have a flux station called which is representative of the Senegal groundnut basin. And our study area is characterized by mainly agropastoral fields. Next, please. So starting by the first challenge, how to estimate correctly the limiting boundaries or edges. So we use this famous illustration. We can observe that we have three main situations, and we cannot provide in each situation sufficiently cold and hot pixels at the same time. Only in transition period, which is the third illustration, where we have sufficiently cold and hot pixels at the same time, and only in this case we can estimate correctly the two limiting boundaries. However, in dry season, for example, we don't have enough of cold pixel, so we have some difficulties to identify the wet edge. So appropriate method that we have to use in this case are methods that use directly the minimum LST value observed in the image, and from this we can estimate correctly the evaporative fraction and to reach the maximum of contrast observed in the image. And the opposite for the wet season, where we don't have sufficiently hot pixels. So for this reason, we have developed an algorithm that provides an automatic identification of the positioning of LST albedo scatter plot. This method is based on the estimation of derivative values in order to assess the variability around these two limiting boundaries. And our aim is to select automatically adapted method to use for each case. Next, please. So here we present some results for this automatic selection. We have used Moody's data available at a kilometric scale. So what we can observe here is that we have produced evapotranspiration from the proposed automatic selection method, presented here in red color, and in yellow, evapotranspiration derived from all methods provided in Evaspa tool. So what we can observe is that we have significantly reduced the uncertainties observed initially when we use all the methods provided in Evaspa tool. And using our selected methods, we are more closer to evapotranspiration provided from measurements, which are presented here in green color. Next, please. It's the same. Okay. And also we have, using this method, we have more realistic evapotranspiration estimation after the method selection. For example, in dry period, we have lower evapotranspiration, and in wet period, we have, after method selection, we have an evapotranspiration mean which is higher, which is expected for wet period. Next, please. So for the second challenge is to provide sufficiently heterogeneous data. We have used the high spatial resolution data from Landsat available at 30 meter. Here we have we want to assess the added value of using high spatial resolution data comparing to the use of MODIS data in the same day, which is a day from dry season. So we can observe here from these two scatter plots that we have more heterogeneity observed in the Landsat data. So we have sufficiently hot and dry pixels that allow us to estimate easily the two limiting boundaries. And as we observe in the empirical distribution, we have more dispersion in the LST and the albedo variable that allow us to provide evaporative fraction estimation. Next, please. And also, when we use high spatial resolution data, we have also benefit on ET estimation. Here we have presented the scatter plot to compare Evaspa estimation from Landsat and MODIS with evapotranspiration from observation. So we can observe in the second graph that using Landsat that we have beta ET estimation when we observe that we have reduced significantly the root mean square in comparison with the use of MODIS data. So we have a better estimation of ET, and also we have succeeded to reduce significantly the uncertainties observed when we use MODIS data. However, the only advantage to use MODIS data is the temporal availability of LST, and this problem will be resolved when with the launch of Trishna mission that will provide for us at the same time the performance of the use of high spatial resolution data and also high temporal frequency. Next, please. And here we present for the same day comparison at spatial scale for ET average provided from MODIS and Landsat, and also standard deviation according to evapotranspiration mean. So what we can observe here that mainly for standard deviation, that we have with MODIS we have more variability using the different methods. Mainly in the coastal region and in some cultural region. However, using Landsat, we have very low standard deviation. It means that using different methods, we are able to provide similar result and similar estimation of evapotranspiration. So from this, we can say that maybe for Landsat, using high spatial resolution data, there is no need to select methods. Since we have a reliable estimation, already we have a reliable estimation of evapotranspiration when we use the different methods. Next, please. And also the main conclusion here is that contextual methods show better performance with high resolution data. Next, please. So finally, to conclude, for the first challenge is to estimate correctly the edge estimation. So for medium, when we use medium resolution data, as here we have used MODIS data, we are obliged to identify appropriate method to use and to apply our automatic selection in order to estimate reliable evapotranspiration estimation. And for the second challenge, to provide sufficient heterogeneity, the use of high spatial resolution data could be very helpful to reach the maximum of contrast and to help contextual method to provide better estimation. And there is no need to apply method selection in this case. For the perspectives, so for Trishna emission, we have to continue to provide uncertainties analysis. And here I have started with first benchmarking sites in the side region, and after that we have to apply this method in other benchmarking flux sites, such Tunisia or south of France. And also we have to generate continuous ET estimation using interpolation method. And other perspectives, apart from Trishna objective, is to continue to analyze the use of high resolution data according to land use, and also to use these estimation using Evaspa tool to assimilate the VAT model. And thank you for your attention.
Thanks, Nesrine. I think we have time for a few questions, no? Before lunch break. So I invite the previous speakers to come here. I think it will be easier to circulate the microphones, and please
don't hesitate to ask questions. And to Nesrine also, even if she's not on stage. Yes, Jean-Philippe. I will run. We have lunch after.
Oh yeah, that's right. Okay, I have two questions. So a small question is about sun-induced fluorescence. So you use the scope model, and so I wanted to know if you use a double photosystem or the combined photosystem when you use a scope model.
Yeah. Hello. Yeah. So you have asked whether we have used combined photosynthetic system or not. Yeah, we have used the combined photosynthetic system, and in that it's estimating this both SIF A as well as SIF B.
Okay, so combined. And so why did you choose to use a combined? This is simple for my own information. Why to use a combined instead of photosystem 1 and photosystem 2?
Okay. The thing is, since we need to correlate with these two parameters, SIF A and SIF B, so because both the photosystem 1 and photosystem 2, basically the SIF B, which is most closely related to photosystem 2, as well as this SIF A is related to both of these. So since I am having these both observations, so I try to select the first and the combined one.
Okay, thank you. So I had another question, so more general, maybe more to Kanishka, I don't know. So in many model, people are using what we call Jacobian, which means derivative of the output signal as a function of input parameters. And so I simply wonder why in this model, I'm not an expert at all of evapotranspiration model, I didn't see people using this kind of approach. So I simply wonder why not, because you are very interested by sensitivity studies, you want to know the error, and Jacobian, as far as I understand, are designed in order to help in this approach. And so I wonder why this approach seems not to be used, as far as I understand.
Okay. So this I will explore the model what you have said in the future work.
Okay. And I was speaking more generally to evapotranspiration model, like the stick model, for instance.
Yeah, sticks will be better. In fact, the scope, one of the output of the scope model is your ET. But it's a combined one because it's a combined the energy balance as well as the transfer balance model. So I kept it the sample separately.
Yeah, I mean, we did some sensitivity analysis here. I didn't show, but we used the rate of change of ET per unit rate of change of the input variables. Yes, we have the results, but I didn't show it here.
Okay, but without using the so-called the derivative, so no need up to now.
Yes, yes.
Okay, thank you.
Thanks.
Thank you very much.
Thank you. I have a general question, probably any one of you, maybe Albert. So we can see that the challenge is that every tile may have various differences in the contextual models which you're going to use. So do we know already which tiles are good, which tiles are not good, for example, in India, for example? So as a step one, we will have already sieved some of them and say what we should do for the other ones which are probably fuzzy. Just for an example, in India, for example, because
For India, I don't know. That shows that at the moment, let's talk about the contextual model. So we need the range of altitude in order not to have variation of temperature depending on the altitude, which are breaking the hypothesis for computing the Evaspa, I mean the triangle. So we cut the number of pixels in order to have just pixels which are working. So if we are going in the north of India, I don't know what happened. I don't know if it's possible to find the possibility to obtain tiles with where it's possible to apply this type of model. I don't know. There are works undergoing in France for trying to adapt the temperature to the altitude, so to correct the surface temperature for the elevation. And we also think that we maybe can use this type of model with different altitude as soon we are able to adjust the temperature, or maybe to do it in 2 steps. First, run the triangle system, and after that, to correct the temperature outside of the area where it is working, and to apply in the same triangle. But at the moment, we don't know. But after that, the question may be also for a model like stick, and everything will rely on the capacity to have a spatialization of the air temperature in a complex topography system. But we don't. For India, I don't know. I know that south of France is a mess. We have mountain everywhere, but they have a lot smaller than the one you have. But it's already a mess.
Shekhar, yeah. So we are taking up some studies for comparison, especially both the models or different Indian tiles also. So maybe some of the things already we have discussed, that what are the issues for both this and also the altitudinal variation. So for India, definitely we'll be doing some validation studies or comparison of these models.
And I want to add that if you take estimation of evapotranspiration in the already available data, or even the different type of models that are available, nobody is doing it. I mean, nobody is accounting of the slopes, which have an impact on the radiation or also on the measurement of temperature. Nobody is accounting of the variation in altitude. So it's, you may, you have data everywhere in the world, but you never know where they are like following something which is close to reality in terms of the impact of altitude or topography in general. So with Trishna, maybe we will have, we are at least we are thinking a lot of this problem in order to either to say we cannot do it, so we don't provide data, evapotranspiration estimation at that place because we cannot do it, or to provide something with a correction that may be better than not doing anything.
To operationally, what does that mean? It means that within the ecosystem stress group, there will be products. We don't want to produce something that people are going to use whatever is available. So we are going to mask a lot of pixels where we know that we are going to have difficulties to have some operational product. But what we can do is, so in ecosystem stress, there is a group on forest. It's a very specific environment, and on topography as well. And I think what would be interesting in Trishna would be to have, beyond the product, to have toolboxes, and that the topography group can actually put on these toolboxes whatever they've been doing to tackle the topography problem, for instance, or the forest problem, for instance, so that people who want to really have some answers on complex topography or forest ecosystem, they can actually download specific methodologies or specific models to provide some ET estimate.
My question to Albert is, you had shown that you are also going to use soil water information when you are unable to define dry and wet edge. So at what scale you are expecting that you will get that this soil water information so solve this issue?
Okay. Because and the people say okay because I say maybe we can do it and I'm sure it's going to work, but actually I'm not sure. But it's possible to make some water balance calculation, not at the pixel scale, but for specific or a combination of situation. And is this water balance simulation say we are not in a situation, we cannot have in this image something which is a dry line. We can try to correct the evaporative fraction according to the fact that we have some kind of minimum evapotranspiration. Like for example, at the moment in south of France, we have a place called La Crau where there is the site for calibration for Trishna. This place is the driest place in France. And in most years, you have evapotranspiration maximum, during summer, evapotranspiration is in between 0 and 0.5 millimeter per day, every day. This year, it was 1 millimeter. So we will need to correct this because this place has a large impact on the calculation of the dry line. This is what I call the information on water, soil moisture or water status.
Okay, one last quick question, please. Anyway, everyone is here for lunch after, so you can ask.
Sorry, just a fast comment. We are here at SAC, and of course, NISAR will be coming online shortly. So I'm sure that was the answer you were looking for.
So Zil, if you permit just one query to
How can I say no?
one query to Emmanuel, that you have mentioned that some constellar satellites data you will be using for benchmarking of the products. So what are the sources of the data and whether it can be available for Indian conditions also?
We have requested some area. I don't know if there is some tile in India. I'd have to check. But we have requested. We have buying some area of the consular data. So we will have the first data, the first satellite as a local time of 10:30. But maybe the second one will be at noon. So If we have data, we could share with you, Bimal, it's okay.
Okay.
But I don't know if we have all data, if we have India, maybe. What of Olivier?
I think there is someone from council.
Yeah. I think
There will be one
Raj
Indian
is
side.
here. So will you give your comment on that? You are from Constellar. So what is the availability of the data and how one can get it?
There will be some Fati acquired as well. Yeah.
So I don't know anything about the contract here, what Emmanuel was referring to. But yeah, we are launching in January, and we have several bigger contracts within India. So there will definitely be data available.
There will be some acquisition on Berambadi.
Okay.
Yeah.
So is there any site or some process for procurement through where we can also approach?
I can give you contacts, of course.
Okay. Thank you.
Yeah. So we can close the session.
Yeah, so as a token of gratitude, we would like to present our session chairs with a memento. So I request Dr. Raj to present a memento to Dr. Gilles. I again request Dr. Raj to present the memento to Dr. Kanishk. Now, as we conclude the session, we thank Dr. Gilles and Dr. Kanish for wonderfully conducting this session. We are also thankful to Athira KV, the rapporteur of the session, for noting the minutes of the meeting. We thank all the speakers and the audience for this wonderful session. There is an important announcement. After lunch, there will be a parallel session on solid earth and cryosphere in Vikram Hall Complex Horseshoe Room. So whoever is interested may join there. In case if you are unfamiliar with the venue, you may assemble here after the lunch and someone will accompany you to the venue. Now we break for lunch. Yeah, so we break for lunch and we resume the session at 2:15. You should try to come here before 2:15 if you are willing to join the session in the Vikram. And there is only 1 hour session after lunch. May I have your attention, please? There's an announcement. Anyone who wants to join the parallel session on solid earth and cryosphere may assemble here. If you are unfamiliar with the venue, our team will escort you to the Vikram Hall.
Nicolas et Nathel.
And good afternoon to you all. Now, there is again, I am making the announcement. Anyone who wants to join the parallel session on solid earth and cryosphere may assemble here. If you are unfamiliar with the venue, our team will escort you to the Vikram Hall. If anybody is interested to go to the parallel session on solid earth and cryosphere. So let's start this session. This is the third session of the day 2. So yeah. This session is on future challenges in modeling terrestrial ecosystem processes. Let us invite the session chairs, Dr. Nicholas and Dr. N.R. Patel on the dais. We also invite Pradesh Jena on the stage, who is the rapporteur of the session. So now I hand over the session to the session chairs.
Good afternoon. We will start the session with the presentation by Gilles Boulet, actual and remaining challenges for level 2 and level 3 daily evapotranspiration products from Trishna. Gilles, please.
Thanks.
From this side, you can change the slides.
Okay. Good. Good afternoon, everybody. So there has been a lot of presentations of the choices for algorithm between level 2 and level 3, and I will emphasize the actual and the remaining challenges we are facing, and zoom in on some particular question to show some results. So, is it working? Where should I part actually? Okay, so you can. Okay, down in fact, okay. So as it has been pointed out many times, we have broadly two kinds of families of models which are used to compute evapotranspiration from thermal infrared data, the single pixel model and the contextual models. And in fact, each of these families has some advantages and drawbacks, and usually they are complementary. So contextual models are relying only on very reduced meteorological forcing, which is mostly the incoming radiations. The single pixel models, on the other hand, they require usually meteorological forcing, and that requires, of course, also some additional data for the surface. So you can actually have models which are computing the evapotranspiration for a surface, or you have some models which are actually able to separate the contribution from the soil and the contribution from the canopy. So as it has been said before, the advantage of the contextual model is that you can actually have only solar radiation and incoming atmospheric radiation as an input. So you can actually have some input that is really compatible with your spatial and temporal scale in terms of robustness, which is not the case for the single pixel model, where you have to downscale at least air temperature and relative humidity at the 100 meters pixel scale from multi-kilometric data, analysis data. And this data also, it has not been mentioned, but another drawback also is that usually this data of air temperature and relative humidity are acquired at half an hour, whereas land surface temperature is almost instantaneous data. So you have also a temporal mismatch. So in order to be able to take the advantage of both kinds of model, we selected Evaspa on one hand and STIC on the other, because STIC is the only one from the single pixel models which is not taking into account the wind speed and does not rely on roughness, for instance. This morning, Atira has been presenting some results on SPERS at various scales. So SPERS is the model I derived on the same kind of assumption as a TSEB. So why not using spares as a third product? It's not because my ego is smaller than the one from Kanishka or Albert. It is just that spares indeed is a complex model and relies on roughness, on wind speed. It doesn't mean that it is completely useless and I'm not working that I'm working for nothing. It means that it should be put in a toolbox so that people who really have some additional data, such as a local meteorological tower or some information of vegetation height mapping on a small area, it's actually useful to use directly the Trishna land surface temperature with this kind of model with your additional data. And then you can really work on a lot of more subjects because, for instance, spares is separating evaporation and transpiration, and you can deal with a lot of issues. And the other advantage also is that Samuel Mwangi has derived a version which is accounting for shadows and directionality of the land surface temperature. ATBD, we are 2 years away from launch. So that means that we have to organize the work a bit operationally. So we are dealing with a lot of scientists. We have like an endless time framework. So we have decided to organize our work and plan the work over the next 2 years according to 3 levels of the algorithms. The first level, called V0, is taken only off-the-shelf algorithms and solutions that are already existing and using little ancillary data and data that is, of course, routinely available worldwide. The V1 is taking into account all the algorithms that require very little additional test or calibration. So we can perform this work in the next 2 years easily by doing some calibration of empirical parameters on available datasets. And the V2 is actually based on more scientific or more complex methods, which involve more research, and there is some kind of risk that it's not going to be completely ready by the launch. So these 3 versions are actually deriving relative algorithms for inputs. Specifically for topography, we have been speaking about topography a lot this morning. Evaspa and stick and also the level 3. So for the inputs, V0, we are just going to do a simple correction of the incoming radiation according to a digital elevation model that's easy to do on a constant lapse rate for air and dew point temperature. For V1 and V2, we are doing something more complex, variable lapse rate, use of analyzed meteorological forcing that is readjust, disaggregation, etc., etc. Shadows. For Evaspa, we have already some approaches that have been used by different groups, so we have to merge them, specifically for the selection of dry and wet edge. And then we will do some flags. That's the next big step, is to do some flags on uncertainty estimation based on statistics. And of course, there is the issue, I will be speaking about it, on the solid flux. V2 will be, as Albert has been saying, will be based on using water budget model to analyze whether you have sufficient heterogeneity in water in your image. For stick, one version is already freely distributed amongst the various groups. The V2 will be using a direct forcing of the land surface temperature and the stomatal resistance that has been published. And there is a development of a 2-source version for V2. For level 3, we will just use a very basic clear sky theoretical incoming radiation for support for interpolation and extrapolation. For V1, we are using the antecedent precipitation index, and that involves some empirical parameters that we have to test over all land uses and climate zones. Improve daily incoming solar radiation using a geostationary satellite. And the V2 is going to be more complex based on water budget models, etc., etc. So what are the current and pending challenges? So first, of course, is to secure input data. So incoming radiation for Evaspa instantaneous and of course daily for the extrapolation to daily time scale for daily evapotranspiration. For stick, there is the additional issue of air temperature and relative humidity. And when you're going to SIMCA-CET water budget model and the level 3, you need also reference evapotranspiration, so wind speed and rainfall. Of course, we have been starting benchmarking. So for the moment, so Evaspa and Stick have different issues. Stick is a pixel-based model, so you can use the current network of flux towers. So that's fairly easy. For Evaspa, it's a bit more complicated because you need supersites with various estimate of evapotranspiration. So we are buying some cheap evapotranspiration measurement devices. And we have already a few supersites in France, Senegal, India, Spain, and Tunisia. So for level 2, we are going to rely on Sentinel-2, Landsat, and EcoStress. And for level 3, to have enough data for the timeline, we are going to use MODIS and VIRS, and we are using, sorry. Then we are going to work on uncertainty to be able to provide some flags and hopefully some corrections, especially for Evaspa. And I will focus here on, in my next slides, on the recent focus on the solid flux at satellite overpass time. Also, there are some activities on calibration validation. So for Evaspa, we have this network of low-cost ET devices. And for Stick, we mostly focus, as I said, on the network of flux towers, so ICOS, Ameriflux, OSFlux, and hopefully Barat Flux soon. So I will, in my next few slides, I will mostly focus on the solid flux. Bimal has been talking this morning about a method which is based on inertia, which needs some concurrent estimation at the beginning of the day or during the night. Usually we don't have that, so we have empirical relationships that relay solid flux as a function of net radiation, and you have empirical relationship of the ratio between solid flux and net radiation. Evaspa is using a lot of this empirical relation, but when you see on the graph, they are all really coalescing in a tight group from around 35 to 0.5. So we say, okay, let's try to figure out if we can also downsize this estimate by using all the flux towers we have in the ICOS, Ameriflux, etc. So we had an internship last year where we have been working on it, and I will be presenting his work. So the flux station, we have been gathering 90 flux towers, so that's more than 23,000 clear sky days. The peak of solid flux and the peak of net radiation are not synchronous, but the difference between the both peaks is varying a lot from one side to the other. So we took some midday solar noon as a basis, and we looked at an interval which is around it. So the data, that's the main issue of this internship actually. So solid flux can be either measured by this solid flux plates, which is a device that is that big, so very different from the footprint of the flux tower. Recently, some people have been questioning the accuracy of this kind of device for two reasons. One, because it is buried in 5 centimeters, so you have to correct for the soil heat that has been stored between the surface and the 5 centimeters to get the surface estimate that you need first. And then it's a small device, so usually it is placed not really in a place that is representative of your entire canopy system, or at least the footprint of the eddy covariance system. So recently, people have been using another estimate of the solid flux based on the residual of the energy budget measured by the tower. So in fact, the solid flux surface energy budget derived is net radiation minus sensible heat flux minus latent heat. So as you see, in both cases, you have something a bit flat compared to the theoretical empirical values. So you could say, okay, the empirical values have been, the empirical parameterization that I showed before, they were usually estimated on a small number of sites, but still they are pretty consistent to the one with the other. So what is happening? So we said maybe in the first case, we have something that is not very valid for the big solid flux values, that is for a fraction cover close to bare soil, so a fraction cover close to 0, because then you have a large heat flux value, and you have a plate that is probably not efficient. On the other hand, for the very large fraction cover, usually a lot of forest sites, you have values of the surface energy budget that is the residual is very big. You are expecting a very small solid flux, and you have a very big residual. In those sites, some authors have been saying that probably the height of the measurements on the uncertainty on the turbulent flux is not valid to do this kind of thing. So we said, okay, let's combine these two estimates and do some kind of an average or a weighted estimate using the fraction cover. And you say that in the later case, you have a coalescence of the results, which is very consistent with the empirical equations. Okay, you would say maybe it's a bit artificial, but I will come back to that. So we say, okay, for Trishna, we will have the performance of the various empirical relationship with the original calibration, so default, and then we use a global calibration over all the sites. So of course you reduce the root mean square error. So this is for using the solid flux place or the surface energy budget estimate, the average one on the one which is I call mix, which is depending on the fraction cover. You can see that the one from Bug is actually the one that is providing the best global calibration. So since all the empirical functions are roughly having the same kind of behavior, we selected this one for the last calibration. So we have done two things. We have calibrated fraction cover intervals per fraction cover intervals and validated on another flux net point, which has not been used for calibration, which is the Avignon flux tower dataset. And we used another calibration method, which is to use 50 random samples and to validate on the remaining unselected samples. So as you can see, the mix and the average estimate are most consistent with the validation, and you can see that on the validation for Avignon or for the second method on the remaining unused dataset for calibration. And what is particularly interesting is that even for the method which is based on solid flux plates alone, you don't really have a very good retrieval after calibration on Avignon or the other ones. So we think that the average or the mix is really the way to go to define this solid flux ratio to net radiation. So as a conclusion for solid flux to net radiation, it was just an internship. So we used actually a fraction cover estimated from NDVI, which is not the best way to go. So we will use a radiative transfer model, the one that is actually the one for Copernicus, instead of the empirical relationship to have a better fraction cover. And then when we will have done that, we could use for Trishna level 2, the median, the first and the last quantile to generate the ensemble for Trishna. For the level 2, what we have to do is a big issue is to disaggregate air temperature and relative humidity at pixel scale for stick. So that's a big challenge for Trishna, and flag, of course, Evaspa according to assumptions on heterogeneity. So Nesrin is working on that. For level 3, as it has been mentioned, we need to look at climatological data, especially land use and phenology, to run the water budget model. And we should be using also active microwave data, because especially in India, we have a long
period with 1 or 2, and this is the case in Sahel as well. In both cases, we have monsoon, and we can have 2 months with only 1 or 2 available clear sky data. Thanks a lot.
Sure. Thank you, Gilles. Okay, now we will continue with this one. Yeah. Okay. Now we will continue with the next talk, which concerns the estimation of GPP in Indian region using deep learning. Okay, it will. Yes. You. Okay, good.
So basically in this presentation, I would like to highlight the potential of the uses of deep learning or the neural networks to estimate some of the physical parameters such as the gross primary productivity. And we will try to highlight mix the agriculture physics with the modern techniques such as modern data analytic techniques as ANN, and try to generate or estimate the GPP. So basically GPP is the amount of carbon dioxide captured by the plants as the photosynthesis process and stored as the carbon. And it is a very important and the key parameter in understanding of ecosystem productivity, carbon storage, and also is the important parameter to understand the effects of the climate change. So I have listed some of the important parameters those affect the GPP. One is the light availability, the water availability, temperature, nutrient availability, and CO2 concentration. So why it is a challenge? It is very hard to estimate the GPP using optical satellites. So these are some of the few regions that I could figure out from the literature. One is the atmospheric interference such as clouds. So basically optical satellites have the limitation in case of the cloud, in the presence of the clouds. So that is one of the hard challenge that we want to tackle. Second is spatial variations such as land cover variations. So as GPP is very much dependent on the land cover type, so we have to take that particular thing also into the consideration. Third is the seasonal climatic variations. And there are some ways that is used to estimate GPP. One is the light use efficiency, which is very simplest one in terms of the number of parameters. So the equation in its simplest form is given here. So it is based on the light use efficiency, that is the maximum, multiplied by fractions of power that a plant can absorb, and multiply the total photosynthetically active radiations that is available to the plant. Second method is eddy covariance. But since we are talking about satellites, so it has very much limited uses in case of the generation of the GPP product. And third is remote sensing techniques, which take consideration of the various vegetation indices, some of the physical parameters, and try to use all of these information to get the GPP information. So with these kind of background, so the research objective is can we develop a continuous all-weather GPP product generation algorithm using optical satellite data, maybe for the upcoming Trishna mission or some other similar kind of projects in future, applying AI techniques and the principle of the agriculture physics. So with this research objective keeping to mind, my presentation goes on like this. So these are the data sets that I used for the estimation of GPP. So as you can see here, the GPP input in terms of the physical model. So my reference model is LUE model, light use efficiency model. So where photosynthetically active radiation is used as one of the input. Second is fraction of power, and it takes on to the consideration of the environment stress. Typically, most popularly used stresses are temperature and the water stress, and also LUE max. But in case of the AI model that I try to develop, I use either the same parameter or the surrogates of these parameters. So in case of the power, I use the insolation, the available from INSAT 3D at the resolution of 4 kilometer. For fraction of power, I use NDVI as a surrogate variable, but as NDVI is calculated based on the surface reflectance of measured in NIR and red band, so I directly gave NIR and red band to the model. The data source which I used as a for this study is from the MODIS 8 days composite. for measuring or to get the measurement of the stress. So we used maximum LST temperature, which is captured daily. Also, we tried with the surface air temperature, 2-meter surface air temperature, as well as 2-meter dew point temperature. And the sources were from the inset, that is available half-hourly LST at the 4-kilometer resolution. And we used daily ERA 5 surface air temperature also, which was sampled to close to the inset resolution at 5 kilometer. For water stress, we use NDWI because in literature it was shown that NDWI captures water stress in a very good manner. So that's why we use NDWI, and it's also very easy to calculate based on the satellite observation in a VNIR region. So I used SWIR and NIR reflectance as a proxy to the water stress. And it is also kept, it is taken from the 8 days composite reflectance from mode 09A1 Terra Modis. For LUE max, because MODIS also uses LUE model to calculate the GPP, but it has a biophysical parameter lookup table predefined into the algorithm to generate the GPP product. Since we do not have that much leverage, that much luxury, so we try to skip that one because it is a parameter which is dependent upon the LULC, and we thought that maybe the model, the AI model will be able to generate these particular constant values from itself, from the given data, given LULC data. So that is the reason why we have not used LULC maximum. And the other inputs for AI model, we try to incorporate DEM, which was taken from the SRTM at 90-meter resolution. The LULC we use, basically we use 2 LULC. One is acting as a primary LULC, which was from the MODIS, and another one is a which I mentioned here as a secondary LULC, because we want to make sure that that land use cover that we are going to have should have the homogeneity. So for that purposes, what we did is that we took some of the pixels which was lying into the pixel of the MODIS, and if 50% of the pixel values have the same land use class, then we considered we took into the consideration to the model, so that the model will be aware of the homogeneity of the land covers. And for training the model, we used 8 days composite gap-filled MODIS GPP, which was available at 500-meter resolution. Coming to the methodology part, so basically all these the inputs that you are showing here, that are presented here, we take into the consideration. So we started with the maximum minimum 2-meter dew point temperature, as well as maximum minimum 2-meter surface air temperature. Basically, these two information are sufficient to get the relative humidity component. So it will also help to understand the water stress also. So this why these two parameters are important. We use the insolation, as I said, as a proxy to the photosynthetically active radiation. DEM we used SWIR reflectance, NIR reflectance, red reflectance, land covers, and we also try to incorporate the previous 3 clear sky GPP, so that model can see that how the pattern is going on in the current season. So that is why we use the previous 3 clear sky GPPs into the model, as well as we took into the consideration of the average last 5 years GPP mean, so that it can understand the year seasonality. So based on that, we try to generate 8-day data composition. Then we do some kind of data processing operation so as to make a uniform data set which can be given to the model. Stratified data set is necessary because the land use land cover that we have taken was not uniform, and to remove the biasness of the model toward a particular land use classes, we try to give a stratified data set to the model. And at the end, we evaluated the performance of the model in various conditions. So this is basically a feed-forward neural network that we used to produce this one. It's a very simple architecture, and each layer is basically is followed by batch normalization, as well as we use the ReLU activation function for producing the results. So this is the example of, this is the slide shows the feature importance. As you can see, the SWIR reflectance plays a very good important role, as well as we can see that the LST, minimum LST is important for estimation of GPP. As well as here we can see that the previous GPP and GPP mean are very significant features to estimate GPP, as it is very very simple to know that the current season GPP as well as the previous year climatic condition of the GPP is very important for such kind of models. So as a proof of concept, we developed this kind of model and see that whether temporal variables such as GPPs plays an important role. So we found out that yes, without GPP, this was the result. But in the next slide, you can see that when we used the temporal variables like GPP mean and the last 3 GPPs, so we were able to improve the model sufficiently much better than the last one. So these were the results. So in case of the clear sky with temporal variables and ERA 5 temperatures, we've got the R square of more than 0.93. And typically all the models were good enough. And LST as well as the ERA 5 temperature was used both in this case and gave the similar kind of results. Similarly, for cloudy sky, the only difference between clear sky model and cloudy sky was that in case of the cloudy sky models, we did not use any reflectance value as it was not available under the clouds. And this is the results that are used for different land cover types. So as you can see, most of our model was able to capture the variability in different land cover types and able to give the GPP values very close to the actual ones. This is for the cloudy sky conditions. And we also try to generate some, we simulate the cloudy condition while assessing our models in these conditions. So as you can see that we actually took 4 months, March, June, September, and December. So based on these images, you can see that the left one is actually the actual images, and the middle one is the predicted image, and then the errors, and at the end the number of percentage that how within which range of RMSE we were able to get how much data is classified over there. So it's basically a histogram of the errors. So with this, I want to summarize this one. So there is I think there is a need for generating a continuous and gap-filled products. To be operationalized, there is a need to simplified data analytic techniques to be used, as well as the traditional technique also. So we have to use the knowledge that we have from the subject domain as well as the modern data analytic techniques, so that both can be used to generate a high quality products. With this, I complete my project. I finish my presentation. Thank you.
The next presentation will be given by Dr. Saxena. It concerns the estimation of actual evapotranspiration using improvised Sebal model in the semi-arid region of Western Rajasthan. Please.
Thank you, sir. Good afternoon to one and all present. So what I will be discussing has been discussed in detail by a lot of expert speakers in today's session. So next one. So what my study basically consisted of analyzing the variability and the climate change impact on the actual evapotranspiration at a high resolution, high spatial resolution. And the study area which we selected was the Western Rajasthan area of India. It comprises mainly of the Thar Desert, the deserted regions that is completely categorized into semi-arid and arid. So these are some of the details, and the agriculture has been always water stressed. What I mean, predominantly, the entire agriculture has been water stressed. This IGNP project, it was developed. The canal started circulating the water in the region, especially the western region, in the mid 1980s. And since then, there has been a lot of change in the agricultural scenario, as well the water available for industrial and domestic uses. So in the next, we are aware that precise calculations can be done using these field methods such as lysimeter, evaporation pans, but there are empirical equations recommended by FAO. For my study, what I used were the Penman-Monteith and a calibrated version of Hargreaves-Samani method. So it was used for the validation of the model. And what I also used these models for was the reference ET or the hypothetical ET, which is for the reference surface. It is as given by the FAO 56 paper. We also use the meteorological data for inputting some meteorological parameters. Next. So this is the study area. This is the land use land cover map. It comprises mainly of the a large portion is of wastelands. The agriculture portion is predominantly in the northern portion of the black boundary that is shown. Now, the entire region, it has extreme climatic conditions. The precipitation is erratic. The atmospheric demand, or we can say water demand, is very high. So next. So these are the two equations that I used. This is a general form of Penman and Hargreaves-Samani method. In this, we did the calibration for it. We used the literature-based equations. We used the simple Sibal version, Sibal algorithm for calculating the actual ET. So this is a general energy algorithm that has been applied for this present study. We have used different sources for remote sensing data. We have calculated the indices such as albedo, vegetation indices required, the land surface temperature. We have used combination here. We have also used Landsat if we are looking or trying to monitor at the field level. We have also used the MODIS data since we are also trying to evaluate the regional scale study. Okay, so I'm presenting some of the results as there is a constraint in time and the number of slides. I couldn't contain all the studies which I have carried out. So these are the land surface temperature that we have observed over the region for the 4 major seasons that we have selected. That is pre-monsoon, monsoon, post-monsoon, and winter. The majority of agriculture is monsoon based. It's happening during the monsoon and the post-monsoon season. We can see the rabi crop, which is only being grown in the canal-fed regions of northern areas. Now, this is a annual variation of NDVI, which we can, I believe the dates are visible. The year is 2020, and this is how the NDVI is behaving or fluctuating in the region. So many of us have been working in Sibal model. There is an iterative process when we tried the calculation of sensible heat flux. So what the problem arose with me was that the region was experiencing a low wind speed. The daily mean wind speed available was very low. And because of that, this iterative process was not converging as expected. So based on one literature by Dungel sir in 2017, he proposed that if we take the average of the U star or the wind speed that we have using, and again use it in this iterative process, then we can converge and get reliable and accurate results as expected within 7 to 10 iterations. Then second biggest issue or challenge is the selection of dry and cold pixel. Presently, we are trying to develop an automated model so that the selection of hot and cold pixel, which has to be done manually, otherwise it can be automated so that this particular model, which has been developed, it can be used in any different area of similar geography. So these are the results that I obtained for the 4 major seasons for the year 2019 and 20. Now moving towards the final calculation, that is the latent heat flux. It is represented, many of the faculties have already explained, I will not be taking much of time on that. So what equation I've used is given here. Instantaneous EV fraction has been calculated. And in the red, I have shown that what it actually signifies physically, the ratio of actual to crop evaporative demand when atmospheric moisture conditions and soil moisture conditions are in equilibrium. Now, this is the daily actual ET that I have observed. Pre-monsoon is generally the time period between April and May. The crops have been harvested. Most of the regions are fallow or barren. The water demand is extremely high. The summers are on its peak, and it is a pre-monsoon kind of condition. So, and the equation that is shown here, I've used it for upscaling the instantaneous ET that I have obtained on a daily scale. And as we can see, during the monsoon season, both the evaporative demand is also high and the available water is also high. And also there is a development of natural vegetation along with monsoon-based agriculture. So there is an increase during the monsoon and post-monsoon season. And in the winter season, what we can see, predominantly the regions which are canal fed, the agricultural farms that are canal fed. So I selected a representative pixel at a farm area nearby to the weather station. And these are some of the results that I obtained. While comparing the Sebal-based ET with the Penman-Monteith-based model, we received a good accuracy as expected. I want to highlight the use of Hargreaves and Samani model because there are areas and we are well aware that there is a high scarcity of meteorological data. And in those cases, this Hargreaves-Samani method is very useful once it is calibrated for that particular region. Just the minimum and maximum temperature data can be used, and we are obtaining a R-square of around 0.86, which is decent, satisfactory. So that's all from my side. Due to constraint in time and number of slides, I'm not able to. But what we have done is we have also studied the land cover change over the past 30 years, starting from 1990, 2000, 2010, and 2020. I have done simulations to project what will be the land cover changes till 2050. Apart from that, what we have tried, we have used the CMIP 5 model based RCP 4.5 and RCP 8.5 based scenarios. And we have taken the maximum and minimum temperature parameters. We have incorporated it. We have upscaled the ET results to annual to seasonal levels. And then again, we have projected for near future till 2050 and far future till the end of the century. And we are able to provide the stakeholders and the farmers that how the evaporative demand will be increasing, how ET is varying with season, and what are the expected impacts of the climate change. That's all from my side. Thank you.
Thank you. The first presentation concerns the estimation of evapotranspiration and soil moisture by integrated use of optical and thermal infrared observations from MODIS. It will be given by Dr. Rial. It was correct? No.
Sweta Pokhriyal. Okay, she is my student also.
It's Shweta Pokhriyal. Okay. Good afternoon, everyone. I'm Shweta Pokhriyal. Today I am presenting on the topic estimation of evapotranspiration and soil moisture by integrated use of optical and thermal infrared observations from the MODIS. My team members are Dr. Patel, Ina, Natsa Guren, and Dr. R.P. Singh. So we have sustainable agriculture, precision agriculture, more crop per drop. These all concepts are based on the estimation of simple agrohydrological variables like your evapotranspiration and the soil moisture. So in this particular study, I am focused particularly upon the estimation of evapotranspiration and also the soil moisture. So we know that in India, the sparse measurement networks in India, they usually fail to represent the diversity in the vegetation. So remote sensing in this manner that provides scalable and the consistent data set. So these methods will minimize the dependence on the ground-based measurements, making them ideal for the regional scale studies. So in this regard, this study was carried out in the Uttar Pradesh region of India. So this is the western part of the Uttar Pradesh region. This region is actually a semi-arid region, but is predominantly an irrigated region because of the high water table region. So the study was conducted from the December 2007 to March 2008 for the wheat crop particularly. The data set was of the MODIS data set, and the ancillary data set was of 6 stations was taken for the daily meteorological observations, and field measurements of the soil moisture data was taken at the 28 sites on 14th of March 2008. So from the last few days, we are talking about the various ET estimation models. So in this study, we have utilized the SCB, that is a Simplified Surface Energy Balance Model Index. Like in the previous previous talks by Albert and the Gill, we have come across the advantages of the SAB model, which does not require the minimal meteorological data to calculate the fluxes. So this whole study is based upon the SAB model, particularly the estimation part. As we can see here, the Dr. Ishwar has talking about the relationship between LST and the surface albedo. He beautifully expressed how the with increase in the albedo, the ecosystem changes from the water limited to the radiation controlled system. So this is the whole framework of the ET model. Here we can see how the evaporative fraction is calculated, and net radiation in this case is calculated using your short wave radiation, and short wave radiation is calculated using your MODIS cloud cover dataset. You can see the equation in the below section. These are some of the results. As you can see here, the results are on the specific dates in which the MODIS data is acquired. So you can see here, according to the color template of the images, you can see how the ET is varying according to the phenology of the crop. And on the other side, we can see here the ET is estimated and is validated with the ET estimated from the Penman-Mantis equation and also the pan evaporation data set. We can see here the relationship between the ET estimated from the SAB model, and the Penman-Mantis model was found much higher in comparison to the pan evaporation method. Now, the second concept is the soil moisture estimation. The soil moisture estimation was was done using the apparent thermal inertia. You can see here the flow chart of the soil moisture estimation, in which the MODIS Landsat data of the daytime and the nighttime was taken to calculate the thermal inertia, the apparent thermal inertia, and with that the albedo from the MODIS dataset was also taken along with the soil water constants, that is your field capacity and the permanent wilting point, to calculate the soil moisture saturation index, that is further are linearly scaled to get the soil moisture. So these are the constants which was developed. These are the maximum that were retrieved actually. These are the maximum available water content is difference between our field water capacity and the permanent wilting point. This is the apparent thermal inertia that we got through using the constants and the albedo, as I have discussed it earlier in the earlier slides. This is the soil moisture saturation index, which is calculated using the ATI, that is the apparent thermal inertia of that particular pixel, and the maximum and the minimum apparent thermal inertia for that particular pixel using the long-term data set. So in this case, the long-term data set is taken is from 2002 to 2008. And you can see in the lower portion how the ATI is calculated. That is 1 minus A by divided by, this is your difference in the daytime and nighttime LST. This is how we got the soil moisture index for particularly for the 14th April 2008. We can see here, these were the validation points. We have validated our soil moisture results at different depths. Like first one was the 5 centimeter, 15 centimeter, and the 30 centimeter. The relationship of the 0 to the soil moisture estimated, particularly at the 0 to 30 centimeter, was found much stronger in comparison to other that varied from 0.6 to 0.7 in this case. So if I talk about the conclusion of the study, the SCB method that we already know due to the minimal amount of the meteorological data set used in the model, that is easily amenable to the satellite observation and can easily captures the variability in the evapotranspiration with almost negligible meteorological inputs. The ET's estimates that were based on the remote sensing evaporative fraction that showed the good agreement with the actual ET estimate. Particularly from the Penman-Monteith equation, that the R-square varies up to 0.86, and less agreement was found with the Penn coefficient, Penn evaporation method. Secondly, the second component, the soil moisture index, that was from the long-term apparent thermal inertia, that provides a good measure of the average soil moisture, that is particularly in the 0 to 30 centimeter depth. The agreement between 0.6 to 0.7 that was observed between the in situ soil moisture and the estimated soil moisture values that was estimated from the ATI measurements. And further, more in-depth research focus that is needed, that to implement the ATI, and subsequently the missions like the Trishna, the SPG missions, these are very much these weighted missions are very much important for Indian conditions in which the average land holding capacity is continuously decreasing, and as of now it is only 1.08 hectare. For those fragmented landslide and the land segments, and for the field scale crop yield estimation and the agriculture water management. So these kind of missions are very, very much important. That's all from my side. Thank you so much.
This session technically enriched because it constitutes all three components: soil moisture, evapotranspiration, and productivity, which are the basic component of ecosystem functioning, as well as this is unique in the sense because it began with the highly complex and uncertainty associated with the to-be product of Trishna, then machine learning, then sheer application of agro-hydrological variable. So this is a unique session which have raised interest among many people. So there must be many questions among audience. So now I invite all speakers on the stage.
Question, please.
Question to Juval. I pronounced correctly? Okay, just I was not clear what you connect land use efficiency to land use and correction, because you need to know a bit the efficiency of conversion. So do you just limit this to planting C3 and C4 for the land cover, or you go further than that?
So basically, we went through the ATPD of the MODIS product, GPP product generation, and there the biophysical lookup table was there, and there was a coefficient given based on some studies that they carried out, and that coefficient was just an integer. Okay, so we thought if we apply all the sufficient information that is used to calculate the GPP, so model it will automatically find out the optimal value or the optimal integer that will be acting as a maximum value. So that is why we removed the necessary of finding LUE, maximum LUE. So that's why we are calling it as a semi-physical model.
Thanks, and it's clear.
Yes.
A couple of questions. So actually for Dhruv and Shweta, I've seen that you have compared your evapotranspiration with ET0. Reference ET. And you could find that I think 0.86 or very good correlation and the RMSE. But I'm surprised that how you could get it. Because one is only depend on the atmospheric demand, okay, and others is taking both soil moisture variability and all these constraints. So can you just explain? No, let Dhruv answer. You can answer for Shweta. Okay.
Yes, sir. So based on literature, firstly, we selected the civil model, and then regarding this question, sir, the Penman-Monty, the basic criteria, all the details, they lie in the FAO paper 56. So it is a very generalized and it's applicable method. And we were fortunate that in this case, in the semi-arid region of Jodhpur area, we were able to get the data R square value as 0.88. So I'm not getting the exact question.
You know the difference between the potential evapotranspiration and the actual evapotranspiration.
Yes, sir.
So you are actually comparing the actual evapotranspiration with the potential evapotranspiration.
So one parameter.
Actual to actual, you have to.
One parameter, yes, sir. I got it.
Yeah.
So one parameter was missing.
No, I suggest you in future. I think if you want to compare or contribute in the Trishna program or Calwell, so I think there are a lot of ET covariance tower data available, like we share with many people, I think with Shekhar and.
So I talked with Patel sir this morning only about.
Just for your information, I'm just giving this thing. Okay. Otherwise, fine.
One addition I want to make that that component was missing in the presentation. I used the crop coefficient data as well for different seasons. Like I have taken 4 major seasons. So based on the crop cycle, we have also worked and identified on what are the major crops that are grown in that particular area in that particular season.
That's fine. We'll talk afterwards. Okay.
Thank you, sir.
Just I am giving you this information. Yeah, but Dr. Patel, you have so many flux towers. So what is the need of?
Dr. Vimal, this was carried out past data, but actually it was adjusted first pan adjusted coefficient and then it was adjusted for the LAI and with the crop coefficient. So she has written already the PET Penman multiplied by crop coefficient adjusted ET. That is not simply potential evapotranspiration. That is a crop coefficient adjusted ET by Penman as well as pan evaporation.
Okay.
That's why R square value is increasing. Yes, sir.
Okay, fine. So I think both of you are in the same school of thoughts. So my question to Zil, that it is just general question, not related to any technicality involved, that this ecosystem activity under Trishna, what is your thought that how from Indian sides we can build some very good collaboration activity, because many people are here and to contribute to the different problematic aspects in the overall development of the product and also maybe the more science part of that?
Well, it's a bit difficult to answer because I'm based in India, so I have really the main concern is about the cloudiness. Really, I think the thing is that in France and Northern Africa, the moment where we have the most clouds are the moment where actually the atmospheric demand is the lowest. So it's not as important as in India. So I think it will be very interesting to have in V1 and V2 for the L3 to have a big involvement of Indian teams. And especially there is NISAR. We were discussing with Professor Shekhar. NISAR is coming up. So a question would be like, if we combine, or what is the level of complexity of the water budget we have to use for this 2 months of data of monsoon where we don't have any data, and how can we actually harmonize, for instance, soil moisture from the different sources of active microwave to have some answer during that season. Of course, another idea on the same kind of problem was what Raoul has been mentioning. So can we actually have a traineeship or a PhD student looking at all the FluxNet stations and look specifically at the cloudy data? Is really evaporative fraction, how does it vary? And can we find some with a neural network or whatever, some factors and some models? I'm pretty sure there are a lot of other area where a lot of Indian teams can contribute, but I think this one, it comes immediately to my mind because I know that Professor Shekhar, I know that in IIT Hyderabad as well, there are people working a lot with crop coefficient derived from radar data. So that's the first that comes to my mind, but there are probably a lot more for atmospheric, for incoming radiation. What are we going to do in India? So a lot of it is very meteosat oriented. So we have to do the same work in India. This kind of work.
I think we can separately discuss more on this focused. Maybe Shekhar also can be roped in that. So to formulate some good plan of the identity, especially over the subtropics, how we can address these challenges.
We would like to have people involved in the forest group.
Yeah.
And in the topography group. So for the moment, a lot of work is done by our colleague Olivier Merlin on the Atlas, the Moroccan Atlas Mountains. We need to have people working in the Himalayas and try to cross-validate or cross-propose some solutions for the mountains.
Right. So now I have just request, Oyon has come. So can we take up his quickly?
चेंज कैसे करें? Okay. ये वाला? Good afternoon all. So I will be presenting on the long short term memory to estimate the cloudy sky evaporative fraction. So we all know that cloudy pixels will occur in most part of the time in the globe, and you can see that the monthly variations of the cloudy conditions. The data has been taken from Google Earth Engine data frame, and in theory, the cloudy pixel can be filled by some linear interpolation techniques, but the relation between the evaporative fraction and some other variables is actually not linear. So we need to take into consideration the nonlinear part. And we'll see that how we can tackle this. So the study has been done over 5 parts of the globe. So I have taken 3 slides from Ameriflux and 2 slides from OSFlux from having different land use and cover types from cropland, forest, grassland, and rainforest with very high dynamics of rainfall variations. So the slide shows the yearly variation of average atmospheric transmittance and the evaporative fraction for each day of the year. So the points you see, those are the averages of defined points for a particular number of days. The color of the points are the standard deviation across multiple years we get. And you can find the regions where the variation in the atmospheric transmittance are higher. There we also get very good, very high fluctuation of EF. And if we plot the average transmittance versus average EF, the relationship is not linear, rather it is a exponential relation. As you can see in the corn, it is having a lesser amount of slope. And when we move to the forest side, that is the Morgan Monroe State Forest, there the similar relationship also holds, where but the curvilinear nature of the curve actually increases. So the curvilinearity increases. And again, moving to the grassland, there is no such relationship existing. So it tells that the modeling of EF under cloudy sky is not very straightforward, and we cannot imply simple linear interpolation techniques to fill those gaps. So we need to have some nonlinearity introduced in this modeling technique. So we have taken the help of, one deep learning technique for estimating the all sky EF. So here I have utilized the long short-term memory network. It is a variant of the RNN data, where we use a time series to get to know another time series. So there are many variants. So the evaporative fraction along with some ancillary variables are fed to the data. For example, the atmospheric transmittance and the date of the year. And finally, it predicts the all sky EF. So the data we have taken from 10 a.m. to 2 p.m. and we have filtered the values to have the transmittance for less than 0.5, and also we have taken the value between 0 to 1. Then we have normalized all the features, and then we have done a train and testing splitting, then fitted into the stacked LSTM model, and then have done the prediction. So this is the result. So we have found that we have two cases where we have given both the cloudy sky and the clear sky EF in the training data, and while doing the prediction, we have only the cloudy sky EF. In another case, we have only fed the cloudy sky data in the training and tested it on the cloudy sky EF. And the table shows the correlation between the actual and predicted values over the test data set for different sites. And we can find that whenever the rainfall increases, the uncertainty also increases. So the grassland side, we have very good correlation, and the crop and forest side, we also have very good correlation. But the OSPAC side, there the annual rainfall is very higher, so their uncertainty also increases. So this shows the prediction curve. So the top curve shows the sequential addition of different parameters. The first curve shows the modeling only using the evaporative fraction. And sequentially, we have added the atmospheric transmissivity and then the day of the year. And you can see the blue lines are the actual value, green lines are the training value, and red are the testing value. And you can see that we can get very close to the reality. And this is for another site over forest. And here you can see that we have very good patterns of variability is picked up, but typically at the lower values, we're having some error bar is higher. But by considering the transmittance along with the day of the year, we can further reduce the accuracy, reduce the error. We have also utilized to use the hourly data in the modeling framework, where we have first taken the hourly data in the training framework, then we have done the prediction, and then we have upscaled it to the daily scale. And we have found that whenever we have fused the hourly data in the training framework, we have subsequently increased our model prediction accuracy, and the result for two sites are shown. And the color of the point shows the variation of transmittance. And you can see that over a very good range of transmittance for the cloudy sky condition, it is fairly well predicting the values. So we wanted to see that how the diurnality of the prediction accuracy varies. So we have simulated from 10 a.m. to up to 2 p.m. How the accuracy varies when at instantaneous scale. And you can see that the higher accuracy from 12 noon onwards we are getting. So obviously, that considering the Trishna overpass, we expect to get similar kind of accuracies. But obviously, these are from the ground-based data, so we need to test it for the satellite remote sensing data fusing it. And although and these are the machine learning models, so under different scenarios, it may go into unbounded conditions. So we need to take into consideration the physical models also and decide the boundary conditions. We have only considered the atmospheric parameters now for the modeling, but in future we plan to use some of the land features also to further fill the gaps. Thank you.
Yes, we will continue the questions. You have a question? No, it's finished.
Hello. Do you have one model for all the sites or one model per site?
No, we have now site-specific models. We have not combined all the models.
Thank you.
And usual, I have one query for you. Okay, you have done some AI ML based model. So how it differs from TGR, temperature, Guinness and radiation model, and how it differs from decision tree model. There is a decision tree. You can, every land use wise, you can generate one regression model. Yes. So basically, in the tree-based method or these kind of method, they gave us the certain rules, and it's up to us that we understand these rules and do the kind of things. In theory, the tree-based methods, like random forest and on the TGR method that you are talking about, and the machine learning method like ANN, they do work very similar kind of condition. But one thing is that one gives us the power of explainability, and one works as a black box. And that but both have it in the literature is shown that both works well given the hyperparameters are tuned properly. And in case of the tree-based method, sometimes the number of hyperparameters are more, and for each kind of properties we have to understand the thing and then tune the parameter, which takes a lot of time. But in case of neural network kind of architecture, it is very simplified. So that is why we preferred over there. We tried other methods also, but we finally finalized over the ANN.
Yeah, Ujjwal, just I'm very much interested to know more about this AI-based GPP product. So have you compared your predicted GPP with any of the field-based data or eddy coherence-based GPP data?
No, sir, not yet.
Second one is epsilon max, about you said. So earlier it was the lookup table developed by the Modis team. So now we have conducted a lot of experiments in India. So all the data required for simulating that epsilon max value to the actual this land use land cover. Have you tried using region with a region specific vegetation specific epsilon max into that model? That's a two thing. Just
okay. Usually I can give you one suggestion. You can, there is a forest inventory, forest biomass inventory, another is the crop census data. Different crop types are there. Crop status is available for last 20 years. You can invert your this, okay, suppose any model is there, you can invert it to get the LU max. Then you can use. Basically, the reason why we do not consider the LUE max is because as you know, the equation of the LUE model, so there is only a quantity which governs the whole equation. We have the par value, we have F par value, we have the stresses rated inputs, and we have LUE max, which is just an integer value. And the ANN has the power to understand that equation, and it automatically, since we are giving land covers as an input, so it can automatically generate that particular value based on the land cover types. That is why we do not consider it, but yet your suggestion is very welcome. We are welcoming it, and we will look into that. Conclude session of this ecosystem and stress and use.
Okay. So as a token of gratitude, we will like to present our session chairs with memento. We request Dr. Albert to come on the stage and present the memento to Dr. Nicholas. You can go this way. I again request Dr. Albert to present the memento to Dr. N.R. Patel. So as we conclude this session, we extend our gratitude to Dr. Nicholas and Dr. N.R. Patel for conducting this session beautifully. We also express our gratitude to Pradesh Jena for noting down the important minutes of the meeting. We thank all the speakers and the audiences for the successful session. We will assemble at 4:30 p.m. So you can all visit the back of this auditorium for the poster session. आगे. Good evening, everyone. So, may I have your attention, please? Now we will begin our fourth session of day 2, which is on water and heat stress management. Let us invite the session chair, Dr. Chandrasekhar and Dr. Rahul Nigam on the dais. I also invite Rapporteur Anand Das to join us on the dais.
Very good evening to all. And we have a very special session on water, heat, stress and management. And without delay, I invite Dr. Shekhar from ISC Bangalore regarding the potential of Trishna for agrohydrology and watershed management applications in India. Over to you, sir.
How to do this?
Thank you.
So, thank you. Thank you. We are running a bit late, I think, for the session. So, good evening to everyone. And I chose to present a topic where we thought we have heard a lot on algorithms, science, etc., how the science goes to the next people who will use it, who will contribute back as a feedback for our calibration purposes. So with that as in mind, I thought I will present some ongoing activities in India especially, and how the stakeholders could benefit and also contribute to our science. So let's look at it. One of the important problems in Indian context, as we were just discussing, is water stress, which was already mentioned by several people in the morning. So one of the things is the groundwater problem, where the groundwater resource is heavily used in India. As you can see, we use a lot of groundwater in comparison to many other countries. But interestingly, this use of groundwater is not limited to command areas or select areas. So it's spread out everywhere, even in all the parts. So this also proves a challenge when we look at I think the issues which came up in the afternoon session when we said if it's a cloud cover and what is the ET there, and there is a groundwater use in a small parcels and so on and so forth. So we'll come back to that. And so I tried to present some of the recent work of my student who was looking at combining you already have the initial steps of water use efficiency was pointed out. So here is an example of water use efficiency estimated over a longer period, or between 8-9 years, 2010 to 2018, in the entire Indian system. Now, what we tried to do is, we knew that the groundwater tables are quite varying in the country, especially in the peninsular India and some parts of the areas in the western hemisphere of India. So as you can see, so there are deeper water tables. And we tried to put the water use efficiency map on your left, as you can see. And you will see that low water use efficiencies are also linked to deeper horizon, deeper water tables, which are under use, and so on and so forth. Why I wanted to point out this is there is a strong link between when you compute your water use efficiency, you have both GPP and the ET, and a good estimate of ET will help us to understand what is the water use efficiency, especially from groundwater use, where the water tables are gone down, and how. So it all depends upon how good we estimate our ET. So that means the challenge for the community who are using this for improving the use of groundwater, for buffering, or doing the demand side studies, for example. So the point which I wanted to say is also that the deepening groundwater tables in many parts of India are also linked to the yield decline in water. So that means the amount of water which can be pumped from the groundwater system, especially in fractured rocks. India is about 2/3 hard rocks, and the other one is alluvium. So which will have an impact. So as you can clearly see here in this slide, If it is an irrigated area, the groundwater tables are going down with the time, and as the groundwater tables are going down, the yields are also declining, which means that my ET is contributing differently, and so on and so forth. So in short, it also puts us into an important context for our stakeholders who are going to use this information in the form of how to improve our groundwater management in this context and sustain the food and food production, and also probably food, water, energy nexus, because these deepening groundwater levels also guzzle a lot of energy. And how do we manage this? By using supply and demand side, which requires a good assessment of ET. This is what the user community is asking at a higher spatial granularity. Needless to say, I'll try to go back to a small pixel, like, for example, a small watershed. This is about something like 5,000 hectares. Typically in India, the watersheds are managed at micro watershed, which is about 500 hectares. These 500 hectares are treated through various programs in the country. So that means a bunch of watersheds, about 8 or 10, belong to a sub-watershed, and the sub-watershed would look like this. As you will clearly see, the green patches are the ones which are under plantation. That means you have a crop throughout the year, so which cannot be sustained by rainfall, it cannot be sustained by any other means, but by using either a lot of groundwater use, so especially in dry land areas. So that means you can see that along the drainage lines, a lot of plantations, and these plantations have a lot of evapotranspiration happening. And in order to do this, we worked some years ago. This Ishwar is here. So with Ishwar, we started this work of trying to build ET products across the country, and we started using them more so. So now it is much more easier to use this. So for example, if you take this sub-watershed and try to put the ET, so we have 1 kilometer and 5 kilometer products available. I'm hoping that we'll have much finer products as we go along. But what you see interestingly in this is that we still have a good capture of information. So you can see where there is a water body, my ET is relatively higher by several magnitudes. You have the rainfalls are probably 600-700 mm, but in some years it could be higher. But you can see that the huge variation of few hundreds of mm in ET between pixels in a small watershed. I mean, small means we are talking about 5,000 hectares. So if you take 1 square kilometer of 100 hectares each, so you can see nice variations in these pixels. So this is something which is very critical for us to be able to estimate, especially. So what I wanted to say is there are a lot of errors at the daily scale. Probably we are discussing several things, but for many applications, even a fortnightly ET is great, because we're talking about management plans and our stakeholders are looking at 15-day, weekday, or even at a monthly scale. So this becomes a critical exercise. So for example, an exercise which we were doing for some watersheds was helping the Department of Land Resource in designing them. So for example, if you carefully see here, it's a monthly product of ET is used for a watershed, a micro watershed of the same, a small pixel there, 500 hectare, and try to put that in the form of a rain minus evapotranspiration. The interesting part is most of India has a good rainfall product. For example, the state of Karnataka, where I come from, the rainfall has probably, we have 15-minute rain gauges, about 6,000 of them. So rainfall is well collected at the ground level. But what is probably missing is a good futuristic ET. So currently we have something. So if we are doing a rainfall minus ET, what do you see here? You see that, this works only. Okay. So the Kharif part in the middle, which you see, is the May-August period when you have the agriculture going on. And in this period, you'll see that we have roughly rainfall minus AET is positive. That means there is a good conservation plan happening. you have still higher surplus water during the Rabi season because there are not many crops, which is second crop, but that is aspiring, which will happen in future. But in the plantations are taking a lot of water in the season, which is the summer season or January to April, May season. That's where the groundwater use, and you see the negative deficit of rainfall minus ET. So the interest would be for managers who are managing these watersheds would be to put the water in these places by looking at ET. So the better way of trying to understand ET would help in designing our watershed management plans. So that's why I said, so many DSS tools developed by, like, for example, Department of Land Resource, watershed management programs, they are looking at ways of doing it at micro watershed scale, which would require one of the inputs is from an ET. I will also show you an example of, even for designing watersheds a priori, there is an interest to say which watershed I should do rehabilitation or restoration. A country like India, they have some money every year and watershed management programs go on. Each watershed, as I said, is a small watershed, micro watershed. So now here I'm giving you a well-known, many people probably know this. This is a Budikov curve, which is a Budikov plot, where you're plotting the potential evapotranspiration versus precipitation on the x-axis, and actual evapotranspiration on the precipitation on the y-axis. Typically, if it is a natural system, my water limit line of 1.0, where actual evapotranspiration by precipitation will be 1.0. But you'll see several dots in watersheds which are above this. This is not what originally thought about by Budikov, but now you see here that these plots indicate that a lot of groundwater is used beyond the rainfall in those regions. So in canal command areas, you always have this situation, but we're talking about rain-fed watersheds where the water is closed with rainfall and evaporator. So quickly you can see these areas where the evapotranspiration or precipitation is much higher than the orange line, which Budikov said is sustainable. It's also useful to close the water budget because AET by P, the rest of it is for you runoff and groundwater recharge. So one can, if you're looking at the mass balance by saying rainfall is converted into runoff, evaporation, and recharge, these kind of plots will give us a good water balance. But the important point which I wanted to highlight here is that a good evapotranspiration is helpful for making a decision on which are unsustainable watersheds, which are sustainable watersheds as of now. And that's a first step for the decision makers or the ground people to start implementing their management program. So that means the ground users in the field, people are already looking for good ET products, which is good for us, community on the science. How do we transfer this information? So this is another cartoon which tells you how we can adapt the ET to further to look at making making some understanding about the groundwater. This has been some exercise which we've been doing. Typically, the groundwater levels or maps are being made by using simple approaches of groundwater budgets through topography and other things by recharge. You can see nice papers on groundwater level mapping in the continental United States by the USGS and so on. In a country like India, what happens is the groundwater level is dictated not by topography and recharge, but also by a lot of groundwater pumping. So here is an example of, I wanted to show the cartoon by saying the same plot reconverted into depth of groundwater with evapotranspiration precipitation shows an interesting signal. The yellow band is where you have canal command areas where evapotranspiration is high, but groundwater tables are shallow. But when you are on the other areas, if my evapotranspiration is increasing, my depth to the groundwater level is also increasing. That means one can use this information to be able to make a good assessment of groundwater level, which is also a very useful index. So that means some kind of an evaporative index for this. I may have few slides, sorry for that. So I was just pointing out a previous USGS work where ET is not used, but they use topographic index and recharge to present a continental groundwater level, I mean, the groundwater level map for Conus region in US. So coming back quickly, 1 or 2 slides on how do we benefit from the sites which you have in the different sites. We were discussing about how to benefit the science from the existing data products. So in Karnataka, we launched through the government initiatives, we have several sites which are Bowen ratio energy balance sites. We could not afford AD towers, but we thought these are much easier to manage and much more easier to handle, and but also can significantly benefit in making an evapotranspiration calibration validation. So we have several sites, about 25 of them, which have been installed last year. We have more than a year and a half data set, and we are promoting this in several. This was from the previous earlier BRB site, which we have put long back when Bimal and Dr. Parihar were involved with when we started the work with Ishwar. So, but still, we are happy to have these sites because these are starting to provide. So, like this, we are planning in Maharashtra, we're planning in Uttarakhand, in Himachal. I think there's going to be more and more BREB sites. What I wanted to say is that local agencies are happy to put these sites than putting in AD towers. Chandrasekhar will talk about AD covariance sites, but the local stakeholders are not very happy to put the AD towers. But we can have a combination of these to fill up the gap for our calibration. So, but what comes out of it? But interestingly, these sites are co-located with multi-soil moisture sensors. So this is a good opportunity to do, and also heat flux plates and all that. So it will probably help us to fill up some of the science gaps which are pointed out in the session 3, session 2, and so on and so forth. But then there are some challenges. We also have the site, just to show some of you, where every time Berambadi comes up, but you're not seeing the site. So I thought of the Berambadi site is shown in the circle over there, which is comprising of AD towers, BREB towers, and we have the new LICAR being also set up for co-calibrating all the sensors to see how much error among them. And also we have several other measurements over here. And it will look something like this, and quickly to show the 2 towers which are very close by to be able to calibrate and evaluate the performances of them. But I think Atira, currently working with us, tried to quickly evaluate the ground measurements from these tower sites, and we tried to compare with the satellite product, in this case, Gleam. What is appearing is to be a very large bias. So there is also a problem of what we get from the ground versus what we have to do with the satellite product. That's also an important, because when you convert the evaporative fraction into ET, you look at the number of hours of the day, and the number of hours of the day is producing a lot of positive bias, and the evapotranspiration is much higher. So what I think Atira was doing was reducing the number of hours to match this. So now the question is, how many hours in a day you should use for this, etc. So this is a question which I have, and probably I think we will mull over it with all of us sitting together to say what should be the way to convert this database into a good database. So going back, last slide, probably the synergy to. There are 2 ways of synergy. We're talking about how do soil moisture helps the ET community, ET community, and how does ET community help the soil moisture. So I see Anup Das also there. So the interesting point is, here I am trying to look at how thermal data could improve my soil moisture modeling. So the vice versa. So what is being used is that typically when you want to derive root zone soil moisture map, the surface soil moisture map is assimilated, or surface soil moisture assimilated into hydrological model like this, and then get the root zone soil moisture. So you have two opportunities. You can do a surface soil moisture assimilation and surface temperature, also soil temperature assimilation. So let's say you're giving LST, I can do the surface soil temperature and use it as into the assimilation. The advantage is that you have several microwave satellites. Addition of every 3-day Trishna product will enhance our root zone soil moisture. So here is an example of that. I'll show you the observations at different depths of soil moisture in these sites. It's one example of one site, which I showed you about 25 sites where we have multi-depth soil moisture measurements continuously. And black dots are the soil moisture measurements. And if you were to give only soil moisture from 5 centimeters, you have the blue line. At sometimes, especially if it is a layered soil, you have a poor performance. But if you have a temperature, you get a much better performance. So that means combination of temperature and soil moisture is a great asset for improving the root zone soil moisture. This will be a good opportunity of a synergy of a different kind of merging the temperature and moisture. So I just wanted to show that how it really benefits. So if you were to look at the parameters estimated in the assimilation, typically when you are assimilating the data and estimating both the variable as well as the parameters, you can see clearly that the best estimates are obtained when you have both soil moisture and temperature being given at 5. So what is shown in the third column is the soil moisture and temperature 5 for a layered soil. That means we have layered soils where the lower layer properties are completely different from the upper layer. It could be a black soil sitting on a red soil or red soil black. So estimating root zone soil moisture not easy. So you can see very good estimate of or the question of variation of these properties or uncertainty in the parameters is very low. So this does not mean that we have to use complex models like this. There could be a simpler models, which is what we're probably discussing at tea time, saying that how do we use the gradient of root zone soil moisture and like this with surface soil moisture and use it as an information back into thermal into ET products based on the gradients or time lapse between two different times. So I stop here and thank you for your patient listening.
Thank you, Dr. Shekhar. And first we will take questions for you because you are in rush. So if you have any questions, please raise your hand.
Hello, Professor Shekhar. A nice presentation. It is not a question, it is rather is a query that in the JGR journal as well as you have shown, there is a relationship between groundwater level and the ET.
Groundwater level and?
ET.
Yeah.
My question is groundwater level, what kind of groundwater level it is? Because whether the water percolates down, whether it is a water table or it is a confined aquifer, because if it's a confined aquifer, then it will not percolate down and the relationship is very difficult to establish. This is my query. I don't know.
I didn't show that it is a ET and groundwater level. I said water use efficiency and the groundwater level. So where the groundwater levels are lower, where the yield is lower, correspondingly my water use efficiency is also low. So it is telling you that your productivities, etc., are getting low due to your water use.
I agree, but in the plot, particularly in the JGR journal also, what it has.
Okay. So,
yeah, that is a relationship between the groundwater level and the ET.
Yes.
And in that case, groundwater level must be a water table or whatever, what kind of groundwater level, because the area where you have studied is mostly a fractured aquifer. It's a unconfined.
So again, the same concept. The ET is linked to amount of water you can bail out. Irrespective of most of these fractured rocks there is nothing like a confined aquifer in the alluvium. They are fractured rocks, there's the one and a fracture. And the yield is, I showed you a yield versus groundwater level depth map. So most of the time as the groundwater level goes down, the yield goes down because the water column becomes smaller and smaller, your transmissivities are becoming. So essentially they have an input information on the ET.
There should not be any confined area in between it.
No, there is. Exactly. In fractured rocks, there's no confined aquifer.
Sir, just I have one query. As a Karnataka, there has a this you have shown second or third slide that the total rainfall and ET. So you have shown that this water storage. You have just
Yes.
that rosy picture comes that in Kharif, Rabi. So, but that for entire Karnataka or for South Karnataka or
No, this is for one micro watershed.
watershed for only
One
watershed.
watershed of 500 hectares. So you can
Okay.
do this exercise. You can do this exercise in several places. It's possible that in some places you wanted to quickly figure out which season my water stress is likely to be and where I want to do a better management.
Thank you.
First of all, compliments to Professor Shekhar for such a great work, because groundwater is a great problem, actually. In fact, from SAC ISRO, even a layman also sometimes asks who are the agriculturists here, and they ask only the same question. Sir, can you give us some kind of location where I can put bore well or something like that for my agricultural field? Okay. So that's why the subject is very important, and you have linked it to the evapotranspiration and precipitation. So that is another thing. And next compliment is that the work which we have started long back, and that you have taken it forwarded to the state level. Actually, for AD covariance is more of the science understanding, but this slow response sensor BREV, that is more adapted to the operational kind of nature, where maintenance requirements will be very, very low, but it can give you some reliable estimates of 7 to 10 day or maybe 15 days average kind of thing, where actually hydrologists also will be interested. So in order to take it further, just I would like to know that suppose you are putting tower somewhere, so you need the faster computation and automated computation, because state government may not be aware about the computational part. So you are looking for developing some software package, so that that package also can be given with that, so that anybody can just click and get the ET data. Okay, so long back we have come up with some FluxSoft software, yeah, which actually takes both BREV and the aerodynamic part also. So if you require any help towards that, so we are always there, and just throw some light on that about your vision for the software packaging or for that.
Okay. So I think for the last comment, very, very useful comment, because right now some of us are helping the state governments when they put these investments to help them locally, but they are all going fast. They are putting this data in dashboards. They want people to use the data. So will become redundant. So I think such kind of softwares can be given to state governments, and local communities can directly use. So it will have a large far-reaching implications. And these data are also, because they're putting in dashboards, they're open nowadays, both state governments. So I would say that these will help us in our improved calibration, apart from so if you see a bunch of 25 towers in one state, similarly another state 25, we are talking about a large numbers, which can be useful for improving our science also. Thank you.
If there is no question, then I will ask sir a very simple query for my side. That in last few years we have seen there is a change in the rainfall pattern in distribution in temporal and spatial form also. We have receiving very heavy rainfall also, and sometimes very scarcity. So this also impacting. There is any study that we can convey that how this affecting the groundwater recharging also?
Okay, this is completely a different subject, but we see that the groundwater traditionally was assumed that most of the high rains or high intensity rains go as only runoff. But in the recent times, some of our studies are showing that you have something called indirect recharge, which is also benefited from the large number of infrastructures created in watersheds, because the water which comes doesn't get out of the watershed, because you have hundreds of check dams nowadays. So this water which is staying is helping in the form of an indirect recharge. I can tell you that in 2020 we had big rains in south of India. Water tables went up by about 30 meters. So there is new papers on nature science and nature communication looking at groundwater and links to high intensity rainfalls.
Sir, thank you, and give a round of applause to Dr. Shekhar for his presence in this workshop. Thank you, sir. So now it's my turn to ask Dr. K. Chandrasekhar is also co-chair to deliver a talk on detection of flash drought and utilization of evapotranspiration for improved irrigation scheduling and performance evolution. Over to Dr. Shekhar. Chandrasekhar ji.
Good evening, everyone. This is actually, this is my colleague's study. There are two studies in this. One is detection of flash drought using evapotranspiration indices, and the second one is use of evapotranspiration in irrigation scheduling. So Nidhi Mishra and Annie Maria were the people who have been working. Unfortunately, they could not come, so I'm presenting here. So, yeah. So we all know conventional drought. Conventional drought, as you know, is characterized by its slow onset. We call it a creepy phenomena. Unlike the conventional drought, the flash drought is having a rapid onset. Generally, these flash droughts are subseasonal in nature, lasting for a few weeks to a month or 2 months, and it can also evolve into a conventional drought. So it is slightly a different sort of a drought, and it is mainly caused by the high demand in ET, atmospheric demand, caused basically by the high temperature, huge winds, and higher net radiation. And these sort of conditions create an energy limited by ET to a water limited ET. So you don't have water in the root zone, and therefore it could not satisfy the atmospheric demand, and therefore the drought sets in. So this happens in an accelerated way, so that the plant or the vegetation cannot cope up, and that's how the flash drought sets in. So we can decipher flash drought from conventional drought by the rate of intensification. In this study, we have two objectives. One, to identify the incidence of flash drought. There was an incident of high heat wave event during 2022, wherein the flash drought occurred. And we want to try to detect this using the evapotranspiration stress index, and to validate these observations, satellite-based observations using a flux drought data. At NRSC under National Hydrology Project, we have been deriving evapotranspiration for the entire country using NPP SAUMI data on a daily time scale at 750 meter resolution. And this is the data that we have used in this study, the database ranging from 2015 to 2023. So coming to the index, basically the evapotranspiration index is basically the ratio of AET by PET. The difference, deviation from its mean normalized by its standard deviation. So basically this index mimics almost like a precipitation-based indices, but the only advantage with these indices is it is a process-based indices. So precipitation indices generally have a lag time, lag relation with the vegetation or the crop phenomena of phenology. Whereas this index, because it is associated with the plant, so it is a process-based indices and more realistic in nature. This is the event that I was talking about, that during 2022, there was a heat wave event, and therefore there was a large negative deviation that occurred in the northern part of the India. And March and April is a critical phase or a peak phase of the wheat crops that is growing there. And therefore, we want to find out whether this really affected the yield of these crops during that time. So we used three eddy covariance stations that is available in this region. One is at Narayangarh in Punjab. The The other one is in Pantnagar, which is in Uttarakhand, and the Prayagraj is in the Uttar Pradesh. And you can see the Narayangarh is in the heart of the high intense heat wave region, while Pantnagar is slightly in the middle, and in the fringes you see the Prayagraj located. Now, IMD started issuing heat wave warning from 11th of March 2022. Heat wave here in IMD terms, it's defined as something beyond 5 degrees above normal is considered heat wave, and there are several other criteria to consider or declare it as a heat wave. And this severe heat wave conditions persisted from 11th of March or the entire March and till the middle of April. And the average April temperature it was the highest in the last 15 years recorded. We couldn't get the records of previous years. It could have been the highest overall. And if you see the evapotranspiration stress index, this is not working. Evaporation stress index, you can see till March 11th, the northern plains have more or less normal condition. And the intensity or the negative deviation started setting in from the second, third week of March, and then it intensified in the first week of April to the third week of April, and then again it returned back to the normal during the end of the March. So you can see a clear sign of a setting in of high intense event. Sorry. Yeah, high intense event, and then it is coming back to normal. So if you see the average ESI for the Punjab state, it was the highest during the March 25th timeframe, and the other two sites were more or less slightly lesser than that. If you, we collected all these weather parameters or the slow sensor map parameters that Bimalji was telling, and if you can see the Narayangarh, which is in Punjab, the top one is in Punjab, second one is in Uttarakhand, and third one is in Uttar Pradesh. You can see the air temperature was higher. The relative humidity was lower, indicating that it's a lot of vapor pressure deficit. So there is a lot of evaporative demand. The soil temperature is higher in Narayangarh, but much normal in Uttar Pradesh or Prayagraj. The soil moisture incidentally was lower in Punjab region, whereas Punjab state, whereas the other two are more or less in the normal regions. Probably they are irrigated. And if you see the actual evapotranspiration, the bottom channel, bottom row, you can see Narayangarh, there is a steep decrease in evapotranspiration from that peak point. So that is the typical characteristics of a flash drought, where the latent heat flux or the evapotranspiration drastically falls because the plant is unable to cope up with the demand and the non-availability of soil moisture. And similarly in Pantnagar, but more gradual, and in Prayagraj, it was much more gradual. And the estimated GPP from the flux tower shows not much of a deviation from the other 2 years. And if you see the seasonal cumulative AET and GPP, you can see that there was not much of a great difference, but in Narayangarh, that is Punjab, the GPP was much lower than the other 2 years. So here I am comparing 22 with 23 and 24 because the flux tower was installed in 22. So we don't have the previous year's data. So we are comparing with the next 2 years' data. And there was not much change in the other two sites like Pantnagar and Prayagraj. This probably is because of the soil moisture, that in the seasonal soil moisture in the Punjab site, it went down drastically during March timeframe or through the entire heat wave timeframe. Whereas the other sites were having soil moisture, probably they are irrigated. Here it was unirrigated, and therefore the crops were unable to get the enough soil moisture to support the demand, and therefore you see that there is it affected the yield. Incidentally, that year the estimated wheat production was 111 million tons, and Government of India scaled the production to 106 million tons after the heat wave set in. So to conclude that, I can say that the ET-based indices were able to detect the quick events or quick flash drought events. And this can be used as an early warning index because it is similar to the precipitation-based indices, while precipitation-based indices need not translate into a drought. However, here it's a process-based indices, which means there is really a problem there, and therefore it can be used as a early warning indicator. And the flux tower data were really collaborating with the findings of the satellite-based indices. So this is my first observation. There are a lot more analysis we did because of the lack of time to combine two presentations. So I am skipping those things. Going to the next study is the use of satellite-based indices for improved irrigation scheduling. As you all know that 80% of the water in India is consumed by irrigation, and it is very essential to optimize the use of water to enhance crop production. And the need for irrigation or the decision to irrigate the crop should be based on the actual deficit in soil moisture or the water level in the field in case of paddy crop, and it should optimize the crop productivity also. So the need for so this necessitates the need for developing a decision support system or decision making for irrigation scheduling. So irrigation scheduling is basically when to irrigate, where to irrigate, and how much to irrigate. And this is basically based on three primary concepts, like you find out the deficit in soil moisture conditions. You plant sensors, soil moisture sensors in the field, and then estimate the maximum allowable deficit and then try to irrigate. Or you visually observe the crop condition, crop water status, and then irrigate. Or you can adapt a soil water balance model, a hydrological model, or crop model to decide on when to irrigate. Now, in this study, this is a map of a command area called Narayanpur command area, which is located in the northern part of Karnataka, where Dr. Shekhar is coming from. And we have conducted this study in this command area. Basically, we tried to forecast the irrigation requirement for the next 7 days to the authorities so that they can release it accordingly. Basically, this command area is has a SCADA, that is a supervisory control and data acquisition system, which is a highly automated system, and they release water through that system. And since they have that system, we thought we'll carry out this experiment there and then try to suggest them our decision rules or irrigation schedules so that they can adapt and then see how much it is varying from their things. So, so the basic objective is to provide them the irrigation advisories for the next 7 days, given the present day's crop condition or the crop standing that is there. So major crops that is grown in this command are paddy, sugarcane, the biseasonal crops like cotton and chili. So this study was carried out during Rabi. In that case, the cotton, chili, and sugarcane was already a standing crop. And then during Rabi, there are new crops that is coming up, basically the paddy and the other dry irrigated crops that will be coming up. So basically here we adopt a basic soil water balance model. The basic inputs like remote sensing based using the optical data. We use the Landsat data here. It can be replaced by Trishna data when it comes through. So Landsat data is used for, optical data is used for crop classification. Here we use the in-season crop classification right from the start of the season. So the start of the season, we assume the cropping pattern to be the same as last year, which is already mapped. And then we try to improve as every single fortnight as we progress through the machine learning technique. And the evapotranspiration here, initially the model estimates through FAO method, but here we incorporated the actual evapotranspiration that is derived from Landsat data. And The crop growth stages is phenologies are derived from the crop classification map. Soil parameters are incorporated. And the weather parameters, of course, we get near real-time weather data is also used. So this data is used to estimate the irrigation. And we also estimate the potential evapotranspiration using Penman method. And the AET by PET gives the relative ET, which is used to gap fill the evapotranspiration between the two Landsat data. So you have a Landsat data today if you're using, evapotranspiration today using Landsat data. Until the next subsequent 16 days, we use this relativity into potential evapotranspiration to gap fill those evapotranspiration data for the site. And we also carry out a performance evaluation using evapotranspiration data. Here, there are two types of crops, the paddy. So for paddy, it's a field water level balance model that we adapt, a FAO-based model. And for soil, dry irrigated crops, it is basically the hydrological model, which is used to measure the soil moisture deficit. Basically, the irrigation is triggered when the soil moisture reaches the maximum allowable deficit or the management allowable deficit. So each crop has its own MAD, and the model tries to trigger the irrigation. So it's about the relative evapotranspiration to gap fill the data. So AET by potential evapotranspiration is used to gap fill the data between the two Landsat scenes or dates. And we verified the projections of these data at various locations of our sites. And we used our own ET to compare. The observed data is not the actual observed data. It is another satellite data. And it was more or less matching. And that's a good correlation. The top row shows the crop map derived for each branch canal. So first one is the overall command area. You can see the biseasonal crops that is standing during the start of the season. And as the season progresses, the biseasonal crops senescence happens, and therefore its area reduces. And subsequently, the paddy and the dry irrigated crops increase during the season. And the bottom row shows the irrigation demand that we have projected for each fortnight. So initial, because of the biseasonal crop, the irrigation demand was high. And as the season progresses, due to senescence, the irrigation demand decreases. And then as the paddy crop goes into a vegetation phase, you see the increase in demand and then peaking down. So it more or less mimics the crop phenology during the Rabi season. And basically, we also try to evaluate the performance of the command area by several means, like adequacy. Here, the adequacy index is being used, like crop water satisfaction index, a summation of AET by PET across the command area distributaries. And we see that the head reach of the command area is performing better, which has better adequacy, means the amount of water supplied is satisfying the AET, whereas the tail reaches are much more, has a poor crop water satisfaction indices. So the conventionally, the irrigation commands operate on rotations. So they keep open the gate for, say, in the first rotation, around 18 days, they have kept it open. And then in the second rotation, after 8 to 10 days gap, they open the second the rotation. Like that it goes. So it is not based on any principles. So blindly they open every with a gap of a week, they keep open the gate, and therefore the entire command is being flooded and irrigated. So it's not an efficient way of irrigating. Here we compared their amount of water provided or opened by the command area and the way we estimated using the model. You can see that at the start of the season, ours was estimating a higher irrigation requirement, basically because of the standing crop. But however, in the subsequent, that means you can see the red line, which is the actual release, is more or less on a very, there's no variations at all. Basically showing that they're just opening without any thing for the particular amount of day. And the last rotation is basically, since it is more number of days, it has consumed more of water. Whereas the model estimates are in line with the phenology of the crop. And on the right side, you can see the similar crop water satisfaction index during each rotation. And here again, you can see this is actually based on the irrigation released by the command authorities, and therefore even though they release so much water, the tail reach of the command area is performing poorly when compared to the head reach. And seeing the success of this project, we have developed a decision support system for this to be adopted by the authorities, wherein we use the satellite data, and this satellite data can definitely be replaced by the Trishna data when it comes, because we'll be estimating crop maps as well as the evapotranspiration. And we have the near real-time forecast meteorology, and UET will be going into the decision support system to provide the crop map, irrigation requirements, and the crop water performance indices. So there are several performance indices that will be rolling out that. And Ministry of Water is also very much interested in this decision support system. They want to roll it out on an experimental basis to other irrigation commands under various agroclimatic conditions. So this is my last slide, I think. Thank you. Thank you for your kind attention. Any questions?
Can we have some few questions?
Sir, I have one question, sir. So regarding the water stress, evaporative stress index, the mean and standard deviation was computed for on what interval of time?
The same interval of time for which we estimate use the AET. So it is for a weekly interval. It is weekly interval for mean, and standard deviation is for the weekly interval.
Over a long
period of time.
Any further question? Yes, Gilles.
What is exactly the mechanism to trigger irrigation in your model? Like, is it a soil moisture kind of?
Yes, it is we run the hydrological model which estimates the everyday soil moisture, and the soil moisture has we have fixed the management allowable deficit for each crop. Once the soil moisture reaches the MAD for that crop, then it is triggered. So in a command area, we choose the highest MAD. So for example, there are 2-3 crops and different types of soils are there. We use the highest MAD so that so these crops in the if it crosses that level, it will suffer. So we use the highest MAD and trigger the irrigation, which means we start estimating the.
And then do you keep some latency in the next irrigation, things like that, or?
No, it is a continuous.
It's a continuous irrigation.
Yes. Every day we estimate the requirement, and then we also provide, using the forecast data, we provide the next 7 days irrigation requirement to the authorities.
Okay.
Thank you very much.
So if no further questions, thank you, sir. Thank you, sir. So now I invite the next speaker, Dr. Rajesh Saran from IIT Kanpur, and he will talk about UAV-based thermal imaging for high-resolution crop water condition monitoring and futuristic spatial Calwell protocol for the Trishna mission.
Thank you, and good afternoon, everyone. It's a long day. People are tired to, listening about soil moisture and ET and everything else. So, yeah, so this is a project which we did, in collaboration with University of Leicester. One of the collaborator, Harjinder Sempi, is sitting at the back, and she will answer all the questions she has promised. And also, it was a part of a PhD student which we jointly supervised, Saroj Kumar Das, who is currently at UC Davis. So the idea of this project was to start using the UV-based high-resolution thermal imaging for deriving the soil moisture and also to do the crop water stress assessment. The motivation came from the fact that, in areas like the Ganga Plains, the agricultural areas are extremely heterogeneous. So there are plot level variability in not just in terms of crop types, but also soil type and the water conditions and water requirements and everything else. So there is, and also there is a very non-uniform surface and groundwater distribution of the areas. And there are anthropogenically modified irrigation strategies. Every farmer has its own schedule of watering and things like that. So therefore, what we tried to do is to use the high resolution thermal imaging from UV to create a field scale estimation of the land surface temperature and then convert that into crop water stress. So obviously, there's a huge implication of the thermal data for crop water condition and stress assessment. So this study was based at a critical zone observatory, which we have been maintaining for the last 8-9 years in heart of the Ganga Plains. So apart from a complete AWS measurements, we also do a 15-day campaign for soil moisture, groundwater. We also have an array of soil moisture sensors which are installed and which give us the data at every 15 minutes interval. And apart from that, we also have an in-situ radiometer installed up there, and then we use all of this data eventually to calculate the LST and then eventually the soil moisture stress. So you can see these are two drone images which can show you how heterogeneous the whole area is, not just in terms of the land use and land cover, water bodies, agricultural areas, and also some small habitations in terms of villages, but also in terms of the different crop types. There are different crop growth stages of wheat and paddy. Both wheat and paddy are grown in that area, and also from at every plot scale, you can see that there are crops which are at different stage of evolution. So there is this sort of necessitates the need for estimating the field scale, LST and then the soil moisture, because without that you can't develop a very efficient irrigation strategies. So this is the kind of data set which we used. We had several UAV flights, in 2019. For some flights, we had synchronous data from thermal as well as multispectral images, because that was used in some calculation for NDVI and others. And for some days, we could only fly the thermal, data. So we had a total of 8-9 sets of data, and then of course we also use EcoStress as spectral library to do our calculations as well. So this is the basic methodology which we followed here. So there are 3 sets of data. We have aerial data coming from thermal images and also multispectral images from where we generated the brightness, temperature, and emissivity. We also use the ERA5 reanalysis data for calculating the radiance, boiling radiance and transmissivity, and also we use the in-situ data coming from the the radiometer and the laser infrared temperatures. And then, of course, we combined all of these data sets to derive primarily 3 parameters: brightness, temperatures, which came from the FIR thermal imagers, and then, of course, the emissivity from either from the multispectral data of the Sequoia or the EcoStress library. And then we, of course, calculated the radiance from the Mortran modeling and so on. So that's the kind of a flow chart which tells us the the procedure which we followed for this project. These are some examples. You can see the brightness, temperature, which we calculated from the drone data. The FLIR camera was set at 100% emissivity and transmittance, and that's an image of April 2019. Then again, the NDVI calculation for which we, this is an image again for that, and then we did the Mortran calculations, from the ERA5 data. So that's the kind of a data set and the products which we generated from the UV data. These are, by the way, almost a sub-meter scale data set which we're talking about, 50 centimeter scale data set we're talking about here. So this is the land surface temperature calculation, which was done for 2 windows. It's a small watershed, but we flew the UV on small pockets, one in the upstream part and the second in the downstream part, and you can see that our our in-situ radiometer data and the FLIR derived LST, they correlate quite well with the R-square value of 0.93. So there are And the reason why we chose the two windows, because these two windows, even though it's in a small watershed, they're very different land and water bodies. And also, you can see some calculations of the overall temperature ranges were varying from 298 to 345 K, and that has again implications for winter and dry summer periods. There are differences between aerial LST and in situ determinator was less than 1 K, with a maximum temperature difference of about 4.93 K. So that's a reasonable correlation between the two sensors. We, of course, recognize that there are instrumental biases for both sensors to fluctuating conditions. We had limited data. We still have limited data, but I will tell you more about that, how we are planning to extend this data set as of now. So that's the crop water. And then we went ahead we used the VTCI approach to calculate the crop water condition, CWC, which is primarily based on a cold edge and a warm edge. That's the data set of 4 different dates in April, May, for both upstream and the downstream windows. And then what we can see that, is as per the standard VTCI space, LST VTCI space, we don't have a horizontal cold base, but slightly inclined base. And but then the relationship still holds because both the slopes of warm and cold edges are showing a negative relationship with NDVI and LST. Then we went ahead and calculated the LSTs primarily on, and this is what you see, that these are VTCI images for 4 different dates. And then we plotted the VTCI variability and different dates as per the location index. And you can see that the soil moisture plays a very significant role in the LST and DVI derived species. And as the CWC gets healthier from severely dry to very wet, the SM becomes higher and vice versa and so on. And what this plot shows you also that what are the different classes of the VTCI values, which were divided into 5 classes from severely dry to very wet, and how the percentage of the different classes varies on different dates. So that's a good estimation of the crop water condition. VTCI is a good proxy for the crop water condition. And then we estimated the field scale crop water stress for both paddy and wheat. There are multiple methods of doing that. We use the eco-stress data primarily, and also the CW flow estimation. That's the kind of a standard equation which we use for the lower baseline and for the upper baseline. We are using the LST derived from the UV data and also from the radiometer data. So of course, the issue which came that radiometer is providing us a very confined point level data, whereas UV is a larger window which has multiple lanules and land cover. So therefore, there was a challenge to relate the two, and the standard methods could not be used. So you can see that here. So for the lower baseline, there was not a problem, which was correlated very well with the radiometer data as well. But for the upper baseline, we had to devise a method which was based on histogram method, and we used the 95% and the 5 percentile data sets for deciding the upper baseline and the lower baseline. So you can see that this data here this is what we use the histogram method to decide the upper baseline and the lower baseline data. So that's what is shown here. For the upper baseline for radiometric sites, we didn't have to change much. So sorry, the lower baseline, but for upper baseline, we had to change. For the full UV window, we had to choose a different, upper baseline because the data was involving a lot of heterogeneity in the land cover. So therefore, then we went ahead and we calculated the CWSY at a radiometer site, a point for both rice and wheat crop season. And we also have the rainfall data coming from AWS. So you can see that, the crop water stress index matches quite nicely with the available rainfall data. We could identify the most non-stress condition as well as, the better conditions as well. But then when we look at the entire window covered by the UV data for paddy and for wheat, this is what we get. We have a reasonably good correlation between the UV-based, CWSI and the radiometer-based side. So, correlation is pretty good. And then the soil moisture, which we estimated, from the field conditions and the CWSI, they also show a very good correlation. So the data set is really fantastic, and we are very hopeful and very optimistic about this whole approach, basically. So the implication for the Trishna mission, before we go ahead with this slide, this is an ongoing activity. We are continuing this activity, the site and the measurements and the flights. So right now, as I said, our data set for the UV flights was limited. We are now covering entire season, so that, for the last few months, we have done already 6 or 7 flights in this year. This is a project funded between SAC and IIT Kanpur, and Mehul Pandya is involved in that project as well. So we would like to create a complete seasonal availability of the LST and the VTCI and also the CWSI. That's one. And then we are also extending that project to, we're trying to do the flights coinciding with either RSI data or the Sentinel data. So the idea is to develop the relationship between the two. This site is also going to be a CalWell site for the upcoming NISAR mission. And we will also have a science project which will continue to use the NISAR mission data as well as the ground data which we are collecting, plus the UV-based thermal imaging process will also continue. So given all of that, since we don't have a high resolution thermal data as of now, so the only way we can upscale the UV-based measurements is to use the SAR data coming from different data sets plus the NISAR mission. But when the Trishna data starts coming up, 60 meter, I think there'll be a very nice, comparison between the high resolution UV-based thermal data and the Trishna data coming in. So I think this is a very potential site for CalWell mission as well. And there are a lot of implications for this project because Trishna mission is very heavily based on, the soil moisture estimations and agriculture application. So this is a pretty good opportunity for all of us to utilize this kind of data and move from a point-based CalWell data set to a larger window-based CalWell activity. So that's one of the activity, and this kind of data can then lead to field scale estimation of the irrigation scheduling and of course the crop water stress. So I'll stop here for now. If you have any questions, I'll be more than happy to answer. Thank you.
Thank you, sir. The floor is open for question. Yes, John Louis.
Can you? Because maybe you were quick, so I didn't pay attention. Did you fly UAV different time of the day?
Yes, we try to match the timing of the flight with. For this data set, we flew something around between 10 and 12. But now we are trying to match the flight timings with either RSI timing or the Sentinel timing within an hour of difference. That's the kind of approach which we are following now. But yeah, we can always time it. Most of this data came around midday time, 10 to 12 p.m.
In one of your slide, you were showing that your CWSA is negative.
Did I? Can you go back to this slide? This one?
Yes.
No, this is this is the most non-stress condition basically. So this is because you can see this is coinciding with the rainfall. There's a lot of rain happened around that region. So that's why there is actually there is no stress, almost a saturated condition. So but we need to correct that kind of value. We can plot everything in the positive side as well.
And in another color coding, if you go back.
Yeah. Which one?
Back. Yeah, this one.
Oh, yeah.
Next one.
Yeah.
So your severely dry and very wet are both coded in black.
No, I
The
think
map.
this is the very wet is actually green. In
Okay.
the projection, it's not looking. I
Okay.
think the spectral resolution of the slides
Okay.
is not
Maybe
good.
my visual there.
I
Sorry.
can see. I know that I colored it, so it's
Okay.
black and green. So
Thank you.
yeah. Okay.
One question on the ET Calval perspective. Since it's a critical zone observatory, would you have, I have two questions.
Yeah,
Would you
sure.
have money to buy one eddy covariance tower?
We are in the process of developing a very large proposal where we are trying to put a Cosmos here, actually. So that is one we have in mind. But Eddy Tower, Shekhar is the boss.
No,
so he
because
can
I would have a
advise.
suggestion. Is that for Evaspa kind of Calval activities, we would like to have at least 4 or 5 measurements of ET, sensible and latent ET, for various vegetation cover and hydric conditions.
Yeah.
So like 5 or 6 points. And it comes out that with one eddy covariance tower money, now you can buy 5 or 6 Lycor 710. So it will be probably interesting to have a few Lycor 710 if you have money to do that.
Well, we can discuss that. But as you can see, this is a very highly, almost a very pristine agricultural area. So this is a very good site and very far away from the city. And so all these settlements which you see are very small huts and houses. So very far from any kind of anthropogenic disturbance. So very nice, pristine agricultural area where we have both crops, paddy and rabi. So it's a very nice site for doing addition measurements. So we have been discussing about putting up other sensors. I have just bought a, LiDAR. We are just started to do a LiDAR survey as well to do the LAI calculations. And also we have bought a chlorophyll, meter as well to start measurements of the chlorophyll. So these are the sensors which we can afford and buy. But Eddy Tower is something big. We can discuss that. Yeah.
No, but Lycor 710, it costs something. The instrument itself is costing roughly like 8 lakh.
Okay, not
so
much.
That's not completely unreasonable now.
Yeah.
So I think it's we are lucky to have it now at our disposal for Calval activities, actually.
Okay. Yeah, sure. Thank you. Yeah.
Yes, actually, what Zeel suggested. So tomorrow there will be whole Calval session, and from our side, Rahul will present the whole L2B, that ET and all this Calval will come in the L2B product and the calculation. So your whole efforts, actually, we would like to build in our overall efforts, so that I think it can be very coordinated efforts and we can get good data and many people that can work on that. So this is just my suggestion.
Sure, we'll be there. We'll be there. And as I said, this is already been selected for our NISAR core Calval site. So we'll be, we are doing all these measurements anyway. Yeah. Sure. Okay, thank you.
Next, I would like to invite Dr. Indrani C. Singh. She'll be presenting on evaluation of satellite-based thermal anomalies for assessing crop risk due to mid-term heat wave advisories.
Thank you, sir. Very good afternoon, everyone. I'll be presenting on the topic evaluation of satellite-based thermal anomalies for assessing crop risk due to mid-term heatwave advisories. To begin with the introduction, the consequences of climate change that increase the frequency of extreme temperature as reported by IPCC and leading to heat wave, which is a significant natural hazard. Similarly, in addition, that World WMO also reported that heat wave occurrences are 30 times more prevalent in India. This intermittent heat wave during post-monsoon season, specifically in semi-arid and arid climate, pose strong thermal anomalies coinciding critical wheat crop growth stages. As we all know, the wheat crop is a thermal sensitive crop, and the temperature above 27 degrees centigrade, it slows down the grain filling rates and increases the number of sterile grains. And in addition, the temperature above 30 degrees centigrade inhibits the photosynthetic processes, with reduction in grain filling rates causes severe impact on crop yield. As we all know, the many thermal Earth observation data has the potential for detecting the thermal anomalies at a spatial temporal scale. Therefore, if we construct a thermal-based weather index, and that can act as an effective risk management strategy that has already been defined in Pradhan Mantri Fasal Bima Yojana program, that can in the perspective of crop insurance, that can provide a transparent solution by linking weather parameter directly to crop loss. In this context, we have constructed two indices. One is the heat wave magnitude index, which was formulated to evaluate the midterm thermal stress and anomaly, and another is the combined index that was constructed based on the linear combination of land surface and biophysical parameters to assess the impact of heat wave on wheat crop. Next, please. Now, the study area that has been selected as Maharashtra, the states of Maharashtra and Madhya Pradesh in India, that witness a special variation of thermal pattern during the important wheat growing season, that has been observed from the analysis of the long-term average LST at monthly scale, that depicts a wide variation of significant variation of thermal pattern over Indian regions, specifically if we focus on the Madhya Pradesh as well as Maharashtra. And the list of data that were used at the for thermal anomaly, MODIS Aqua 8-day composite day LST data were used, that is during 2003 to 2023. Then for detection of vegetation and canopy water stress, MODIS Aqua 16 days composite NDVI and MODIS 16-day composite NDWA was used for the period 2009 to 2020. Then one of the important component that was constructed, that is the evaporation stress index, that is the ratio between the actual evapotranspiration to the reference evapotranspiration, where the actual reference evapotranspiration at daily scale were computed using the FAO 56 model, using Penman-Monteith formulation, using daily surface insolation data from the geostationary satellite, and the short-range weather forecast data from WRF model. And that daily reference evapotranspiration were integrated at the monthly scale, and the monthly actual evapotranspiration data were obtained from USGS, that is during the period from 2009 to 2020. And the crop yield data for the period 2009 to 2020 were obtained from Directorate of Economics and Statistics, Department of Agriculture. Next. Now, this is the flowchart of the methodology. The entire methodology were carried out in Google Earth Engine cloud platform, where the heat wave magnitude index were computed, where the time series of 8-day composite day LST were used, and these times during January used for the reference period 2003 to 2023. And this time series of 8-day composite LST data that were renamed as DY-1 to DY-89, covering the major wheat growing period, that is from January to March. And the percentile-based approach was used, where the heat wave for a particular DY was computed when the day LST for a particular DY, if it exceeds the 85 percentile threshold percentile of the threshold of the climatological threshold of the reference period. Then this is followed by the computation of heat wave magnitude index at DY scale. That is the ratio between the differences between the heat wave LST and LST at 25th percentile and divided by the LST at differences between the LST at 75th and 25th percentile. So heat wave magnitude, after computing the heat wave magnitude index at weekly scale, DY scale, that was integrated at the monthly scale. To compute the heat wave magnitude index at the monthly scale. Now, another indices, that is the combined index, which is a composite index that has been derived using the satellite-based LST and DVI evaporation stress index and NDWI at monthly scale using the data from 2009 to 2020. Now, all the data sets were standardized using the JET score, and this is followed by the computation of principal component analysis to compute the composite index at monthly scale, where each input variable is assigned with a particular weight based on its contribution to the overall performance. And then the heat wave magnitude index at monthly scale and combined index at the monthly scale were then correlated with the yield at the monthly scale during January to March. And this is the total structure of the satellite-based heat wave insurance product. Next, please. Now, coming to the results, this shows the regional scale assessment of the thermal anomaly and heat wave. And in Madhya Pradesh and in Maharashtra, there were 9 districts where observed heat wave events during 2018 and 2019. And there are 2 districts in Madhya Pradesh, that is Tikambar and Chhatarpur district. They observed heat wave events in the year 2018. If we observe that in the year 2018, the 9 districts of Maharashtra that were observed heat wave during DY1, that is in Akola, then DY81, then DY9 to DY33, that was found to be most vulnerable DYs, and 4 consecutive DY heat wave were observed in Amravati, Washim, and Awadh during 9 to 33. Then 3 consecutive DY was observed in Akola, Buldana, Aurangabad, and Jalgaon during 17 to 33, and 2 consecutive DYs was observed in DY 17 to DY 25 in Dhule and Wardha. And in 2019, during DY 1 to DY 17, 41 to 49 and 65 to 89, these were found to be most vulnerable. And Aurangabad exhibited most effective district with 4 consecutive DYs heat wave events from 1 to 25, 65 to 89, then 2 consecutive heat wave events in 41 to 89. Then scattered heat wave events were also observed in Akola, that is the 1, 17, 81, 89, Awadh in 17, and Washim in 1. Next. This is the heat wave frequency in the affected frequency in the affected district of Maharashtra and Madhya Pradesh. And in Madhya Pradesh, we have observed that in 2018, this Tikambar district exhibited highest number of heat wave events, that is 8 as compared to Chhatarpur district 5. And in 2019, on Chhatarpur observed a single heat wave event. But in Maharashtra, the 2018 highest number of heat wave events were observed in Amravati, 5, Jalgaon 5, Washim 5, Awadh 5, Akola 4, Buldana 4, Dhule 3, Wardha 3, and Aurangabad 1. And 2019, highest number of heat wave events were observed in Aurangabad 10, Jalgaon 9, Dhule 8, Buldana 8, Amravati 7, Wardha 5, Akola 4, Washim 1, and Awadh 1. And in 2020, no heat wave event was observed in Madhya Pradesh as well as Maharashtra. And this magnitude and intensity of heat wave in a particular month is very much important and depends on the frequency of the heat wave events. How much, if the frequency is more, then the magnitude and intensity is also more. These are the temporal evolution of heat wave magnitude index. We have it has been observed in the year 2018 in Tikambara and Chhatarpur district. Magnitude is more as compared to 2009 and 2020 and 2020. No such magnitude of heat wave was observed. Similarly, in Maharashtra, 18 and 19, the heat wave magnitude intensity was more as compared to 2020, and there is a scatter plot between percent division of LST and heat wave magnitude index. It shows an increase positive correlation, and a crossover point also observed, that is below that certain point, that when the heat wave magnitude index, that point is corresponding to negative deviation in LST, that is found to be the generally that can considered as the identification of the low intensity, no intensity, less intense heat wave magnitude location. And it is a primary driver for detecting the anomalies in the biophysical parameters that ultimately affect the crop yields. And next. Now, the temporal evaluation of crop combined index. So these 4 parameters we have integrated together to generate a composite index, and LST shows a negative correlation with NDVI, NDWI, and evaporative stress index. And the 2018 Chhatarpur, the condition of crop, and this composite index, the range is -3 to +3, indicating the poor to good condition of crop. And Chhatarpur, if you observe Chhatarpur and Tikambara district in 2018, the condition of the crop was poor condition of crop, is showing the poor health of the crop is poor. And if you see 2018 and 2019, the crop condition was in Maharashtra, the condition of the crop is poor as compared to 2020. Next. Now, this is the heat wave magnitude index versus combined index. District-wise analysis was carried out at a monthly scale, which showed a very good correlation, good measure of association among the two parameters, two indices. And this scatter plot, the combined pooled data also plotted, which also shows a very good correlation. Therefore, we can conclude that when there is an increase in the intensity of heat wave, the combined index decreases, reflecting the heat stress curve. Next. Now, the district-wise analysis also were carried out on monthly scale in between the heat wave magnitude index to crop yield, which shows a negative correlation, and also it shows a good measure of association among the parameters. And next. And response of combined index to crop yield, it also district-wise analysis, it also shows a very good measure of association, and it shows the positive correlation among the parameters. Next. And district-wise correlation analysis also were carried out among the yield and combined index, and yield versus heat wave magnitude index, which also shows a very good measure of association at district level. And this combined approach of heat wave magnitude index and combined index, that can be used for identification of potential heat wave affected zones and for conceiving zone specific adaptation strategies for shielding wheat crop from heat wave events. And therefore, to conclude, this combination of this heat wave magnitude index and combined index, that can be together, can be coupled together to derive, to design the satellite-based heat wave weather insurance product that is very much unique, and that can give us information at the monthly scale and with a threshold level to identify the heat wave vulnerable zones, and it can also assess the heat wave impacts on crops. And the continuous monitoring of this heat wave magnitude index, it provides quantitative estimates of the magnitude, intensity, and duration of heat wave, which is crucial for understanding its effect on crop growth. Additionally, we have also computed that combined index that integrates the various satellite-derived parameters that evaluates how heat wave affects crop vigor and yield. And since it has been generated at a monthly scale, Therefore, if this satellite-based heat wave insurance product is highly recommended for assessing the midterm heat wave advisory during the critical crop growth phases. Therefore, this insurance product can offer multi-phase insurance protection for farmers throughout the crop growing period. And it also, this insurance product represents a pioneering approach in climate resilient agriculture and for faster claim of indemnity in thermal-based weather crop insurance. And with the coming up of the Trishna mission, when there will be a thermal and V-sphere will be available at final resolution, then heat wave magnitude index and CI constructed for using those spectral bands can better predict the impact of in-season heat wave on crop yield at finer granularity, and which will be useful for designing a heat wave weather insurance product for faster claim settlement by farmers with better accuracy. Thank you.
Thank you, Dr. Indrani.
Yes,
Very
sir.
nice presentation.
Thank you, sir.
The floor is open for 1 or 2 questions.
Indrani?
Yes.
See, sir. Presentation is very fast. You show so many things in very less time. My question is, you showed that you saw the heat wave occurrence in Maharashtra in 2018 and 19, but strangely no heat wave observation in 2020. Whether it is measurement limitation or something else?
Whether it is?
Measurement limitation or something else?
No, yeah, we have, this is when we computed this heat wave magnitude index, then that if you have observed in that similarly when we have computed this composite index also, so in 2020 no heat wave was observed in 2002, and we have
verified from somewhere else?
No, verify in the sense that literature we have, from the literature and some report we have verified, but not field observation.
Second thing is, how are you determining the heat wave magnitude index? Either are you getting it directly, this product, or you are computing yourself?
Which one? Heat wave magnitude
index.
that has been, I have constructed this index.
You are.
Yes, yes.
Okay.
Presentation was very wonderful and informative. Just have a small query. Somewhere you mentioned this product can also be used for the weather-based crop insurance.
Yes.
So currently, the term sheets available for different crops in India are based on the ambient temperature and their threshold levels, temperature max, minimum, and mean temperatures. How this LST can be used for?
I'm not getting your question actually.
So currently the term sheets available for settling the claims of the farmers are based on the minimum, maximum, mean temperatures.
Okay.
How this LST product can be linked to
see LST
assessing the claims.
His question is that now the terms and conditions given by the government on the basis of air temperature.
Term sheets.
Term sheets. Oh, I'm not aware of this.
Can be useful in that.
We can go
for this one, assessing the claims for the farmers for whether in the weather-based crop insurance, we generally use the term sheets.
Okay.
So for particular crop stage, if the threshold temperature minimum maximum above from the 1 degree or 2 degrees, some insurance will be given to the farmer kind of thing. So you're mentioning this product can also be used in the weather-based insurance that is particularly based on the term sheets. So how this LST product can be linked for assessing the that
yes
growth assessment kind of thing, but settle the farmers.
Shesh, you convey that air temperature.
Air temperature, minimum temperature.
Yes, actually you are talking about weather insurance, no? So that weather insurance, first of all, the term sheets with respect to air temperature maximum and minimum, only LST noon and night time need to be converted through some mechanism into that, and then you can use as such in the air temperature, in terms of air temperature. But in the restructured weather insurance manual, if you see that it is clearly written that you can come up with a new index, but any new index of related to weather insurance, it needs to be correlated to the yield anomaly. Then only it can be accepted. So this study is towards that to establish some new index. And another part is that any weather insurance till now, no satellite data are being used in India. So this is the starting point. We have already come up with another rainfall based index for the weather insurance. I think recently it is
Recently it has been published.
So another thing is the heat wave factor. So these are all R&D studies which will finally lead to some convincing results to the policymakers also to adopt such kind of indicators for the weather insurance based settlement.
I think idea is that if we have some IMD based air temperature data also, and
Maximum,
we can overlap on this, then we have a more confidence.
We can link.
I have one small query. The thermal anomalies you are showing in the third slide.
Yes, sir. Which one?
Thermal anomalies, no?
Yes, sir.
All
Yes.
India. So most of those quite matches the type of soil. So mostly it is black cotton soil areas. Okay. So they have a higher thermal radiation.
Yes, yes, sir. Yes, sir.
Emissivity.
Yes, sir.
So I think you should normalize that in future studies. Maybe the difference between the soil and the thermal
Yes, sir.
are quite different.
Yes, sir. Actually, these things will be taken into consideration in our later part of the study, and this is a preliminary study.
Okay.
So we have tried to
Yeah.
develop the new index.
Yeah. So
Thank you, sir.
there are no questions. Thank you, Indrani.
Thank you, sir.
We'll go to the next presentation. We are running short of time, and we'll invite Mrs. Sangeeta Rani from IIT Mumbai. She'll be presenting on integrating vegetation index-based evapotranspiration disaggregation and crop water balance model for farm scale vineyard irrigation estimation. Hopefully this is the last presentation. So.
Yes. Good evening, everyone. Today I'm going to be presenting a topic, integrating vegetation index-based evapotranspiration disaggregation and crop water balance model for farm scale vineyard irrigation estimation under the supervision of Professor Ishwar Rajashekharan from IIT Bombay. To start with introduction, irrigated agriculture accounts for over 70% of global freshwater consumption and more than 80% in semi-arid regions. Monitoring and quantifying vineyard irrigation volume is crucial for sustainable water management. However, detailed irrigation data at plot scale level is often lagging. While remote sensing studies have used microwave soil moisture data to estimate irrigation value with the help of water balance calculation. And these approaches faces challenges such as co-spatial resolution and shallow sensing depth that do not fully capture the root zone storage. A promising approach for accurately quantifying irrigation is combining remote sensing ET at a fine scale from optical and thermal with crop water balance model. Study area I have chosen is located in the Central Valley of California. It is a vineyard farm. It is a experimental block. It's like a 400 by 400 meter. There were 4 AD covariants were installed at a distance of 200 meter to monitor the micro observation variables as a part of GRAPEX project. The data was given to us during the period of 2018 to 2020. And the figure represents the study area. It's a vineyard, it has intermediate bad soil. So I got the seasonal irrigation volume during the year of 2018. So during that time, the LST data is available only from the Moody's. So I have taken the data from daily Moody's LST and I used Sentinel NDVI. And the leaf area index is modeled from using the SNAP toolbox. And from the eddy covariance data, I used radiation
air temperatures and wind speed and relative humidity for estimating the ET at sentinel time interval. And the latent heat flux is used for the validating the ET. And the field observed block-wise, there are 4 blocks in the study area. Field observed block-wise seasonal irrigation volume are taken from the literature Diurnal et al. 2021. So the model I have used is SPAST model, and disaggregation model I used for DISRO. The SPAST model is developed by G. Boulay et al. And it is based on 2-source model, and it is a single pixel model, and it runs in a 2 configuration, in series and parallel configuration. In series configuration, in the single pixel, same pixel, soil and vegetation is coupled together, and together it interacts with the atmosphere. In parallel configuration, it separates the soil and vegetation, and it individually interact with the atmosphere. In parallel configuration is it's well suitable for my study area vineyard, because my study vineyard is as a intermediate bad soil, and it tries to solve the surface energy balance using with the help of land surface temperature from the remote sensing data, and I have given the LAI from the remote sensing data, and plus meteorological variable like solar radiation, air temperature, wind speed, and relative humidity. To calculate, finally it will give the soil evaporation and plant transpiration separately, and the latent heat is the summation of soil evaporation and plant transpiration. So latent heat flux I calculated from the SPAST model. So at a instantaneous mode is instantaneous scale. Latent heat flux I converted into daily ET using the relationship. Like first I calculated RG factor. The ratio of latent heat flux divided by RG instantaneous is solar radiation instantaneous from the meteorological variable. Then the solar radiation factor is converted into a ET daily using the daily average, day average solar radiation, that is also from meteorological data. So from the SPAST model, I calculated ET at coast resolution at 960 meter. It's further disaggregated into 60 meter using the disaggregation model. I have chosen the disaggregation model is name called DISRO. It represents disaggregation of solar radiation ratio. From the SPAST model, RG factor at coast resolution and the Sentinel to NDVI is resampled to 960 meter coast resolution. This DISRO model is similar to LST NDVI triangular space. It gives the relationship between the solar radiation factor and NDVI. That relationship is scale invariant. It's applied to the fine scale to estimate the RG factor at finer scale. From the finer scale, RG factor is further converted into ET daily using this calculation. This is the overall methodology. First, I used MODIS LST at 960 meter and Sentinel-2 resample to 960 meter plus meteorological observation. First, I run the SPAST ET model. The parallel configuration is suitable for my study area, so the steady landscape. The ET at 960 meter further disaggregated into NDVI at 60 meter using the DISRO disaggregation model. The disaggregated ET, 5 days ET, and again interpreted into a daily scale ET, and used in the FAO 56 crop water balance model. And finally, I calculated the irrigation estimation. So this figure represents the comparison of SPAS ET and in situ ET at 960 meter resolution. In x-axis, the ET from the flux tower. This color bar represents the 4 flux tower, and the y-axis represents the SPAS ET. This table shows the RMSE and bias. I got the maximum RMSE at the tower location T3, 1.4 mm per day. So after disaggregation, most of the disaggregation model, after disaggregating into a finer scale, it improves the error. But this DISRO model, it reduced the error from the first 2 tower, and the third and fourth is slightly improved. This shows the NDVI-based DISRO model works fine. This figure represents the spatial pattern of SPAS ET at 960 meter is the left-hand one, and disaggregated at ET at 60 meter. The disaggregated ET at 60 meter in each pixel showing the variation of ET at the steady area. The black triangle represents the eddy covariance locations. This one is error performance. So the red one shows the course resolution 960 meters sparse model error performance between the model and the in situ data, and the green one shows the after disaggregation the error performance. So most of the points green after disaggregation the error was slightly reduced. So from the 5 days ET data, I interpreted into daily scale using linear interpolation, and I used for the daily water balance simulation. So for the 4 blocks, I run the daily water balance with the help of ET, daily estimated ET, and calculated the seasonal irrigation volume only for the major growing season. So from the estimated seasonal irrigation volume is slightly lower than the observed irrigation volume. It's error showing 10 to 20%. This is for the block 3 x-axis showing the major growing season from late May to late September. During the time only they will do the irrigation. The previous bird burst and all, initially they refill the root zone storage. So y-axis showing the irrigation in mm. There are 21 events, bloom stage from late May to late July. And the Verizon stages start from the August to September 8. In conclusion, this study aimed to estimate ET at a final resolution using a simple NDY-based disaggregation model. The sparse model patch configuration was suitable for vineyard landscape, and the DeSero model was tested with 60 meter sentinel NDVI over vineyards. The NDVI-based disaggregation consistently improved ET estimates throughout the growing season. This study simulated the irrigation volume events at the field scale using classical FAO 56 water balance model, and it validated with the observed value. The error showing a average of 14% lower than the observed data. In conclusion, this research show the potential of using high resolution ET coupled with the water balance. It's highly helpful to irrigation management at field scale level. Thank you. Yes, sir.
Questions there?
I have one suggestion
Yes,
that you have assimilated LAI from Sentinel.
Modeled from Sentinel. Yes.
From 960 meter. Again, you have desegregated using Sentinel.
No, I used NDVI.
UNDVI.
LA is only for sparse calculation.
As far as calculation. But reflectance is going in the same way. So my suggestion is that you assimilate LAI from some different sources, multispectral, and then disaggregate using Sentinel-2.
Yes, sir. Actually, the study period is very old, like during 2018. So during that period, only the Moody's and Sentinel are the only available.
Oh.
Only I have a query regarding the vineyard you have shown from May to September.
Yes.
There was a ET that how it is changing, and you are suggesting that irrigation is required. Have you considering the weather forecast, because July to September is having rainy season, and there is a high water demand in your result. It was showing more than, I think, 12 or 22 mm per day.
Actually, in California, the average annual rainfall itself very low. It's 120 mm or 12 centimeter only. So once the harvest done, they after the harvest they refill the soil. They supply with the help. They supply 400 mm water to refill the root zone storage. That will meet for the till the bud burst period. So only the major growing season only they start irrigate one. That block is a treatment block where they induce treatment. It's based on that, they're trying to deficit irrigation. They follow drip irrigation.
I have one question. You have utilized Sentinel-2 NDVI to downscale the ET to 60 meter.
Yes.
But from Sentinel-2, we can get NDVI at 10 meter. So what is the reason that you have stuck up to 60 meter? Is it been optimized that there you get best performance?
Before I tested using Planet Scope also at till 3 meter. This time we are just tested 960 to 60. That it's a reasonable. We thought it is reasonable.
Okay, thank you.
Thank you.
Thank you, Sangeeta. Thanks. Good presentation from you. And now over to organizers.
Yeah.
And am I also one of them? Thank you.
Yeah. So as we come towards the end of the session, as a token of gratitude, we will like to present our session chairs with a memento. I request Dr. Ishwar to come on stage and present the memento to Dr. Chandrasekhar. I again request Dr. Ishwar to present the memento to Dr. Rahul Nigam. So as we conclude this session, we thank Dr. Chandrasekhar and Dr. Rahul Nigam for conducting this session wonderfully. We also thank Ayan Das for carefully noting down the minutes of the meeting. We extend our gratitude to all the speakers and the audience for this fruitful session. There are some important announcements to be made. There will be now a tea break. After that, the cultural event will start from 7 o'clock, followed by the director's dinner. And tomorrow, the sessions will strictly start at 9 o'clock. There are two very important sessions. One is the CalWell and the other is the downstream applications in the forenoon. So your presence will be greatly appreciated.
So those who are staying in different hotels, especially Novotel and nearby hotels, so buses will come tomorrow 15 minutes early. So make sure that you will be in the hall by 9. Okay, thank you.